level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience.
I think, yes, as far as I know, I will check right now. Down the road?
Yeah, well, it's going like tire, or that may be standing in front of it. Maybe it's gone by now, but yeah.
Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience. Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience.
This meeting is being recorded.
Welcome to the NASA Exploration Science Forum. At this time, you may adjust your audio to a comfortable listening level. We will begin at the scheduled start time. Thank you for your patience.
Good morning, everyone, or good afternoon, or good evening, wherever you are in the world. Welcome to the NASA Exploration Science Forum. This is our 13th such forum, starting with the Lunar Science Forum a number of years ago, and the second all-virtual meeting. I'd like to start with a few Acknowledgements and thank yous. First of all, we have a number of VIPs attending. Administrator Bridenstine will be joining us in just over an hour. NASA Chief Scientist Jim Green, I believe, is online now and will be giving a talk tomorrow. Lori Glaze and Mark Kirisich. Lori from Head of Planetary Sciences at the Science Mission Directorate. Mark, a division director within HEO MD, will be joining us on Friday for an interesting session. We have a number of headquarters speakers coming up very shortly: Ben Bussey, Sarah Noble, Jake Bleacher, and Andrew Petro. Also would like to thank Shoshana Wider and Victoria Andrews and Betty Siegel, as well as Brad Bailey all at headquarters for the continuous support. And I want to thank the Science Organizing Committee for their help in putting together what I think is going to be just a great program. So Rachel Klima, Tobin Munsat, and David Rupetti were the chairs, and I want to thank them as well as the entire SOC. And then I also want to thank the virtual organizing committee for the forum. And we're having this meeting virtually. We also had all the preparations virtual as well, and the team did just great. So this is comprised of the Survey Central staff, as well as Lisa Faithhorn, who joined us as an advisor. We're also going to be joined on Thursday, tomorrow, by Masaki Fujimoto, a senior leader in JAXA in Japan. And then before I go on, I want to acknowledge my predecessors, and particularly David Morrison, who just celebrated his 80th birthday. So I'd lead in a round of happy birthday, David, but I don't think you want to hear me singing here. And also my thanks to Yvonne Pendleton as well. It's really great to have everyone here. Back in March, when it started to become clear that this meeting wasn't going to be in person, we wondered what it might be like. I wondered personally about and worried about the potential for not getting a response. Would we send out the call for abstracts and get just a handful? Well, I shouldn't have worried. We have a record number of attendees, and we're at just shy of 600, and also a record number of abstracts at 185. So with that, the Science Organizing Committee had quite their job ahead of them organizing things, but they did it very well, and we have quite a great meeting ahead of us through Friday. I want to take the time right now, many of you have probably seen it already, but I want to take the time to announce our annual awardees. And then tomorrow we will have the formal ceremony in which you'll get to hear them talk. So starting with the Susan Mahan Niebuhr Early Career Award, we have awarded Amy Fagan and Ryan Watkins jointly with this award. Following that, with the Angioletta Corradini Award, we've awarded Harry Hiesinger of Germany this year with that award. For the Michael Wargo Award this year, we've awarded Mark Robinson. And then finally, for the Eugene Shoemaker Lifetime Achievement Medal, we've awarded Brad Jolliffe. So like I say, we'll have a ceremony tomorrow, and I want to congratulate everyone, and I wish that we could all give them a round of applause. We're lucky to have the tech team that we do at Survey Central. We went into the pandemic with, I have to say, a lot of experience at doing the kind of work that all of us have had to do. We thought hard about the forum and what did we want to do with it. We have a lot of new features that you'll see. I want to also start off by saying I think of these events in the context of a wedding. So most things are going to go right and be wonderful, but plan on a couple of things going wrong. The thing is that we have our very capable team to fix it, and so I'm not worried at all. But if you do have problems, go to the Best Practices tab on the forum website, and there's a link to connect you to our tech team, as well as a lot of other information that you will hopefully find useful. One of the features that we have this year that I think that we've done a much better job with as compared to the last forum is posters. And so posters, in my way of thinking of it anyway, represent the bulk of the science that we are doing at the forum. We have 98 posters that you can take a look at, and you could take a look at them anytime you want and see recordings that people uploaded, as well as the posters themselves. And then during the poster sessions, you'll be able to talk with the poster authors. And so we have signups for this. All of you should have gotten my email last night, as well as Christina's email earlier saying how to do this. And so I strongly encourage you to sign up. It won't work if we don't have attendees. So please do attend the poster sessions, and I think it's going to be exciting. And I particularly encourage you to sign up for the student session as well. Just a few other notes. We encourage you to turn your camera off as well as your audio during presentations. We will have a group photo after Professor Dina Khalil's talk. Her talk follows Administrator Bridenstine's. So please hang around, don't go away to the break too early. And we'd like to have everyone turn their cameras on at that point and get a group photo. One thing, as compared with last year and the years when we do this in person, the recordings are going to be available just a bit later than normal. One of the explanations, the prime explanation for this is bandwidth, and let's just say it's not what it is at home where we all are, as compared to what it is at NASA Ames, where we usually hold the forum. Furthermore, there's no errata on the schedule, so please check the schedule daily. We have made some changes. For instance, the time that Lori Glaze and Mark Kirasich are talking on Friday has changed by a half an hour. That will be reflected later. It isn't yet reflected, so do check the schedule daily. So I just want to say a few more comments here, and then I'm going to turn it over to my co-chair for this session. So to say we live in unusual times, that's become perhaps the most overused phrase that we've all heard in the last few months. There's a big cost to all of this, and that's in people growing apart and communities drifting. And I think that when our team got together in March, when we realized that we're going to have to move this meeting from being an in-person one, we were then planning it for Boulder, Colorado, to an online one, we thought hard about these challenges. A large part of our community had just suffered the cancellation of LPSC, and many of you out there were planning to go to LPSC, and I know that the talks are always wonderful, but the companionship of other people is equally wonderful. And so, and I know from talking with many of you how hard that hit. But on top of that, many of these friends that I have in this community are just starting their careers, and they face some unique challenges, such as not being able to mingle and meet with future advisors and employers. We decided that despite an online format this year, we're going to do our best to bring people together and make connections, and I hope we're successful. More recently, the country's experienced an enormous amount of unrest, entirely justified after so many years of not dealing with some core problems. We've decided to try to help in that way too, and we recently formed a diversity and inclusion focus group under the very capable leadership of Dr. Jay Greer. We're featuring a talk this morning on that topic right after Administrator Bridenstine on some of the challenges and opportunities we have by Professor Dina Khalil of Howard University, who does research in this area and is part of the resource team under the leadership of Dr. Jennifer Heldman. My sincere hope is that when we all get together next year, we will have made some measurable progress in this area. Please hold us to that. With the philosophy of more next-gen involvement, you probably noticed that we have 2 co-chairs for each of our sessions this year, one of them being early career. This opening session is no exception, and with that, I'd like to introduce Dr. Ariel Deutsch. Dr. Deutsch is a recent PhD graduate from Jim Head's lab at Brown University, and we're lucky that she will be joining us at NASA Ames this fall for a postdoctoral fellowship under the guidance of Jennifer Heldman. Ariel, please go ahead.
Thanks, Greg. I'm so happy to be able to help welcome people online today. ESF is always one of my own favorite conferences. And I think especially now, as Greg was saying, it's so important to have an opportunity to come together and share new ideas and advance discussions in science and tech and exploration. And we have a really great program over the next 3 days, which excitingly features lots of student involvement. So I just encourage everyone who's tuning in to consider how to reach out to and support those early career participants. As Greg was saying, especially now in these difficult times, which are creating some challenges for people that are just beginning in the field. I think that for students is integrate the student lightning round talks into the program. So about mid-program today and mid-program tomorrow, we'll have the chance to learn from some of the students about what they're working on, and this will be really great, so please pay attention to that. And then hopefully also everyone's aware, but we have 2 virtual poster sessions, one at the end of the program today and one at the beginning of Friday. And both are also featuring lots of excellent student work. So please keep an eye out for the student presenters, and they're denoted in the program with an asterisk. And Ricky and Olive Serby has really put a lot of thought into how to make these virtual poster sessions as personable as possible. So we have these individual poster Zoom rooms, and it would be really great if we could all make an effort to visit the posters. I think the only thing worse than standing by your poster for an hour at a conference and not having anyone come by would be sitting in a Zoom room by yourself for an hour and not having anyone come by. So let's definitely support one another and show up and really engage in these poster sessions. As Greg was saying, that face-to-face aspect or that hallway run-in that we have at normal conferences is something we're all missing right now. So hopefully these Zoom rooms can address some of that void. I know that for me, this conference has always been such a supportive place ever since starting graduate school. And I hope that the students and early career people can continue to count on all of the incredible mentors that really make this community what it is and maintain communication and contacts and support networks. So finally, I just want to recognize the success of Loon GradCon, which is a student-run conference that always precedes ESF. And this year, Loon GradCon took place virtually just last week. And for the first time, the program filled 2 full days as opposed to just the historical 1 day. So massive thanks to Serby for supporting this as always. And then of course, the student organizers who made this a possibility. And so I don't want to take any more time. We have a brilliant program. I'm really looking forward to it. So I'll give it back to you, Greg.
Great. Thank you so much, Dr. Deutsch. It is such a pleasure to call you Dr. Deutsch. I was at her thesis defense just a handful of months ago, and I am just, with people like her in the community, lunar science, our field has a very, very bright future. So thanks to you, and thanks to all of our next gen attendees and speakers and poster presenters for what I know is going to be just a fantastic contribution to our community. So with that, we're ready to start the NASA headquarter programs panel. The first speaker in this panel is Dr. Ben Bussey, and Dr. Bussey is a former PI with both NLSI and CERVI. He did some key enabling research on lunar science, and he moved to NASA headquarters a few years back to be the chief scientist for human exploration. And more recently, he has joined the Science Mission Directorate, where he currently is acting leader for the Exploration Science Strategy and Integration Office. So Ben, please go ahead. Ben, can you, I'm not hearing you.
Okay, can you hear me now?
Yes, yes.
Okay, so for those of you on the phone, you also have to, I had to end up doing the internet version for Zoom, because, but we won't go there. Yes, so good, hello everyone. I'm going to give you a very brief overview of the Exploration Science Strategy Integration Office, where we are. Most of you remember my predecessor, Steve Clark. For those that are interested, he has become the Deputy AA for Aeronautics, which is a great challenge for him. And I am temporarily running the office. Next slide, please. Great. So here's our portfolio. Our portfolio is to conduct an integrated strategy for exploration science by collaboration within the divisions, the SMD divisions, as well as with the other mission directorates and international space agencies. Many of you would have possibly have heard of something called LDEP, or the Lunar Discovery Exploration Program. That is a significant portion, but not everything in our portfolio. So the reason we exist is to help the development of lunar surface science instruments, to use the commercial companies to deliver those payloads to the moon, to develop mobility systems, to expand and enhance science investigations on the lunar surface. Leveraging international partners is a key part for what we try and do. We're also looking at the right way to obtain new scientific data from lunar orbit, predominantly using CubeSats and SmallSats. And we're also working very closely with our HUMD colleagues on how the human exploration side enables science. And in fact, Jake and I will be giving a joint talk on that later. So such as Gateway and then the human landing system. Ultimately leading to the science planning for the Artemis missions. Next slide, please. So probably the highest profile thing that we do in the office is the Commercial Lunar Payload Services, or CLPS program. And this, as it says, this is utilizing commercial end-to-end delivery to enable access to the lunar surface. We currently have 14 companies shown in the image on the right on the CLPS catalog. And we do task order, the way we solicit to get our payloads to the lunar surface is we issue a task order twice a year, and any of those 14 companies can propose, and then they are reviewed and when we pick one. The task order typically lists what NASA wants delivered, as well as any other constraints. So if we have very specific landing site requirements to do the science that we want to do, as well as the specific needs for all the instruments on our manifest. So the first 4 lunar surface delivery task orders have been awarded, and I think, the first 2 deliveries are this time, whoever's giving this talk this time next year, it'll be a very exciting time for the office, because we'll be very close to the first 2 deliveries by Astrobotic and Intuitive Machines. Within the last few months, we also selected Marston to be a CLPS delivery in 2022, and that will go to a lunar pole. And then very recently, Astrobotic was selected to deliver NASA's Viper rover to the moon's South Pole region in 2023. Next slide, please. So some of you have seen this before, but this is the manifest for the first 2 deliveries that go next year. The reason for showing this is really the color key to show that the payloads that we're taking, whilst this is a significant driver, we're also keen to fly other payloads, both technology demonstration payloads, as well as payloads that acquire data that are of use to human exploration, and that's represented here. And most of these payloads were acquired through the NPLP solicitation. Next slide. And so these are the manifests for the next two small Eclipse deliveries. I mentioned that Marston has already been selected to go to the South Pole. We're very particularly excited by this payload suite, predominantly made up from proposals to the LSIP-P solicitation. We think this is a good payload, a good manifest for the first US landing at a pole. We will soon be putting out a task order for a non-polar delivery with the 7 instruments shown, and working with the PIs. We've decided there's a couple of potential locations in Crisium for where we want that lander to go. And then our plan going forward is, as I said at the beginning, is to have two task orders a year. Next slide. So how are we going to get payloads for the future deliveries? We have, as I showed, the payloads we've allocated so far predominantly came from NPLP and LSIP-P. The solicitation that is going to go out this summer is called PRISM, for Payloads and Research Investigation of the Surface of the Moon. And this is how SMD will acquire its payload for the manifest for task orders that occur in 2021 onwards. As I'm sure many of you are aware, we did a 2-stage process. We did a stage 1, essentially an RFI, and that was to help us at headquarters understand what is the interest in the science and technology communities for what they want flown, so that we can make sure that when we do a stage 2 solicitation, which is where we actually solicit for payloads, what we ask for, we know there's an interest in the community to provide those kinds of payloads. So when we do a stage 2 solicitation, we will most likely state the location for that delivery, which allows PIs to propose science optimized for that location. At the same time, we're sensitive to, we understand the moon scientifically, and there are lots of high value science payloads that are also location agnostic. So we are juggling that aspect as well. International contributions are welcome as part, just like on at a larger scale in the discovery proposal, and up to 30% of the cost of a PRISM proposal could be an international contribution. And after PRISM call, as we build these manifests, payloads from international partners, as well as from other mission directorates, STMD and HERMD, will then be incorporated into the task order. Next slide. So we're actively working on the lunar mobility strategy. Initially, we are focused on the value, both the science and exploration value of the poles, and doing the ground truth of volatiles. We want a strategy which allows mobility that can last for longer and longer periods of time. But we're also very aware that even non-polar Eclipse deliveries, you can have an enhanced science return by having mobility. And we're looking at different options for how to acquire that mobility so that you can put your payloads on a mobile platform if that's the right thing to do scientifically, and just on the static lander. And my final slide, even though Viper is a rover that started off in SEO and now it's in implementation stage, it's being run by the Planetary Division. But I mention this because this is being delivered by, as mentioned, Astrobotic in late 23. And we're obviously very excited by this mission. It'll be a very capable rover. It'll follow up, obviously, the Marston polar delivery to get us even more information on where the volatiles are. And with that, I will stop and go to the next talk.
Great, thank you. Thank you so much, Ben. And I forgot to mention at the beginning that the format of this is going to be that each presenter will talk, and then we will take questions in a panel group format at the end. So Ariel, go ahead.
Great, thanks. So our next speaker is Jake Bleacher. He's the Chief Exploration Scientist at the Human Exploration and Operations Mission Directorate. So Jake's going to be giving us an update on HEOMD.
Jake, we can't hear you.
All right. Can I get a sound check now? Can you hear me?
Yes.
Great. Okay. Okay. Thanks for the introduction. As Ariel mentioned, I am at NASA headquarters working for Human Exploration Operations Mission Directorate as the Chief Exploration Scientist, which was a position that Ben held before me. And that has been a great opportunity for us to work closely together between SMD and HEOMD, along with a number of other colleagues. And so what we have here today at this point is a few slides that are going to be presented jointly by Ben, Sarah, and myself to go over what we've developed over the last several months, an Artemis science plan, and also some updates additional to what Ben has already given. And I think the first few slides here are going to be presented by Ben, and then he'll hand off to me, and then Sarah will close us out. So Ben, if you're still online, go ahead.
Apologies, I didn't realize I was good. I'm sure if people realized that you're going to get back-to-back Ben talks, you would have slept in. So anyway, so yes, as Jake talked about, we have been starting to think about what is the science we want to try and achieve from once we get humans back on the lunar surface. And as you know, don't really have to tell this audience, but you know, the moon enables scientific exploration, really is a cornerstone for solar system science and exoplanet studies, a natural laboratory to study planetary processes and evolution. It's also an important training ground to learn how to conduct scientific exploration from a planetary surface, working together with crew and robotic explorers. And also it's an opportunity to use the infrastructure and resources associated with having crews on the surface to leverage that to do scientific investigations. Next slide. Thank you. So, you know, we're not reinventing the wheel here. A lot of people have thought about this for a long time. And we started off, there are a plethora of documents, both US and international documents that have considered this. And as you read through all of these, we found that you could really summarize the science that you want to achieve under these 6 themes. You know, study of planetary processes, understanding volatile cycles, the impact history of the Earth-Moon system, record of the ancient sun, fundamental lunar science, and a platform to study the universe. And so we've been looking at this with a view to understand what do the crew need to be able to do and what type of science do we actually want to conduct, so that we can ask our HEO colleagues for what we need to get that science done. Next slide. And so this does feed into sort of the 4 exploration objectives that Jake will talk about in more detail. You know, field geology with mobility, collection, return, and new sample, you know, access to the cold regions, and the ability to have delivered and install instrumentation on the surface. Next slide. So I'll just go through these 6 very quickly. You know, the idea here, when we say study of planetary processes, the moon really is a mini planet and has undergone large-scale, you know, differentiation, impacts, volcanism. By studying the moon, we can get a better understanding on how the terrestrial planets formed and evolved. Next slide. So, you know, it's now generally accepted that the moon has several, you know, there are several different types and sources for volatiles on the lunar surface, both volatiles that might have been delivered, as well as volatiles essentially made on the moon, as well as volatiles that date back to the origin of the moon. And we really want to understand all 3 of those water cycles to get a better understanding of both the science and exploration part of this. Next slide. Obviously, the moon and Earth sit at roughly the same distance from the sun, and we want to understand the impact history of the Earth-Moon system. Can't do that on the Earth with the craters being erased, whereas the moon really does retain what is the impact record of the Earth-Moon history. And this is important because we know that impacts have had a major effect on Earth throughout geologic time, including particularly once life was on Earth. And this is something that you can only study on the moon and you can't study on Earth. Next slide. So the lunar surface has been bathed in solar wind for the last 4.5 billion years. And the dust grains retain this information. And so buried regolith, as well as regolith trapped between lava flows, could contain historical record of the fluxes of the early sun. And so by having a crew on the surface, very careful detailed excavation and study can retrieve this record. Next slide. Sorry, screensaver just kicked in, so I can't see the slides. There we go. Platform to study the universe. So the lack of an atmosphere allows the full electromagnetic spectrum to be visible from the lunar surface. And indeed, the far side of the moon is unique in the solar system, we believe, to be permanently shielded from Earth radio noise, allowing much more sensitive measurements to be made that look back further in time. And also, potentially, astronomical observations might be an example of opportunistic science that you could do to leverage the infrastructure there because of crew. Next slide. And the last one is what we called here. One's always a bit hard to pick a title for, but calling it fundamental lunar science. And this is essentially science that you can do because you're on a fractional gravity body with deep space radiation. And so there's a lot of life sciences, combined effects of those two things, as well as exploration physics, such as combustion science, fluid dynamics, dust and material science. There's fundamental physics. You can do general relativity, gravitational physics, quantum information science, as well as food drug degradation. As we go further into the solar system with people, we want to understand how the nutritional value and the drug usefulness works when exposed into deep space for long periods of time. And these are all examples of things that we categorize as fundamental lunar science. Next slide. And now I'll hand over to Jake, who'll cover the next portion.
Great, thanks, Ben. And so working together with SMD, as Ben mentioned, we weren't trying to reinvent any wheels. We're trying to pull from the wealth of documentation that many of you online have participated in providing over the last decade plus. And so as SMD pulled that material together, we also looked back across HEOMD, as there's also research that we're interested in conducting. And I think we can characterize human research for risk reduction in the mind frame of trying to establish sustainable human exploration in the solar system. And so with respect to this, we have activities already ongoing here at the Earth, simulated habitats and operations on the surface, as well as taking advantage of the platforms we have in low Earth orbit. So this is really kind of the starting point for where we can start to characterize the risk that we're going to be facing as we explore the solar system, the moon, and later on to other destinations. At the moon, we now have a location away from the Earth where we can start to characterize some of these risks. And this will be an integrated approach using orbital assets at the moon as well as our surface assets as we begin exploring the lunar surface. This will really be an important step to characterize and understand how to mitigate that risk for human crews that will be exploring the moon for longer durations, being in orbit and low gravity. And this is an opportunity to characterize those risks so that we can plan for moving on into other destinations. So I think one way to characterize all this is down in the lower right-hand corner of this slide, we want to characterize the risks. We kind of have 5 groups that we put that into: understanding isolation and confinement, being distant from the Earth for our human crews, experiencing changes in gravity, experiencing the radiation environment, and working in hostile closed environments. So the surface assets that we'll have at the moon, including the gateway and orbit, give us an opportunity to begin to characterize these risks and develop a mitigation plan. The goal is to be able to continue sustained exploration of the moon as we also think about other targets. And so this is a critical step moving forward for us. Next slide, please. So by merging the SMD goals and the HEOMD research goals, we put together this strategy for Artemis Science. And I apologize, I have some folks working in my house suddenly today, so if you hear that or dogs barking, Greg did mention that we're not quite sure how all these things work out in this socially distant virtual world we're in now. So I apologize. My dogs do mean well, they're just trying to keep me safe, but they are very loud, so apologize for that. So by thinking about the breadth of the SMD research goals, the HEOMD research goals to characterize and mitigate risk to our human crews, we can start to think about advancing beyond the Apollo paradigm. And so Ben had a slide earlier that characterized kind of these 4 exploration goals. So again, understanding the full breadth and integration of the research that we want to conduct at the moon is the basis for ensuring that we develop requirements on the HEO systems that enable us to meet those goals. So working through everything that Ben presented, one of the most important things we want to think about on the surface is how do we conduct science kind of in the field on the surface of the moon. It's really important that we provide mobility as well as time to access different units, different materials, different locations so that we can do the jobs that meet the goals that were presented by Ben earlier. Making sure that we can collect new samples that are not currently represented in the Apollo sample suite. This is another critical aspect to exploring the moon. Making sure that we can put into place the types of surface instrumentation, making sure that on the SMD side, we're identifying the right instruments and getting them built, and then working together, making sure we can put them in place so that they can make those measurements. We are well aware from our interactions with SMD that we're going to need to access cold regions and access colder temperatures than maybe were experienced during Apollo. So that includes just understanding that environment, collecting the critical data to help us understand what that environment is, and then being able to apply the correct requirements on the systems that we develop as we explore the moon. Next slide, please. And so this next slide talks about this bold new era of human discovery. And so we try to link up those objectives there with some of the capabilities that may need to come out on the human exploration side. So the opportunity to study broadly planetary processes as applicable to understanding the solar system. Again, recognizing that this is going to require mobility and time to access diverse terrains and unique locations that we haven't yet explored. Understanding the volatile cycles at the moon, we know again requires us to be able to access persistently shadowed and cold terrains. That may be either robotically or with crew. That first step to that is understanding what the environment is that we have to deal with. And it may be that we can access that by developing additional containers or sample curation techniques that enable us to get in there and get out rapidly, again, either with crew or robotics. So it's critical that we understand not just what the environment is, but what do we need to do with the samples once we've collected them, and how do we need to curate them to make sure that we can do the science we want to do back here on Earth. Understanding that history of the Earth-Moon system, this is a good example of how that levies requirements on the types of tools that we're building. As we know from our Apollo experience, we want to collect small walnut-sized rocks, potentially with rake devices, that can then be dated to give us chronological analyses to understand that impact history on the Earth-Moon system. Again, how do we build our tools? Understanding that record of the ancient sun that Ben mentioned, we need to design our tools to make sure that we can collect those regolith layers and don't disturb them such that we lose the data that we're there to identify and collect. A stable platform for studying the universe. We need, again, to be able to deploy the types of instruments that we want to have. We need to access the locations that we need to be at to make those measurements. We can look at the radio silent areas of the moon as another resource. If this is one limited location that we have access to that radio silence, not only do we need to be able to access it properly and deploy the types of instruments, but we also need to be able to preserve it. It's very similar to understanding the volatile cycles and the volatiles and ices that we're accessing. We want to look at those both as a science target as well as a potential resource, and how does that juxtaposition of those two objectives meet? Experimental science enabled by the lunar environment, extending our human operations in that fractional gravity environment, making sure that we have the down mass to include those experiments along with the instruments that we want to take. So this is why we really needed to pull all that information together, because this really drives out the capabilities and ultimately the requirements that we need to place on the systems we're developing on the human side to make sure we can meet the goals that are being provided to us from the Human Research Program as well as the Science Mission Directorate. Next slide, please. And so with that in mind, we had a slide there that just put all of the rest of those points in place. But anyway, those are the objectives. We just walked through them with you. And that is the point where I'm going to hand off to Sarah now. Yeah, it looks like maybe I lost that slide. That's apologies on my side. So I'll hand off to Sarah now, and she will carry us through the rest of this presentation. Thanks, Sarah.
And Sarah, I'd like to do a very quick introduction since you didn't get introduced. And so Sarah Noble, Dr. Sarah Noble is the lead lunar scientist for SMD. She has had an accomplished research career in lunar science with her PhD from Brown, and after that, she is our program scientist at CERVI, amongst many other duties within SMD. And for those who might not be aware, she's also quite an accomplished artist and puts out a painting at every full moon, which I always enjoy seeing. So Sarah, please go ahead.
Can you hear me? Can you hear me?
Yes.
Good, excellent. Let's see, so thank you. Thank you, Jake and Ben, for covering a lot of that. And I hope you all got the idea that it is, in fact, really a great time to be a lunar scientist right now. Even before we get to Artemis, like, think about all of the things we have going on for our community at the moon right now, right? From orbit with LRO and Themis Artemis up there still going strong, with our CubeSats coming up, Trailblazer, not to mention the others. You know, I think that the moon is a great place for us to like work on small sats and CubeSats, and we are just starting to test those things out. We're getting back to the surface. It's been a long time since we've been to the surface, but we have things on the books now to get us back to the surface. Ben talked about CLPS, about the 3 landers that we already have on contract, and there's more to come. And you can see that, you know, as we evolve this program, as we learn about CLPS and CLPS learns about us, that this is an evolving program that is getting better and stronger, and we are driving towards, you know, bigger science. You know, we talked about the difference between, you know, the NPLP and the LSITP calls as to compared to what we're going to be doing with PRISM, which is a lot more science driven. It's actual suites of instruments going to specific places to do big science. And so I'm very excited about the direction that's going. It's only going to get better. And again, it's 2 opportunities a year to land things on the surface of the moon. I think we really have to understand what that means in terms of the science that we can do. Viper, we're going to hear a lot more about Viper this afternoon. I won't steal their thunder, but that is fantastic. We're again getting back down to the surface and doing real science. It's a great example of like LRO was, where we are science and exploration needs combine, and we are being able to serve both communities at the same time. So that's a fantastic thing. And don't forget about ANCSA. You know, in the lab, we're opening new samples for the first time in decades. And that's really exciting too. I know they've been slowed down a little bit by COVID, but haven't we all? But that is coming too. And in some ways, that's like a whole new Apollo mission for us. And it's teaching us also about the ways to do this as we move forward, and how do we curate those samples, and how do we do preliminary exam and things like that. And so I think we are really building using ANCSA towards what we're going to do with Artemis. Next slide. And I know you guys all want to be part of all of this excitement. And so just a couple of reminders about things that we have in the near term coming up. We will be putting out a call for Viper COIs. Rather than waiting till, you know, just before launch and doing a sort of traditional PSP, we're planning to put that call out soon. I won't give you a date on that because it mostly depends on when I can get it written, but soon-ish. We will be putting out a call to add additional Viper COIs to that team to get people thinking about that science and what we can do with the data that's coming back from Viper. PRISM, I know you are all very anxiously awaiting the PRISM call. We are working on that. Hopefully we will have some more information coming out soon, like within days soon, not months. So we can hopefully scratch that itch. And I knew I was going to get this question later, so I thought I would address it here. CerviCan4, we are thinking about it. We are starting to think and plan towards it, but there is no timeline yet for it, and there won't be for a while. So you can keep asking, but I don't have any more information for you on that. And then the one thing that I didn't put on here, and I should have, is because again, we do want participation from the community, and we are doing, again, later this month, another installment of the Lunar Surface Science Workshop sessions that were, you know, the meeting that was canceled in April. We had a kickoff meeting in June and did our first session on tools and instruments. The end of this month, we are planning to do sessions on volatiles and sample science. There'll be a save the date coming out hopefully today, I think, on that, so you guys can get more information. And our intention is to continue doing these sort of once a month or every other month as we get them together as individual sessions to allow everybody opportunities to participate as much as you can and give us the information that we need to maximize the science that Artemis is going to be able to do. And I think that's my last slide. I think the next slide is actually Jake's.
Well, there we go. Thank you, Sarah. There are, again, we just want to close out with the Artemis science objectives. So as we talked about, you've heard from Ben and Sarah and myself, a number of exciting things going on that are trying to address these objectives, collecting data to help us understand how to meet some of these goals and how to prepare and build our human exploration systems so that we're enabled to meet those goals. But we just wanted to bring those together here for you. We presented these also at the Lunar Surface Science Workshop kickoff meeting a month or so ago. So again, these are, as Ben said, I don't think this is anything that's shocking to anybody on the line today. We pulled most of this information together by looking at the documents that you all contributed to. But we're trying to pull it all together so that between HEOMD and SMD, we have an integrated, clear understanding of where we're heading and what the community wants to see done. And as we move forward, you know, each one of these bullets will become ever increasingly more detailed as we work down to what does that actually mean to do that job on the lunar surface. And as Sarah mentioned, we'll continue to work on these virtual workshops to kind of hash that out for us and help us figure that out. So I think with that, our initial talks from the three of us are done now. Thank you.
Great. Thanks to all three of you. One thing that I was going to note at the beginning and neglected to note is that one thing that I'm seeing at headquarters, I spent a few years there myself, is a degree of cross-directorate collaboration that I have not seen in my 35-year career with NASA. And it's congratulations to the people that you just heard speak for all of that. Going forward to the moon is a job for all of us. So I'm so glad to see that, and thanks to all of you for a great presentation. So I'll let Ariel take over.
So next speaking to us is Dr. Rachel Klima, and Rachel's a research scientist at the Applied Physics Lab and is the lead for the Lunar Surface Innovation Consortium, LSIC. So that's based at APL, and Rachel's going to give us an update on what they've been up to.
Okay. Do I need video on or no?
If you want, we're encouraging it.
Okay. It seems like the host is not allowing it, which is not usually a bad idea, but I did put on my M-Cube shirt just for this and my moon necklace, so.
Rachel, you should be able to turn on your camera now.
Oh, that's weird. No, it's still not going. That's fine. Doesn't matter. All right. I will try to share my screen first here. Are you seeing the presentation in the proper mode?
Yes, we are.
Okay, excellent. So I'm going to talk briefly about the Lunar Surface Innovation Consortium, which is a group that it's a new initiative coming out of the Lunar Surface Innovation Initiative, which is an initiative through the Science Technology Mission Directorate. And so its genesis is from the technology side, but it kind of underlies a lot of what's going on throughout NASA, and the hope is that this will provide a very direct, let me just move to this because I've got the words on the screen, a direct communication pathway between the community, the lunar community being industry, academia, other government institutions, and nonprofits with NASA, so that they can flow some of the technology developments that are being made in the various focus areas of the LSI community, and then receive feedback from the community about what's missing, how these technologies can be used for one of the things that Clive asked in the chat, for building towards a sustainable presence that doesn't just center on what NASA is doing, but actually pulls in the different stakeholders over time. So, how can we leverage all the work that NASA is doing as an entire planetary society? Sorry, I didn't mean planetary society like the planetary society, but as the entire world moves towards trying to establish this sustained presence on the moon. So how do we understand what's going on and build that into our programs that go beyond just NASA? So the goals of the LSIC are to try to harness the creativity beyond NASA and get this dialogue going. I apologize, these edited slides don't have nonprofit in the list for number one, but we are explicitly working to see how some of the opportunities that maybe weren't open to nonprofits can become open to nonprofits in the future. To look at the surface technology developments that are key to getting some sponsor support from NASA, especially STMD, in order to build this kind of future on the moon and onto Mars. And then to also, I know we've got Survey, we've got LPI, we have League, we have kind of centralized space and exploration related websites, but we're going to try to provide a portal that links to all of those resources and also pulls in some of this technical information and the technology relevant data that the community can then access in a central location. So we have an actual LSIC group that has been forming, and I'll have a page later in this talk where you can access the website and sign up if you're not already a member. But as a whole, some of the things we're trying to achieve are identifying some of these key technology needs that might might be a little bit beyond what's already being worked on by NASA, what maybe build on those. We would like to kind of serve the entire lunar community without bias and make this as publicly available as possible. We'll be hosting meetings. We have 2 semi-annual meetings in the year, and then we've got these ongoing focus group meetings that are going to be monthly to discuss the key areas. So I won't dwell on this too long, since I know you're going to want to have time for questions. And I have on here build community. We recognize that there is an extremely vibrant science and exploration community for the moon already, but we want to reach out to folks that maybe are not as heavily involved and have different viewpoints. So looking out to academic institutions that have not historically been as involved with lunar exploration, and to bring in fresh ideas, also to reach out to other government agencies, other groups that terrestrial companies that could branch into lunar work, but maybe don't see the value proposition in that yet, and to really engage with all of these stakeholders to try to make this sustainable in the long run. So we have focus groups that center on the capability areas that are called out by the Lunar Surface Innovation Initiative. That's ISRU, dust mitigation, extreme access, surface power, extreme environments, and excavation construction. And these are the groups where we'll have the ongoing monthly telecons, and where a lot of the technical, we'll kind of group things into these technical areas. But we're also going to have a lot of dialogue between them, because clearly there are important cross-cutting topics that go between, for instance, ISRU and excavation and construction. So this is not meant to stovepipe the technologies, but rather to kind of give a forum that focuses on those. And then we have a lot of crossover in our membership between the different groups, and we'll make sure that the facilitators are all kind of communicating. So I had authorized by STMD, I wanted to show you, since I'm not from NASA and I can't give out money, I wanted to at least provide an idea of what kind of investments STMD is making into this, because that is another key role of LSIC, is to help inform the community about some of the investments that and opportunities for proposals that are out there as far as tech development. And one of the big ones that we unveiled at the meeting in February was this Luster opportunity, which is still coming later this summer. And just a couple of days ago, they introduced the Power Challenge, which is the Watts on the Moon Challenge, which is talking about storage of power. So it's not power generation, but it's like there's several facets to storing power, providing power. And I encourage you to take a look. The RFI is open now for comments. And I have the link on the final page, but it's a very gnarly link with a lot of funny characters. So we will also link that from the LSIC webpage so that you can just click to get there. So before I run any further over, the website for LSIC is lsic.jhuapl.edu. If you're not involved in our email lists and want to join, we've got meetings coming up this month, and then a meeting probably in the very first week of September. And then here is the Watts on the Moon link, which I guess you can screenshot it. It's not as bad as having to do this at an actual meeting. So I will leave it there, and then hopefully we still have time for questions.
Great. All right. Well, thanks so much, Rachel. We're super excited about LSIC as it moves forward. A lot of progress since the kickoff meeting in just this last February. So we have one more talk in this session, and hopefully just a few minutes for questions before Mr. Bridenstine gets on. And that talk's going to be given by Andy Petro, who is now in HEOMD and was formerly in space technology. He is the lead for SpaceCom and navigation for the architecture of that and development of that for the moon. So Andy, please go ahead.
Yeah, thank you. Let me just check that you can hear me.
Yes, we can, and feel free to turn your camera on as well.
Okay, thanks. So I'm going to, I think there's a couple of parts they can bring those up to. So I'm going to talk about the communications and navigation service at the moon. And I mean, as everyone knows, there's also communications and tracking network that already exists to support lunar activities. It has, as it has in the past, that is being enhanced and upgraded to support this new era in lunar exploration. But above and beyond that, we're beginning to implement an integrated architecture that will go beyond that, including things like relays, crosslinks, and kinds of navigation services for our lunar activities. And those are to support the science exploration and the technology development missions. We're working on a regular basis across all the organizations, all of the elements and activities. As Greg had mentioned, there's a great interaction among the different mission directors and organizations at NASA. I talked to people like Ben, Sarah, people on this panel, and many others on a regular basis on this subject. So we're working together on that. The idea is what we're calling a LunaNet concept that would include not just the typical data transmission services, uplink, downlink types of things, but position, navigation, and timing service and information services, things that might provide space weather alerts to various missions, collision avoidance kind of information, predictions of impacts on the surface, the types of things that could be shared and would be valuable across all of the various missions operating on and around the moon. One of the early driving requirements for this system will be early far side missions and also the missions in the polar regions. Operating near the poles means that the Earth is very low on the horizon for direct communication. So it's very likely to be interruptions in that, and some interesting places that people will want to explore may also be somewhat difficult to reach in a direct Earth communication. So we think that working relays that can provide coverage overhead would be extremely valuable for that, for the science missions and well as the human missions to come. Our goal is interoperability across what we expect to be multiple providers of these services and all of the multiple users. And we expect those service providers to include commercial vendors and international partners. And in fact, a lot of this will not necessarily be government built and government operated, but working with a collection of providers. So interoperability is very important, and we see that's a key role for NASA to help in that coordination. And with the overall goal that individual missions shouldn't need their own communications and navigation infrastructure. That's something that should be there so that people can build their missions around those capabilities rather than having to include the cost of that in their own projects. And overall, we want to begin small and keep it affordable. There's many things that are beyond our control in big programs like this, but one thing we can do in order to have control over what happens is to keep things small and keep them affordable. And that's the approach we want to take. We intend to do this in through a series of generational increments. So I don't see the charts. The second chart it had was going to talk a little bit about the relays and just the importance of having relays. Obviously, relay satellites orbiting the moon. Obviously, it's essential for any far side landers, rover instrument packages that don't have a direct Earth view. but it's also very valuable for any kind of polar operations wherever the direct Earth view is blocked. And another important thing is that having a relay nearby reduces the link length, between that user and their comm service, so they don't have to have system size to go all the way back to Earth. So that means they can have smaller and lower power systems, for example, on rover or other package, and that should be very enabling for a lot of missions. Flip to the next chart if you'd like. It's what I'm discussing right now about the relays. Also, if we want to have globally distributed instrument networks, again, this is relays could be very valuable. Each of those stations that have a smaller comm system and send their data back to Earth. And we can provide local links between multiple users and avoid having to go from there back to Earth and then back to the moon again, which reduces the time delays, and it reduces the demand on the Earth's receivers, which are going to be heavily taxed with all of this information coming back from the moon. And again, we can aggregate data, and provide cross-link capability, and better manage the demand on those Earth stations. And we also expect that the relays can host navigation pins and disseminate the information I was talking about, the position, navigation, timing, situational awareness. And overall, it can provide a more robust and flexible operations for all of the missions on the moon, and just overall provide a more flexible and capable service for everyone. And we know there's broad interest in developing and implementing lunar comm relay services among industry and among international partners, and certainly within NASA. And as I said before, we anticipate that much of this will be provided through commercial vendors around the world. And we see NASA playing mainly a coordination role in helping it all come together into a very smoothly operating, interoperable system. So that's all I had to share with you this morning, and appreciate the opportunity to bring up what I think is a very important subject for anybody that wants to be operating out at the moon. So thank you.
Great. Well, thank you so much, Andy. And what I hope the message is that everyone has received, and I think that this last talk really brings it together, is that we're going back, and we're going back to stay. You're going to be hearing more about that in the next 3 days. But I'm encouraged personally to a level that I haven't been in my career. I think that NASA and all of its partners are doing the right things here, and boy, it just couldn't be more exciting. So we would like to. I know that the administrator is ready to come on, but I would like to take the opportunity to take a few questions, and let's see. Ariel actually has to leave at 9 o'clock Pacific. So would you like to do the first one, Ariel?
Sure. I actually had a quick question for Ben. I know you mentioned a couple of the exciting missions coming up, and I was wondering if you could quickly talk about some of the synergies between the Masten Polar Rover and the Viper rover, or differences, and how that kind of feed forward into Artemis as a whole.
Yes, certainly. So if you look at the manifest for the Masten delivery, you'll see a lot of overlap with the Viper rover, where you are flying some duplicates. And if not exact duplicates, then at least acquiring a similar data set. So the idea is that the Masten lander will go to a stationary point. It still has sampler that can access below the surface. So we should get our first key data. We've been a lot of pent up demand for proving whose model is right and wrong. And so Masten will start that process. And then I think that will help feed into potentially the Viper ConOps from what we learned from Marston, because it is acquiring, its payload suite is very similar to the Viper rover suite.
Thank you.
Thank you. Okay, let's see. I can read one from the chat. This is from Barbara Cohen. Can Sarah describe what the scope of the Viper COI call will be? Will it be to propose one's own science investigation, similar to traditional PS proposals? What will the criteria be?
Yeah, well, we're still writing it, so details still TBD. But yes, the idea is that it will be similar to a traditional PSP program where you would propose your own science, but you will also be integrated into the team and participating in team meetings and discussions.
Thank you.
We also have a question for Rachel. This question's from Angela DePremont, which is the technology focus and the origin of the consortium was mentioned, but we're curious if there's any interest in incorporating space policy related goals that could serve to inform the technology decisions and the goals.
I was just typing a response in case we didn't get to this one. So yes, I think we have to maintain sort of the technology focus side for the focus areas, but I'm very interested in pulling in the work that some are starting to do, like with Open Lunar, as far as discussing some of the policy and kind of like how, if we're going to have a sustained presence on the moon, what are the societal impacts and the kind of policy and even like, I don't want to say morality, but I am saying it apparently, but like kind of the bigger, more human implications of that. So I'm kind of in the middle of working out how to include that somehow. So I guess the answer is yes, but it's like, it won't be, if you're interested, email me because I'm trying to kind of have these discussions about how's the best way to fold this into our discussions, especially when we have the entire group meet. The highly focused monthly meetings are going to be mostly surrounding the technologies and whatnot. But when we're talking about the larger effort, I think this is something we want to give a voice to in our LSIG-wide events. Great.
All right. Thank you, Rachel. So this is a question from Clive Neal. Question for the NASA panel: how is NASA HEOMD and SMD planning for sustained and sustainable human presence on the moon, as indicated recently in the Artemis rollout? Science alone won't be enough, I fear. Anyone want to take that?
I can take a quick stab at that. I think that dovetails very nicely with the prior question that that Rachel was answering. You know, we do have to consider the breadth of objectives for the lunar surface and exploration of the moon. And you know, an example that I kind of point to often is looking at volatiles and ices on the surface. They can be considered as a resource target. They can also be considered as a science target. And so we have to start learning, how do we have these different goals meet with each other. And you know, we have talked from the very beginning, the Space Council has mentioned the reason we're going to the South Pole is because we can take advantage of the resources there. That includes not only the water, but also the light. So we have to think about, from a planning perspective, you know, things like if you put up a big solar array, it's not like something that, like ice, where you're digging down to get to the resource. A solar array basically blocks the light for the terrain behind it from the perspective of the sun. So there's a lot that we have to balance there. And I think that trying to meet the objectives that are presented to us will require this kind of collaboration, as Rachel was talking about. So that's why we're trying to get these integrated strategies pulled together that include SMD goals, that include STMD goals, that include HEOMD goals, because the decisions that are being made with respect to how we build these things are going to impact everybody that has an objective at the lunar surface. So very much agree, Clive, and I hear your point. Science alone probably doesn't cut it here, but there are significant technology goals. So from a utilization perspective, that's what we're trying to get a handle on, is what are the breadth of those objectives, so that we can make sure we're designing an architecture that enables us to address all of them.
Great. Well, thank you so much, Jake. And it is 9 o'clock right now, so I want to thank our distinguished panelists, Ben Bussey, Jake Bleacher, Sarah Noble, Rachel Klima, and Andy Petro for their perspectives. I hope this has gotten you, all of you, as excited as I am about our return to the moon. What a great time this is. As Sarah put it so well, it's a great time to be a lunar scientist. I couldn't agree more. So thanks to all of you. Thanks also to my co-chair, Dr. Ariel Deutsch, and now we have the great privilege to proceed ahead with the next element in our program, which is going to be a talk by our NASA Administrator, James Bridenstine. So in manner of introduction, Jim Bridenstine's career in federal service began in 1998 as a pilot in the U.S. Navy, where he flew combat missions off the USS Abraham Lincoln aircraft carrier. He later moved from the E-2C Hawkeye to the F-18 Hornet and flew at the Naval Strike and Air Warfare Center, the parent command to Top Gun, and which is, of course, for many of us of a certain age, reminiscent of Maverick in the movie Top Gun. After transitioning from active duty to the U.S. Naval Reserve, Bridenstine was elected in 2012 to represent Oklahoma's 1st Congressional District in the U.S. House of Representatives, where he served on the Armed Services Committee and the Science, Space, and Technology Committee. Jim Bridenstine has served as the NASA Administrator since April 23, 2018. Under his leadership, NASA has developed the most powerful rocket ever built and launched its new human lunar exploration mission, the Artemis program, which will land the first woman and next man on the surface of the moon in preparation for future crewed missions to Mars and beyond. As administrator, he's managed commercial resupply of the International Space Station with a commercial crew program that has once again recently launched American astronauts on American rockets from American soil, something not done since the end of the shuttle program in 2011. Additionally, Bridenstine established the Commercial Lunar Payload Services Program that Ben spoke of earlier to partner with private enterprise in landing rovers on the lunar surface. These rovers will contain tools and science experiments in preparation for the arrival of American astronauts. Quite simply put, during his tenure, NASA has thrived. And with that, I am very proud to introduce Administrator James Bridenstine.
Well, thank you. And thank you for that introduction. Greg, can you hear me?
Yes, loud and clear.
Okay. All right, perfect. So I'll just, I'll kind of give a brief summary here, and then we'll open it up to questions. And I know there's a lot of amazing people that are part of this conference that might want to share their thoughts, which of course is always good as well. So I just like to say to start, when I became the NASA administrator, my highest priority was to maintain and even grow the strong bipartisan apolitical support that NASA has had historically. And the reason that's so important is because in order to achieve what we need to achieve, we've got to have increasing budgets. And that means we need Republicans and Democrats alike to be supportive of our programs. And I think for the most part, we have in fact achieved that. Right now, NASA has the highest budget it's ever had in nominal dollars. I would say in real dollars, Apollo was significantly higher, but we're not in an Apollo era right now. And in nominal dollars, we're the highest we've ever been. And in fact, right now, before the House and the Senate, we have a budget request of $25.2 billion, which is over 3 billion larger than our current enacted budget. So, and we're getting, again, broad bipartisan support. So I'll share with you kind of how this is, the reason this is happening and why this group focused on lunar exploration is so important. When I was in the House of Representatives, there was this argument about whether or not we go to the moon or we go to Mars. It's one or the other, but you can't be for both. And that was very divisive. And what ended up happening is Republicans were for the moon and Democrats were for Mars. I have no idea how these kind of things become partisan, but just by the very nature of partisan politics in Washington, D.C., that in fact did happen. We've also seen the split, Republicans are for human exploration and operations and Democrats are for the Science Mission Directorate. Again, these are false narratives that we have to work every day to unwind, to make sure that we're looking at our agency as a whole and how we're going to accomplish things together, unite our political leaders so that we all believe that what we're trying to achieve is important and we can get those important budgets that are necessary to do lunar exploration. One of the things that I think is so impressive about what the team at NASA has accomplished is tying, and Thomas Zurbuchen gets a lot of credit for this, tying the Science Mission Directorate to the moon. It's always been that human exploration was about the moon and the Science Mission Directorate was about everything else. And now we have, for the first time, the CLPS program. That was my first initiative as the NASA administrator, the Commercial Lunar Payload Services Program. I saw a question from Clive Neal a little earlier. He was a big part of inspiring that initiative. So what does that mean? We're going to go to the moon commercially. We need to go fast. We don't want the government to purchase, own, and operate all the hardware. We don't want to create, thousands of requirements. We want to say, here's the payload. Here's the science instrument that we need to get to the surface of the moon. Who can deliver it for us? And so within the Science Mission Directorate, we now have a plan to get to the moon commercially with these small payloads. But what matters here is by doing that, we now have the science community focused on the moon as much as the human exploration community. And what's so important is that the moon is in fact all about science, and it always has been all about science. And when we think about the Science Mission Directorate, we talk about astrophysics. One of the missions that I've been talking a lot about is the DAPPER mission, an orbiter of the moon that can not just see the first light in the universe, but can see back into the dark ages after the Big Bang and before the first light. And you can only see that with specific instruments on the far side of the moon. But earlier I heard of the talk about the communication architecture that we're building at the moon. If we have that communication architecture for what's happening on the surface of the moon, both with humans and with robots, all of a sudden we can do astrophysics around the moon, and astrophysics even from the far side of the moon on the surface of the moon, astrophysics that we could never do otherwise. And we can do it for a fraction of the price because the communication architecture is already there. We don't have to launch, all of the power that's necessary for, the communication capabilities and the large antennas, because we have a robust communication architecture already at the moon. So when we build the architecture for comms, we're doing it for human spaceflight to the surface of the moon and for robotic rovers, all of a sudden, now it opens the aperture to what we can do with astrophysics, which is a big division within the Science Mission Directorate. But it also opens the door for heliophysics. The moon is basically an amazing repository for data and information from the early sun. The idea that the Earth has the very active atmosphere, very active hydrosphere. The charged particles that came from the sun because of the magnetosphere largely went around, and the particles that come into the Earth, they all get moved around. Well, the regolith on the surface of the moon is a repository of data and information of the early solar system because it doesn't have an active geology. It doesn't have an active atmosphere. And I know the audience I'm talking to, and there will be those who will say, well, there is a trace atmosphere on the moon. It's very, 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 I get it. We get it. There's ice and all these great things. But the point is this: by going to the moon with instruments and landers and rovers and humans, we can do astrophysics in a way we've never been able to do astrophysics before. We can do heliophysics in a way we've never been able to do heliophysics. We can do earth science. Remember, there's a big body of work from maybe a lot of people that are on this teleconference right now, a big body of work that would say that the moon was actually at one time a part of the earth. So we can actually learn about our own planet by in fact going to and studying the earth. So, and as far as planetary science goes, look, we're going to Mars. And if you want to learn how to live and work on another world, there is no better place to go than the moon. And why is that? Because it's always a 3-day journey home. And we learned from Apollo 13, things can go terribly wrong on the way to the moon and you can still make it home safely because it's always a 3-day journey home. But if a bill right now for NASA, the Commerce, Justice, Science Appropriations Bill, this is the opening salvo from the House of Representatives, which is controlled by Democrats, and they have $600 million in the bill for a human landing system. I think it's $620 million. Now, that's not everything that we asked for, but what it shows is that there's bipartisan support for this activity, and we can work with the Senate to help get more resources as is necessary to achieve the 2024 landing. But 2024 matters because number one, it drives the budgets that we need to achieve these goals. And number two, the longer the programs go and the more expensive they become, the more likely they are to get canceled. And we've seen that over and over again. We need to put points on the board. And once we get there, we need to grow. We need to grow from there. Driving down costs, increasing access, reusability, all of these things need to be driven into the architecture. So I guess what I'll do now is I'll stop talking and I'll open it up to a few questions here. I think we have 15 more minutes.
Yeah, great. Well, Administrator Bridenstine, first of all, if you over the internet have heard the sound of 400 people collectively cheering, it's because of what you said. The moon is the best place to unite, and boy, we could not agree more. I've also gotten a few private messages from people asking if you can stay as administrator forever. So we'll have another conversation about that perhaps sometime. Thank you so much for your leadership and all of this for our community and for the nation as a whole.
Greg, it's interesting. I actually had a bill when I was in the House of Representatives. I had a bill that would make the NASA administrator a 10-year term, so that we could have constancy of purpose, just like the FBI. The FBI director has a 10-year term. Now that bill never went anywhere, but I made the effort. But I don't know. 10 years seems, now that I'm in the job, 10 years seems like a long time.
Sure. And I just got a comment from one of the next generation folks saying we are the Artemis generation.
That's right.
It's just like I'm part of the Apollo generation. I remember the Apollo 11 landing, like more than a few people on, they're going to have their missions that they remember. And you're bringing that to us. And that's just so exciting. And we're also very proud as CERVI and previously the NASA Lunar Science Institute to have given rise to some of these things, such as DAPPER, through our funding of Jack Burns and his efforts. So we're very proud to be taking a part in this.
Let me give a shout out to Jack Burns, because he wasted no time in making sure he put that on my radar as early as possible. So it worked.
So
Although
anyway, let
we need
me
to get
ask.
more funding. Yeah, go ahead.
Let me ask everyone. We would love it if you would ask the questions in person rather. And so please raise your hand, and we will be able to select you. And I'll mention that my deputy Christina Gibbs is online as well, and will help in selecting questions. Maybe I'll just start with one myself, and that's, what do you see as your biggest challenge right now, perhaps beyond the political sphere that you spoke of?
Yeah, so I think the biggest challenge is we think about the various ways to get to the moon, and then what do we do when we're there? And building consensus around ultimately the decisions that we make. So I'll just give you an example. We are now under contract with 3 separate providers for a human landing system to take us to the surface of the moon by 2024. And the budgets are not going to probably materialize for us to carry all 3 human landing systems, through the end. So the question is, will some of these companies continue to move forward commercially because there's going to be a future market for, whether it's resources or whatever it is on the surface of the moon or even below the surface of the moon? I guess the question is, if we do down select, which I think we probably will have to at some point, maybe sooner rather than later, depending on how these budgets materialize. Does the community then go pan, what the effort is we're trying to achieve? Do you know what I mean? Because they didn't get the contract they wanted, or are they going to go to their congressmen and senators and start making a stink of it? Because those are the kind of things that set us back. So, and we've seen that a little bit already on CLPS, where certain CLPS providers were upset because other CLPS providers. And I'm going to be very honest. They didn't like the outcome of something, and so they went and got their congressman involved. And that can be helpful for them, but it could be very damaging for the long-term, prospects of what we're trying to achieve. And so the contractor on contractor violence sometimes does a lot more damage to the total effort than it does benefit to you as a contractor. So these are the things that we have to think about all the time, and try to make sure that we're maintaining the right balance. Trying to make sure that as we go forward with our acquisition programs, we're doing it with integrity, and not getting distracted by some of those very difficult issues that we have to deal with day in and day out. But I spend a lot of time creating the unity that we need to achieve these goals, and then it's really easy to just wreck shop in a heartbeat. So if there are folks on the line here that are involved in that, I just want you to have the perspective that I have. That's all.
Thank you. We have a question from TJ Cooney, who has raised their hand. TJ, if you could turn your video on and your audio on, take it away.
Mr. Bridenstine, thank you so much for taking my question. So I know 2024 is our goal, which is a short 4 years away. I'm very much looking forward to that day when we get back on the surface of the moon. I know that for the first landing, the goals of it are going to be pretty much about getting to the moon, showing that we can do it, getting, trying to prove out a lot of the science and get out of there, so to speak, not necessarily requiring to be on the surface for a very long time. But one of the advantages of having humans on the surface or working in space really is the amount of science we can do on the fly, be creative in short periods of time. As of right now, for that first mission, is there any particular science that NASA is prioritizing for those astronauts to do outside of demonstrate the capabilities of the landing system and all that, in terms of core samples or just anything. It would be fascinating to hear if there's any kind of science you guys are prioritizing for that first mission.
Yeah, in fact, we started a discussion on that just yesterday, and this is where NASA historically, its mission directorate wanted to have their say in what we're going to do on the surface of the moon when we get there. What does that look like, and how much does it cost? And again, bringing together these historically kind of separate parts of NASA and saying, let's work together to achieve more than we could do either one of them by themselves. And so yes, we're going through those discussions right now. I certainly don't want to, bias the discussions that are happening already. But I can tell you, you're absolutely right. When we go to the moon the first time, we want to make sure that our astronauts get out, they walk, and now we're going home. That is not the goal for the first mission. So we're working through it. I don't want to bias it right now, but there are certainly a lot of very, very inexpensive and easy experiments that you could expect. Experiments that deal with the solar winds, for example, experiments that deal with characterizing the lunar regolith and the water ice that is embedded in there. How do you characterize it? Is there any pure water ice? Is there is it easily accessible? So there's a lot that I think we're going to do on that first mission that is not expensive, but also very important and meaningful. And yes, when you have a human there, you can do a lot more, a lot faster, and it makes things maybe go quicker. Not to prejudge kind of the experiments that we want to do.
The first is from partners, and the second one is from Clive Neal as part of the Apollo Generation National Environment.
The entire we will have crewing so back to that have very robust capabilities that didn't exist in the 1960s, and we have now international partners that are stepping up to the plate with budgets, which is something we didn't have in the 1960s. So I really think that's a big part of the sustainable effort. And yes, we need to, when you look at it, you got to create the architecture. The first thing is, what is it that we're going to design to go to the moon sustainably? And then we say, what nations are going to have responsibilities for which elements? And then we say, within each nation's responsibility, what commercial providers are going to be able to deliver on that capability? Some countries don't have the robust commercial capabilities that we have in this country. And so then once we establish their role, then they're going to have to figure out how they accomplish it, whether it's government or commercial. So bringing all that together is hugely important. But I think, to the point that both those questioners had, having international partners enables sustainability. Having commercial partners enables sustainability. And what NASA needs to do in all of these cases, we need to set high-level objectives. When I say high-level requirements, we look at the success of the Commercial Crew Program, for example. Everybody saw, Doug Hurley and Bob Behnken launch on a Crew Dragon to the International Space Station. That was successful because NASA set the high-level requirements, but we didn't design the vehicle through the requirements process. And because of that, industry can go innovate. And if you look at what space have done these things, we had a rocket with 9 engines. We had a rocket that came home and landed afterwards that we're going to now reuse. These are things that if NASA were to write the requirements in depth itself, it would have resulted in a very different, not have reduced the cost as much. Now, I will tell you, there were a lot of skeptics about this, and I'm knocking on wood as I say this, because Bob and Doug are still on the International Space Station. Their mission is not yet over. And so we're taking it seriously every day. But my point is, we need innovation, and we need new ideas, and international partners, same thing, and reusable command module. That's the way I think of it. It's a reusable command module in orbit around the moon. We don't have to throw away a command module every time we go to the moon. And of course, it's going to have scientific capabilities and communications capabilities. So all of that drives down costs. If we can use it for the next 15 years, we don't have to throw away a command module every time we go to the moon. So those are, I think, important. and of course, the Gateway itself is international. I mean, the European Service Module, the first time we go to the moon in the Orion crew capsule, it will have a European Service Module. We're international on day one. When we launch Artemis 1 late next year, we're international. We've got 11 countries that are involved in the European Service Module. So all of these are going to be of great benefit as we move forward.
Yeah, thank you very much for that. And as you know, Administrator Bridenstine, we at Survey are also international. We have our European Lunar Symposium every year in May that's now led by Christina Gibbs and our European partners, and we have many other activities as well. And we have so benefited by that. And I know it's 1 minute past your time right now. I don't know if you have time for perhaps one more question.
Sure, we can do one more. That's good.
Okay, all right. So this is from Parks Easter, and how do you envision the future of the commercial space industry past the lunar base? Do you see it continuing to expand?
Yeah, so when we think about commercial right now, what we need to do is we need to have commercial industry. First of all, we need them to have customers that are not NASA. If NASA is the only customer, it's beneficial, but it's not as beneficial as it could be otherwise. So what happens on the surface of the moon is really important. Is there a market for the life support capabilities that we get from the water ice? Is there a market for maybe even taking that water ice, cracking it into hydrogen and oxygen, putting it into cryogenic form, and putting it in orbit around the moon? Could there be a market for that? I think obviously the only market right now for that would be NASA, and we really haven't even established that as our goal officially. But I'll tell you where, you know, if there are large deposits of platinum group metals found on the surface of the moon, which I think there is a probability of. I mean, I don't know, neither does anybody else. But if we look at all of the asteroids that are impacting the Earth and we think about the asteroids that are impacting the moon, they're pretty much the same. And of course, the Earth eats them up. And the moon, again, doesn't have an active geology, doesn't have an active atmosphere. And so there could be large deposits of platinum group metals or other precious metals on the moon. And if those get discovered, I think it will fundamentally shift the race. It will have a space race. It won't be geopolitical in nature. It'll be economic in nature. And of course, the United of that material. Even though according to the Outer Space Treaty, which we fully agree with, you cannot appropriate the moon for national sovereignty, it is possible that you could extract the resources and own the rights to those resources. Just like in international waters, you don't own the rights to the waters, but if you extract resources, whether it be tuna or energy, you can have the rights to those resources because you're applying your equity and your effort to achieve that. So if we can create that, if we can take the international regime that we see over international waters and apply it to the surface of the moon as an international regime, the same, I think, and then platinum group metals do get discovered, I think it will change the game as far as the amount of resources going into these activities. And so I think that should be a part of what NASA is looking to discover when we go back to the moon. And if that discovery is made, I think it will change the game. I don't think NASA needs to be extracting resources, although I think about it, that could really help our budget. But that's not my goal. That's not the goal of the U.S. government. That's the job of the commercial companies should they choose to go into that industry. So I think these are important. It's what the Artemis Accords are all about. You're probably familiar with the Artemis Accords, but when all these countries want to be with us on the moon, and all these countries want to go to the moon and have presence there, we need to figure out, number one, if you're not complying with, say, the liability convention, or if you're not complying with the registration convention for activities in space, then you shouldn't be participating with us on the moon. Like, the very basic principles are, you have to adhere to the Outer Space Treaty. You have to adhere to the conventions that have come from the Outer Space Treaty. And then And then we look at the other international Navy pilot that I flew with over the international waters, international airspace. If I get challenged, I say I'm a sovereign U.S. aircraft operating due regard over in international airspace. And it means you stay away from me, I'll stay away from you. We just don't interfere to internationally, if not in writing, then by convention or by establishing norms of behavior. And so that's really what we tried to start with the Artemis Accords, because every country wants to be with us when we go to the moon. Okay, if you're going to be with us, there's very basic norms of behavior, starting with, adhering to the Outer Space Treaty, and then following up with the conventions that come from the Outer Space Treaty, the Liability Convention, the Registration Convention, and the philosophy of operating due regard, which is on a not to interfere basis. And if we can have the countries that want to go to the moon operate under that legal regime, and then a discovery gets made, I think it will fundamentally change. It'll create the certainty necessary for the private sector to capitalize and continue this dawn of a new era in spaceflight.
Wow. That's just fantastic. And I can say on the international that we do have a lot of international participants in this meeting. And I know that they have been happy to hear you say that. We're going to be hearing from one of our survey partners tomorrow. And so that's just a fantastic way to end this. I appreciate you staying a few extra minutes, and I wish we could share some applause. It would be deafening. So we really appreciate this, Administrator Bridenstine, you taking your time, and please know that you have a whole community here at your disposal. We're working closely with NASA headquarters to enable some exciting science and discoveries, and I can't wait.
Awesome.
So,
well, we're very grateful for Survey. You guys have done amazing work for many years, and keep it up. And thank you for hosting this.
Thank you. All right. Thanks for your time. Thanks so much.
Right.
Okay. Bye-bye.
Bye-bye.
Okay. So, wow, that was just fantastic, everyone. And to continue our series of really important talks and shifting gears somewhat, I mentioned earlier about the national attention on race and issues related to that. This is something at Survey that we take very seriously. As I mentioned, we're creating a focus group to take a detailed look into that and give some recommendations to us on how we might move forward in the next year. And so our next speaker is going to be talking about these issues. Her name is Professor Dina Khalil. Her PhD is from Rutgers, and her research is on the challenges of recruiting, developing, and retaining highly effective teachers, particularly STEM teachers who prefer to serve in either urban schools or in education systems with a predominantly marginalized student population. She is a member of Dr. Jennifer Heldman's resource team, and we're very pleased to have her as our next speaker. So Professor Khalil, please take it away. We're not, I'm not hearing anything, so I did see you on.
Can you hear me now?
There you go. Yes, we can hear you.
Well, good morning, everyone. Let's see.
Hope you're well.
Yes. And I'm trying to share my screen. Okay, here
Oh,
we go.
while you do that, let me just remind everyone that we're going to be doing a group photo right after Professor Khalil's talk. So please don't go away for the break right away. So I'm sorry, please go ahead.
No, thank you. I'm trying to share a portion of my screen. Maybe try it with another. Okay. Well, if it doesn't work, we'll do what we always do as educators. We'll wing it.
Feel free to do whatever works for you.
Share. It was working.
Let me just ask our tech help if they can provide any assistance, Ricky or Ashkan. We are now seeing something.
Okay.
Dr. Khalil, this is Christina Gibbs. If you'd like to send me the package, I'd be happy to share it for you so that you could get started, but then I could
That
share
would
the
be great.
screens. Okay, please just go ahead and email
Or
it
I
to
was
me.
going to give you control over my screen as well. That's another thing.
That's beyond my capabilities, but Ricky could help with that. But I can share your package. I'll watch for it.
My apologies.
That's okay.
Shouldn't be this hard. I did this with a lot of students.
Feel free if you'd like to just talk to it if we
Yeah.
can't get it working, and then when Christina gets your package, she can.
Okay. Well, good afternoon, everyone. I apologize. That was, I don't know if the screen looks odd because I have two different screens and I'm trying to help make it work out, but it's not. So we're just going to move along. I'm here to talk about equity-centered design thinking as a way to interrogate racism and promote inclusion in the exploration science community. So to begin, our goals are to explore perspectives on the definition of equity and its relationship to diversity, inclusion, and social justice, and broadening participation in the exploration science community. Consider issues of intersectionality and identity when designing for broader participation, and recommend next steps for recentering formal K-12 education as well as higher education in the exploration science community. So I'll just start off by this really quick design challenge. If you all can, well, this is what I would be doing if we were in get in groups, and I'll ask you to solve this design challenge. So build a bucket drum for raster so it may fill up to a 50% of its ratio. And I would normally ask students to do this with some construction paper, tape, and to do this silently so that we could see if it could hold 6 ounces of water. While you're doing that, if you don't mind, tell me what kind of scientific inquiry you're using in the chat box. Okay, I see that we're getting answers that you're seeing the whole screen. But again, feel free to share what kind of scientific process you're using to solve this. So the scientific process that I have in mind for all of you is the design thinking process. And this is one that I emphasize because we have the role of empathy. And empathy helps us think about how to make connections and questions before we ideate and come up with solutions. And these ideations are normally based on our beliefs. So a show of hands, how many of you use this? So why this process? I do this process with the students because it helps them connect. And I ask them questions about, what do you notice about the challenge? What questions does this challenge raise for you? What questions does it raise in terms of how it relates to community issues? What connections or memories does it help you recall? And some of the answers they give is that, you know, this reminds us of a construction tool. They might ask questions like, why are we searching for resources abroad? Will it help us have resources like water here, and things like that. So we continue, the reason we're using this system, or we're using this process of thinking, is because almost any system produces what it was designed to produce. And so I think about design thinking as a way to start empathy and helping us notice questions around problems to build understanding, while other scientific inquiry does not help us do that necessarily, and it takes a value neutral stance around problems. It also extends our rational characteristics of scientific inquiry to the social construction of science community. So it helps us think about how we can diversify and build equity and inclusion in the scientific community. So this is why I consider design thinking as a really great process for promoting equity, inclusion, and diversity. So how can scientists design STEM spaces for historically underrepresented minoritized individuals? This is a graphic of how you can consider design thinking when you're thinking about how to make your spaces more equitable. How do you make your teams more inclusive or diverse? And I go back to saying that we have to do this iteratively because we are in a system that was designed to produce inequities. We have to go back to thinking about history and centering history and overcoming a historical context of systemic racism. Thomas Jefferson proposed a two-tracked education system to complement the labor force, with different tracks for, in his words, the laboring and learn. He thought that scholarships would allow a select few of the laboring class to advance by raking a few geniuses from the rubbish. If we look at historical trends in the labor force, which is disaggregated only by gender, this was done because slaves were not counted as part of the labor force, and they were they were only counted for 3/5 just for tax purposes. So I say all this is to say that if the system was designed to advantage some over others, then we have to design a system that interrogates and disrupts this. And if we consider schools a microcosm of society, or if we consider the planetary community a microcosm of society, then we know that systemic racism is there. So today's talk will address this problem, and I'll engage you with what, where, why, and most important, how to design solutions to this. So to reiterate the question, it isn't a question of what. We're here to address problems and design solutions for EDI. The question is not where. It should happen in every organization with every scientist and principal investigator who leads a team who's committed to EDI. It's possible to design spaces that are equitable, diverse, and inclusive. All you need to do is look at HBCUs, where although they're 3% of all universities, they produce 85% of Black doctors, 75% of Black PhDs, 80% of Black federal judges, and 33% of Black undergraduate STEM degrees. The question is not why. I'm going to take it for granted that we're all here and that we're all committed to equity, inclusion, and diversity. The question is not how. The research on how to engage underrepresented minoritized students and professionals in STEM is established. There are numerous scholars who research EDI in STEM and have published findings on how to nurture and support UREM into STEM careers. But I will be going through some of that research with you today. So as scientists, we daily, you can influence how to interrogate, disrupt, and dismantle systemic inequities in products, spaces, processes, and systems. So because society, schools, and communities are by design racist, we as designers have the power to shape how underrepresented, minoritized individuals experience the world. And we need to intentionally and iteratively address racism and oppression consistently. So why do I talk about design and equity together? It's because design can always address the root causes of inequity, and we can be deliberative in how it reproduces inequitable power relationships. That's what we could be deliberative in addressing. Equity work often does not have the resources or the critical number of people to address it. So what I'm saying is that if we can all, as scientists, take this methodology to address racism, this is an opportunity to make a big difference. So how can design thinking serve as a force for equity and address the effects of oppression on education or in our spaces? We have to understand that oppression is a system that is built into our daily life beyond our individual acts. It happens at the institutional level, structural level. We may not even notice the types of oppression that happen when we are researching, leading, training, designing, or improving our innovations. But noticing oppression and how it affects people of color, by doing this, we have the opportunity to make sure our design improvement work produces greater equity. So here's a partial map of systemic oppression at the individual, interpersonal, institutional, and structural level. And blindness to this reality of systemic oppression will only reproduce it. So one example I see in the community is the idea of doing community outreach in informal spaces. When we do things in silos, that means we're saying that that's not our problem, that's not our space. And when it comes to doing EDI work and broader impact work, we cannot work in silos because the system all is influenced by various factors that we can see right here. But the good news is here's a partial map of how we can be liberated. We can, at the individual, interpersonal, and institutional structural level, help overcome systemic oppression. And how do we do that? We recognize our blind spots and build our equity lens in our policies, outcomes, whether or not we have power, who has power, in our relationships, and in any solution we design. So we have to really lead from the inside out. We have to acknowledge how power and identity are important. We have to think about how our authentic self allows opportunities or hinders opportunities. And it really is about developing our own social emotional awareness before entering any context, and to practice empathy, which is the first step in design thinking. This phase focuses on you, the designer, in order to build the practice of self-awareness of your own identity, values, emotions, biases, assumptions, and how it situates how you will go about empathizing with humility, curiosity, and courage. It is about noticing what people bring to the table and centering a rehumanized space in the science community. So I spoke about these things that we should be noticing. our identity, our contacts, who we're partnering with, and our intentionality. And the effect of our emotions and how important it is to share. And how important it is to check in, because this work is emotional, is laborious, but it can be done.
Dina, we have just maybe a minute or two left.
Okay.
Yeah, sorry.
So no, it's fine. So I do want to acknowledge when we're working on something like this, when we're addressing and interrogating racism, it is difficult. And I want to acknowledge that that's why racism not only hurts people of color, but it hurts everyone. Because the only way we can move on with our life is by compartmentalizing and not thinking about all the oppressive situations around us. So this is why we are all in this together. And the way to address it is through courage and love and humility and reflection. And we need both methods and mindsets. These are, this is just a list of things we could be doing so that we can build our mindsets and we can do certain actions to build equity and diversity and inclusion. So as you're striving to be an equity-centered designer, what you need to do is recognize and notice what's happening and think about what actions you want to take so that you can have more equitable outcomes. And axioms for equity: individual mindsets matter, individual actions matter, and we can't only focus on the individual interpersonal inequities, we have to also fix structural institutional inequities. And not take a light approach, like sort of like a light Diet Coke. We have to interrogate structural inequities and examine our beliefs. And it starts from the K-12 education system. You can look at what happens in AP math classrooms, but we can interrogate, we can commit ourselves to making a more inclusive space, create opportunities, avoid tokenizing, checking in, avoiding pathologies, and asking tough questions, and creating spaces for social justice. So thinking about all of this, I'm asking you to think about going from a safe space to a very brave space, because the work of equity and social justice and really liberation is ongoing. We can approach the asymptote, but there's always work to be done. Thank you.
Great. Thank you so much, Professor Khalil, for talking about this and for your work on Dr. Heldman's team. I really appreciate that. Let's see. We have. We're going to limit it to just one question, just because we're behind schedule, and that question is from Jay Greer, and they ask, what strategies would you recommend for scientists to identify their own unconscious biases and assumptions regarding equity and diversity?
In that mindset and method chart, I mentioned a few things, but it starts with conducting an equity audit of your team. And it's a process. It cannot be done in one training. So thinking about what are some assumptions you're making? What are some, are you considering that people are making bad choices, or are you understanding that some people are privileged with only good choices? It reminds me of what is it, Little Fires Everywhere? That was a really, that's a good show that we could watch to understand how mindsets are very powerful and how we need to not only work our own mindset, but work on ways to make change. Because without practicing it, mindsets can't change.
Yeah. Yeah, that's great. Well, thank you very much for sharing this. Sorry for the technical problems at the
No, my
at the
apologies.
beginning.
I wasn't expecting it. I had 2 laptops.
I resonate with what you say about doing this with courage, love, humility, and reflection. This is the beginning of a journey for Survey and the community, and I really look forward to checking in and at the next forum to see how we're doing. So thank you so much.
I will also be at a post session later today, and I'll put my email in chat.
Excellent. Okay. All right. Thank you very much.
You're welcome. Thank you.
Okay. So, we're going to be having a very brief break, but before the break, we would like to do the group photo. And so to start that, Ricky is going to run that. And to start that, please keep your cameras on if they're on, or turn them on if they're not. So Ricky, I'll let you take over. Ricky, do you hear me?
Sorry, I have that double mute problem every once in a while. But that gave everybody a time to get their cameras running. What I'm going to do is just basically do a screen grab, and I've got 7 pages of screen grabs, and I don't know which one each of you is going to be on. So as I let you know before each photo, I'll let you know to smile, and I'll grab the screen grab, and then we'll move on to the next one. And so let's go ahead and get that started here. So in 3, 2, 1, smile. Okay, let's go to the next page. And 3, 2, 1, smile. And we're on page 3 of 7. 3, 2, 1, smile. Okay, next one, get ready. 3, 2, 1, smile. Just got a few more to go. 3, 2, 1, smile. Let's see. Again, 3, 2, 1, smile. And 3, 2, 1, smile. Last one. Okay. And we are all done with the group photos. Thank you all.
Great. Thank you, Ricky. And thanks to everyone who participated in the opening session of the NASA Exploration Science Forum. We're going to take a short break, and let me, rather than just 5 minutes, I think that people may need just a bit more than that. So let's take 10 and start at 10:20 Pacific time. So we'll see you then. Thanks. Okay, why don't we go ahead and get started again? Sorry for the very short break. I'd like to introduce the co-chairs of our Exploration Missions session, Plenary Session 2, and they are Kelsey Young and Nandita Kumari. So Kelsey and Nandita, please take it away.
Great, thanks very much, Greg. So we have the distinct pleasure of chairing our second plenary session of this year's Exploration Science Forum entitled Exploration Missions. Sarah Noble mentioned earlier, we have a lot of really exciting missions now. We also have exciting missions elsewhere in the solar system, and we're looking forward to hearing from some of those missions today. My name is Kelsey Young. I'm located at NASA's Goddard Space Flight Center. I'm a geologist who researches science integration into human spaceflight, and now I want to turn it over to my co-chair to introduce herself as well.
Hi, I'm Nandita Kumari. I am a graduate student at Stony Brook University, and I'm really looking forward to this session.
Great, thanks. Okay, so before we get going with the first speaker, as this is kind of the first session with the traditional format, I'll just have a couple announcements on how things are going to work. For the speakers, you have 10 minutes allocated for each of your talks. We'll be giving you a 2-minute warning with the sound of a ding, and then you'll have 2 minutes at the conclusion of your 10-minute talk for questions from the audience. Please plan to share your screen yourself, and please use your video if you're comfortable with it. And we'll be taking questions, as I said, after each talk. So for the audience, don't be shy. Feel free to ask your questions after each presenter finishes. So with that, let's turn it over to the first speaker, who is Kevin Walsh. Kevin is a co-investigator on the OSIRIS-REx mission and is based out of the Southwest Research Institute in Boulder, Colorado. Kevin will be talking about OSIRIS-REx at Bennu, time to collect a sample. Over to you, Kevin.
Thank you very much for the introduction. Am I coming through and sharing well?
Yes, you are. I think you just put full screen, that would. Great, perfect.
Okay, thanks for the introduction. It's an absolute pleasure to get to talk about OSIRIS-REx and the exciting times we've been having at our target asteroid, near-Earth asteroid Bennu. A reminder, OSIRIS-REx is one of NASA's New Frontiers space exploration missions. This is an asteroid sample return mission with a fundamental primary goal of returning a pristine sample from near-Earth asteroid Bennu. The requirement is 60 grams of sample to come back. Along the way, and to facilitate the sampling, we get to do all sorts of really exciting science related to understanding the connections between meteoritics and the astronomy of asteroids for these volatile rich and low albedo targets. We get to understand the geology and evolution of small rubble pile asteroids, which fundamentally is going to give us context for the sample that we get back to Earth. So I'm going to focus on this talk eventually about the attempt to sample that's coming up and all of the processes that go into that. But I did want to make sure to highlight some of the really exciting science that we've been able to do with our time at Bennu. So we arrived at Bennu over a year ago in December of 2018. We've been surveying the asteroid ever since. And from that, we made a lot of really exciting discoveries. This is just a really small subset. So there's recently, just a few months ago, a paper by Jamie Malaro in Nature Communications observing and detailing and actually mapping cracks in boulders and foliation surfaces in boulders, where she makes a very strong claim that we're observing the rock breakdown process on Bennu in an atmosphereless, in an environment with no atmosphere, strictly due to thermal effects and diurnal cycling of temperature at the surfaces of these boulders. We made an absolutely stunning global shape model of the asteroid using the laser altimeter supplied by the Canadian Space Agency. The science from this has been bountiful, and there's going to be a paper's been submitted to Science Advances where they use this information to detail differences in the two hemispheres of our target body, but is also incredibly useful for getting detailed digital terrain maps of the potential sample sites. And finally, one of the really big surprises when we got to Bennu is that it's actually active. It's releasing particles into space. Some stay on very close orbits, but others are being ejected off the surface, never to return. So this was a really fun surprise, and there was a paper in Science last summer by the PI Dante Loretta. So from all of these scientific studies, one really big conclusion is that Bennu is absolutely the target we had hoped for. We'd hope to get to a near-Earth asteroid that would be something similar to a meteorite, like a CM carbonaceous chondrite, something that would be rich with hydrated minerals, and that's exactly what we found. And this was presented in Nature Astronomy by Vicki Hamilton, and the plot just shows the spectral reflectance as a function of wavelength for Bennu up there on the top in black, compared with a bunch of really primitive low albedo carbonaceous chondrite meteorites that are rich in water-bearing clay minerals. Exactly what we want. We see this across the entire surface. So we're really expecting that no matter where we choose to sample, we're going to be getting the material that we were looking for. Now, Bennu did absolutely surprise us, and in some ways that have had to change the way we were thinking about our sampling strategy. So fundamentally, the asteroid was far more rough and rocky than expected. Our expectations had been built on thermal observations from ground-based instrumentation, and also radar observations. And those gave us an impression that it would be as rocky or less rocky than asteroid Itokawa, which had very large ponds of fine grains across the surface. And in this global revolving image, there aren't really apparent any large ponds of fine grains. And to assure you that we weren't just zoomed too far out, we can zoom way in on Bennu. And here are some images, and you can see the scale bar in the upper left showing only 5 meters across. And here's another one with a similar scale bar. And another one with a similar scale bar. Bennu is a rubble pile in the truest sense of the word. And there's an absolute dearth of ponds of fine grains and an absolute abundance of meter-sized and larger boulders. Now, this is really important for us because of the restrictions of our sampling mechanism. And so let's watch an animation of how the sampling attempt is meant to go for OSIRIS-REx. So that's our main spacecraft that extends a 3-meter-long arm from the bus of the spacecraft. At the end of it is a 32-centimeter diameter ring, an annulus, that is pressed into the surface at 10 centimeters per second. After the spacecraft detects that contact has been made, it blows high-pressure gas into the surface and then only makes contact for a few seconds before we blow our back-away jets and fly away. And to zoom in on the actual sampling process, this is a cutaway of the sampling head. The outer diameter is 32 centimeters. The inner diameter is only 21 centimeters. And when particles are redirected by this high-pressure gas, they go through that red mylar flap, which is only 2 centimeters. And then they're captured in that ring, a metal mesh ring around the outside of the canister. So the restrictions here are that we need to avoid things that are 21 centimeters or larger because they could obscure the entire head. And we have to target particles that are 2 centimeters or smaller so that they can go through the mechanism and get captured. Anything larger than that likely won't get captured. So Bennu presented us with 2 really big challenges. There were no regions on the surface that were safe, that were as large as what we had planned for. We had planned for a diameter 50-meter deliverability region. And that is, we asked the engineers to build a spacecraft that could be navigated to a region 50 meters across using LiDAR-based navigation. And that there is absolutely no place on this asteroid that would accommodate that. So on the engineering and technical side, we have moved to a natural feature tracking based navigation. So this required developing a bunch of geologic features that could be unambiguously tracked optically by the spacecraft for navigation. This could be much more accurate than using the LiDAR-based navigation that we had planned on. This required going back and changing a bunch of observational campaigns so that we could actually develop and find these features around all of the candidate sample sites. And we had to change some of the software on the spacecraft to be able to utilize this technology. Doing so brought the deliverability region from that diameter 50-meter size ellipse down to something closer to 7 or 8 meters across. So it was a huge development that absolutely increased the number of potential sample sites on the surface. It also allows for a hazard map so that the spacecraft can trigger a backaway burn and wave off a sampling attempt if it detects that it's headed towards what we have predetermined is a dangerous spot on the surface. So that was on the technical and engineering side. On the science side, the Regolith scientists were tasked with initially finding the best spots on the surface for our sampling mechanism. Where's the largest collection of 2 centimeter and smaller grains to optimize the total mass that we could collect. And when we saw the surface, we realized that we would have to, in fact, reverse this question. And we approached things in a different way. And we said, where can we positively identify particles that we cannot ingest? Let's map those across the surface and avoid those spots and find the minimum using that metric. So we cultivated regions of interest using a bunch of approaches, using machine learning and citizen science platform. We started with 50 regions that were interesting. In the end, we boiled it down to 4 really exciting regions. They're different flavors of small craters on the surface. Those seem to be the smoothest and most devoid of really large particles. In the upper left is our prime sample site. It's a 23-meter crater in the northern latitudes. It's one of the darkest and reddest craters on the surface, which gives us hope that it's full of really primitive and unaltered material that we're really targeting. It is worth noting that you can see in that rotating image, there is a 10-meter boulder that is 7 meters tall sitting on the edge of the crater. The backup site is Osprey in the upper right. It's a 20-meter crater. It has more larger particles that could frustrate sampling. That's why it's the backup. And it has a 3-meter crater sitting at the 12 o'clock part of the crater, which is also a little bit worrisome. So in the end,
Hey, Kevin, the ding did not work. So if you could finish up in the next minute, that'd be great.
Okay, I will hurry through these. So this is the image of the sampling site, given for scale roughly the 3 sigma deliverability region within the site. And the red pixels are those that would be considered hazardous and could potentially trigger a backaway burn and a wave off from a sampling attempt. And for scale, that is roughly the size of the spacecraft with the extended solar panels sitting in the middle of the crater. So this is just to visualize how tight of a spot we're trying to get the spacecraft into. We have 2 rehearsals, one complete and one upcoming, before we tried to tag in our sample in October of 2020. The first rehearsal was in April, and that's what this video is of. And that boulder that we are descending towards and then backing away from is that 7-meter tall boulder. We will go to 40 meters from the surface in August before we attempt to sample in October. And so with that, my conclusions are really straightforward. Bennu, this near-Earth asteroid, has absolutely supplied all of the exciting scientific discoveries that we expect when exploring a new world. And choosing a site required technical challenges that really pushed on engineers and scientists to come together to solve some difficult problems to find a spot that we could sample. So with that, I'm happy to take any questions.
Thanks very much, Kevin. Apologies that the ding did not work. But any questions from the audience? We have time for just one quick question if you want to enter the chat or raise your hand in Zoom. And if not, we do have a discussion session built in after this session. So Kevin, if you and the other speakers can stick around after the 6 talks are concluded, maybe the audience will have time to think of a question for you during that discussion period. Okay, so let's go ahead and move on to our second speaker. We have Elena Adams from the Johns Hopkins University Applied Physics Lab talking about the Double Asteroid Redirection Test, or DART, NASA's first planetary defense mission. Elena, go ahead and take it away.
All right, sound check, and if you guys can tell me if you see the slides.
Got you loud and clear, and we see the, we do not see the full screen view. There it is.
Okay, all right, great. So my name is Elena Adams. I'm the mission system engineer for the DART mission. Please excuse me, I am in integration and test right now. We're getting ready to launch in about a year, but we are working very hard right now to get this mission off the ground. So this is the first NASA's planetary defense mission. We're part of the Planetary Defense Office at NASA. You can see that the Planetary Defense Office at NASA, just to give an overview, does a lot of things for the nation, including the searching, detecting, and tracking of the asteroids, using ground-based and space-based observations, characterizing of the asteroids, and NEOWISE comes to mind, as well as soon to be launched NEOSM as well. They plan to coordinate between all the different working groups and with other nations as well. They also do the mitigation, which is DART is the first actual test of mitigation of an asteroid threat, and the FEMA exercises as well, and then they assess how well they did. Okay, so here's DART. Just to, sorry, trying to minimize things. Here's DART. We launch next year. Our planetary launch window opens up in July 22nd of 2021. Our goal is to impact the Didymos system. Recently, we were able to, we got a name for our actual moon that we're going to impact. For a while, it was Didymos A and Didymos B, where Didymos A was the larger asteroid, and we were impacting the moon that was moving around the larger asteroid, which we call Didymos B, which was, you know, not a very good name for a moon for a while. But now we're very happy to have a name, Dimorphos. The larger moon is about 780 meters. We're impacting a smaller moon that rotates around the larger moon with a period of about 12 hours. And it's about the size of about 160 meters. Our goal is to impact the moon of the asteroid and change its orbital period around the larger moon. The spacecraft itself is shown here. It is about 650 kilos and about 18 meters. We're also, what we're carrying with us is a small CubeSat provided to us by by ASI, the Italian Space Agency. And this CubeSat is going to fly by the Dimorphos about 3 minutes after we impact, 3 to 5 minutes after we impact, and it's going to image the plume that we create after the impact. So just to explain a little bit more, if I can switch over. So here's the two moons. Here's Didymos A is right in the middle. Didymos B or Dimorphos going around it with an orbital period of about 12 hours. We're about 6.8 million of miles from Earth at impact, about 0.07 AU. So this is the closest approach of Didymos system to Earth. So that happens right in October of 2022 timeframe. So at first, so as you can see, after DART impact, we changed the orbit by about 1%, and that amounts to about 10 minutes. Actually, our requirement is only 73 seconds, but right now the predictions show that when we impact Didymos, we will decrease its orbit to be by about 10 minutes. So it's not much, but it is very safe because you can imagine that since the moon is only for a controlled experiment, this is a really good approach. So not only does DART do a demonstration of the first planetary defense impact, a very controlled experiment, we're also going to be demonstrating a few new technologies for future planetary missions. Number one technology that we're demonstrating is the autonomous smart navigation. We are not able to see Dimorphos until about an hour out before we impact. In fact, we don't actually even know what shape it is until about an hour out, and about an hour out where it's approximately a pixel in our field of view. So there's that, and we don't really see it until about 4 minutes out. We don't see it's not more than 20 pixels to us. So the smart nav allows the spacecraft to be completely autonomous and perform all the maneuvers to target Didymos B and Dimorphos instead of the main asteroid completely late in the game. The ground is just listening the whole time. So we are imaging the asteroid as we're going towards it using our Draco imager, which is based on LORRI from the New Horizons mission. It's a narrow angle camera, and that's what we're using for both optical navigation. So that's what we're using 30 days out when we first detect the Didymos system, and all the way in while SmartNav is using the images from Draco to be able to pick out Dimorphos instead of everything else in the background and actually target towards it. And then we're also demonstrating the NEXT-C ion propulsion engine, which is the next exciting ion propulsion engine. If you remember Dawn mission, they were able to go to multiple asteroids, and what enabled that was really the ion propulsion. We're demonstrating this development that NASA has been investing into for about 16 years on DART. And to power the NEXT-C ion propulsion engine, we need very large solar arrays. And for that, we're demonstrating the rollout solar arrays, which is a first powered flight of the solar arrays as well. They were first demonstrated on ISS, but it was just a TRL-6 demonstration where they just rolled out. We're actually going to be using to get all our spacecraft power. This is what our spacecraft kind of looks like. This is just a CAD model of it. It's a box. The rollout solar arrays are on the sides. This is the NEXT-C thruster sitting underneath a cover that we blow off pretty fast after we launch. With the rollout solar arrays, it's about 60 feet, so 18 meters long. So it's a very large spacecraft. And of course, LICHA CubeSat is shown over here as well. Okay, so just a note, we know very little about the object we're going to hit. If you look at this observation, this is an observation from VLT, from the DART team that was taken in 2019. What you're seeing here is Didymos moving through the star field. This is the kind of observation we can do right now. In 2003, Didymos came close to Earth. There were some observations done with radar, and that's where we have the radar shape model. As you said from the previous talk about Bennu, we don't expect it to look exactly like it, but this is the best image that we have of the main asteroid, Didymos A. We have no idea what Didymos B or Dimorphos actually looks like, and that is one of the challenges of this mission.
2-minute
So
warning.
we think okay, thank you. The last 4 hours of this mission are going to be very exciting. We're basically going to be not seeing the asteroid until very close in. And at that point, the spacecraft is going to be completely autonomously navigating towards it. And what I'm showing here is how what people are going to see on the ground as we're getting close in. We're streaming images real time, once per second, so it basically looks like a video to those on the ground while trying to keep the camera on Dimorphos, and our requirement is to stream at least one image in the last 7 seconds of the mission. So, what we're doing right now is integrating and testing the spacecraft, getting ready for launch next year. This is our structure that's actually in integration test right now. We are launching on a SpaceX Falcon 9, and this is our very excited team as we're getting ready. So last point to make is that we are part of the international cooperation with the ESA space agency as well, and the Hera mission is going to arrive to Didymos in 2026 and is going to look at the impact site after DART. So I think that's it. Thank you.
Thank you so much. Do we have any questions, again, either via chat or via raising your hand in Zoom? Great, yeah, comment on excellent example of different agencies working together. Okay, so again, keep thinking of questions and we'll have the discussion period later on. Good luck, it sounds like a really exciting mission that you're working on. I think everyone was really excited to hear about it. So our third speaker in the session is Elliot Sefton Nash from ESTEC at the European Space Agency. And Elliot will be talking about the ESA Prospect payload for Luna 27, a development status.
Yeah, thank you very much, Kelsey. Can you hear me okay?
Yep, got you loud and clear.
Great. So good morning, afternoon, and evening to everyone online. Thanks very much to the organizers of this meeting and the session chairs. Delighted to be here to give you an update on the Prospect development status. Prospect is a payload on Russia's Luna 27 lander to the south polar region of the moon. And I'm here representing a broad swathe of people, including the science team and the industrial consortium. So I don't think it's news to anyone here that LCROSS provided a very compelling result, that there is an abundance of near-surface volatiles in lunar regolith in polar regions. Of course, LCROSS impacted in Cabeus crater, which is in permanent shadow, but of course that doesn't mean there are not volatiles that could be cold-trapped in a kind of semi-permanent way in places that are not permanently shadowed. And these are the places that are of interest. And certainly for landers who rely on solar power, that's quite a compelling argument to target these places. The evidence that we have from remote sensing data sets and also from theoretical work shows that actually it's not a completely clear-cut picture about the distribution of water ice in particular at the lunar South Pole in this case. So we really need ground truthing, and that's really what Prospect is aiming to deliver on. And I'll just give an overview of the lunar program. So it's part of the Roscosmos, the Russian Space Agency's lunar exploration program. Luna 25, or otherwise known as the Lunar Glob lander, is scheduled to launch with a contribution called Pilot D, which is a demonstrator precision landing package. 26 is an orbiter, and then 27, which is scheduled for launch in 2025, partially confusingly, will carry Prospect along with the full version of Pilot, which has a LiDAR and imaging navigation system for precision landing, as well as a communications package called Spectrum for UHF communication with the orbiter. Prospect Phase C, which is the detailed design phase, is well underway, and we're looking forward to delivery of the Prospect payload in 2023. Prospect has a large number of objectives. Please don't try to read these. I try to condense yet socially distance them into 4 key things that I think are important takeaways. The first is that we want to perform cryogenic extraction of regolith from down to about 1 meter. We want to characterize the polar surface and subsurface environment. And importantly, from a science perspective, we want to understand the abundance, the composition, both elemental and isotopic, of cold-trapped volatiles, both physisorbed and chemisorbed in lunar regolith. Crucially, from an exploration perspective, we'd like to also understand what the propensity is for extraction of oxygen, what the efficacy of oxygen extraction from lunar regolith is. And this is something that Prospect can do regardless of its landing site. So we're really trying to fly something which has science and exploration return in a kind of wherever it lands, which gives it some value for which other mission opportunities may come. So what is exactly Prospect? Well, it's really 2 main components. On the left in this rendering, you can see the lunar drill. It's called PROCEED. I won't go through all the acronyms. Basically, it's a drill accompanied by an analytical suite, which also does some sample handling and distribution to the Russian instruments aboard the Luna 27 lander. The 2 elements have a number of features, which I'll just go through. So of course, the drill can extract down to about 1 meter. As I'll talk about in a minute, this is important for sampling shallow zones of potential volatile stability in the long term. The sample size that's delivered to the Prosper instrument is about 100 milligrams, but there's a larger sample delivered to instruments on the Russian payloads. And so there are sample receiving mechanisms for both types of sample, and the drill is designed to do both. In the drill, there are a number of sensors, including torque and temperature and permittivity. These provide not only operations information, but science results. And there's an imager on the drill with 6 LED groups to characterize the local mineralogy. The PROSPER part of Prospect is the analytical lab and what we call the solids inlet system. So this is the kind of sample handling and processing part of the package. The PROSPER lab itself contains a number of quite compelling sensors. So it has an ion trap mass spectrometer as well as a magnetic sector, and an elaborate system to do gas processing with reactors. And it allows you to do evolved gas analysis by extracting volatiles from lunar regolith. It also has the capability to go up to about 1,000 degrees to do ISRU. And as part of the solids inlet system, as well as the carousel of ovens, there's an imaging system which allows you to constrain the sample volume, which you need for volatile abundance measurements. It's worth mentioning that part of Prospect was selected to fly on the Astrobotic Peregrine lander to Lacus Mortis next year. Exciting to say next year. So it's undergoing an aggressive schedule for development and qualification before delivery. And there's an abstract by Barbara Cohen, an LPSC abstract that was out this year. So it's worth saying Prospect is not necessarily just one payload. It's a family of payloads and derivatives that are suitable for many flight opportunities. We see Prospect as being one payload, but it has many investigations, and we've divided the science team accordingly. We focus on drilling, geotechnics, and sample handling. There's an imaging team dealing with image data coming from the two camera systems. For the sample analysis, we divided it into noble gases and then light elements and isotopes. And they're closely linked to the thermal environment of the landing site and the preservation of volatiles through the sample handling chain. We also have investigations about the precursor experiments, kind of a ground calibration for the ISRU demonstrator, and also for perhaps in kind of a new space mode, we have a prospecting investigation, which is really focused on trying to see how terrestrial mining practices and resource certification and uncertainty estimation can be applied to lunar resources. We also have a permittivity sensor on the drill, which characterizes the water content of the regolith as we drill down. Speaking of the drill, we had a successful test campaign in late last year, where we demonstrated the drill design is mature and capable with all the test scenarios that we could think were reasonable and a few extreme cases. We did tests at a range of simulant configurations with different size distributions, putting in large chunks of amorphosite to try and trick the drill, and at a range of different water ice contents. So we really tested it under a range of conditions that we might expect in lunar polar regolith. The images are really designed to, first and foremost, monitor and analyze the drill and the work area, observing the cuttings pile that gets produced as we drill downward. But also informs things about the landing site, the local area, local geology, constraining the local topography, the illumination conditions. It also monitors the transfer of the sample to the solids inlet system. So it's really a catch-all camera to monitor the activities in operations, but also get science data from. And the sample camera, as mentioned before, characterizes the volume of the sample inside the very small ovens before they are heated to evolve volatiles. The permittivity sensor in the drill, the design of that was tested, so you can see a prototype on the bottom right here. Basically, it determines the electrical permittivity of the materials that are in contact with the sensor. And as we drill down through the borehole, we'll kind of get a spiral-shaped profile of the permittivity as a function of location inside the borehole. So this will tell us something about water ice content, but maybe we can also tease out some other geologic properties depending on how the ground calibration goes. One key thing we're working on is understanding the volatile preservation. If we sample volatiles from depth, we need to know how they are preserved throughout that sampling chain, but before they are analyzed, in order that we can then back out the science information that we want. So for example, the original isotope ratios of D2H, we know their fractionation happens as a function of sublimation. So constraining that and knowing the thermal environment will really help us answer the science questions in a more constrained way. So we have a series of activities that are ongoing to try and really make sure that we have good bounds on these processes to allow us to meet the science objectives that we've set. So really this leaves us to a bunch of priority activities that the science team and the project team are doing during phases C and D. Volatile preservation is really a priority. We're characterizing the cameras, doing a lot of analysis of the engineering models, designing the calibration targets, thinking about how we should characterize the cameras using analog samples. We're trying to understand what the magnitude and the impact of potential contamination for the evolved gas analyses might be. So for example, thruster plume contaminants and things like that may exist. And we're also trying to figure out exactly, given the resources we may or may not have, not only on Luna 27, but on any other potential future mission, what are the science priorities, given a finite time, power, and other conditions that are limited, for example, data, then we need to understand what should we do first to get the maximum science with the minimum resources. So these are the main things that we're focusing on. And of course, there are ongoing discussions about landing site characterization. This is really a shout out to LRO, who have done a fantastic job, over many years, more than a decade, producing fantastic data and being able to characterize landing sites in such a precise way, such a holistic way. We now have, fantastic global coverage, but specifically over the South Polar region. We can really drill down and find the compelling landing sites that allow really good science results. The places with the best combination of all the parameters that would allow us to meet our operations scenario, but also to maximize the chances that we can meet our science objectives.
And if we could wrap it up, that would be great.
Yeah, so we have ongoing work with that, with our Russian partners as well. And the main message there is that there are many exciting places, but we have to consider the time series of illumination conditions very carefully. And just to finish up with a list of great recent work done by members of the science team, and that I'll take any questions if there's time. Thanks very much.
Great, thank you so much. We have one very quick question and then we do have to move on. Jennifer Heldman asks, really interesting mission, and I'll echo that was really fascinating. Jennifer asks, given the complexity of this mission, especially regarding the sample handling process, are there plans for terrestrial analog testing of the hardware and operations?
Yeah, absolutely. The drill tests, well, not just of the drill, they also included the sample handling system. And to elaborate on those, we'll have qualification tests. In parallel, we also have the volatile preservation activities, which are a combination of lab tests and specific setups. And then we couple those to modeling in terms of diffusion rates, sublimation rates, thermal conduction. So there's a suite of things that will form an understanding of the sample chain.
Great, thank you so much. And then I'll turn it over to my co-chair to conduct the remainder of the session. Thanks to our first three speakers.
So next up is Dr. Bethany Ellman. She's a professor at Caltech and PI of Lunar Trailblazer, and she's going to talk about Lunar Trailblazer, a pioneering small satellite for lunar water and lunar geology.
Okay, thank you. Can I confirm that you can both hear me as well as see my slides in full screen mode?
Yes, we can.
Okay, great. Well, thank you to the organizers, and I'm, as we all are, acutely sensitive to the fact that this is challenging to organize in a pandemic, but I think you've done a great job so far, and I enjoyed this morning's sessions and look forward to hearing about the science and exploration of the future. So adding to that, I'm very pleased to have the chance to talk in this session about our mission Lunar Trailblazer, which is a small satellite for lunar water and lunar geology. I am the principal investigator. You heard earlier in the morning in the panel session from Rachel Klima, who's the deputy PI, and we're supported by the science and engineering organizations here. You see the line on the bottom. So it's a large team behind the effort I'm presenting. What is Lunar Trailblazer? We are a small science mission selected in June of 2019 under NASA's Simplex call. We're a mission to the moon. That's an ESPA Grande ride-along craft, and we're getting a ride on NASA's heliophysics mission IMAP. We are coming up on our preliminary design review in October, and our mission is supported by both the Planetary Science Division and then transferring after our PDR to SEO. Our goal of Lunar Trailblazer is to understand the form, abundance, and distribution of water on the moon and the lunar cycle. So it ties in very well to the types of missions that Elliot has just articulated here. Our goals are to determine the form, abundance, and distribution of water and hydroxyl on the sunlit portions of the moon, to understand the controls of the variability by latitude, soil maturity, lithology, to test for and map time variability in water on the moon, and to directly image and determine the form and abundance of water in the permanently shadowed regions, as well as understand the local gradients in terms of temperature. And so these are our driving science goals, but along the way, I think we pick up a lot of data important for exploration, including the best thermophysical properties and compositional maps of candidate landing site zones for our future landed missions. Now, I think everyone on this call is familiar with the drivers, the driving science, and the excitement of the discovery of water on the moon, from the work with the return samples of the Apollo collection showing a relatively wet mantle, as well as the remote sensing data of a suite of orbiters, and culminating with, in some ways, with the L-Cross impact and the direct detection of water in the plume. So a number of scientific questions then have remained regarding water on airless bodies, and the Simplex missions and Lunar Trailblazer is one, directly address questions from the decadal survey and are driven by those science questions to determine how volatile compounds are distributed, transported, and sequestered, and what are their inventories. So how will Lunar Trailblazer advance the state of the science of what we know about water on the moon? So we have the beautiful map that I'm showing here in the center portion of the slide of the OH and H2O distribution on the moon. M-Cube discovered the water on the moon, but that discovery was unexpected, and so the instrument was not optimized to characterize the water. Some of the key questions remaining are certain rock compositions or soils of different maturities more enriched than others in water, and does that vary with time on the sunlit side of the moon? Many of you on the phone may be familiar with some of the issues involved in this, so I'm showing on the upper right two different data sets. So the thin lines, the thin dotted lines, are the initial thermal model for Borealis crater, whereas the thick lines are the results from a new thermal model. And you can see that, well, depending on which model is chosen, either there is a water enrichment or there is not a water enrichment. So that thermal correction is really important. Just to bring that point home with an animation, we have a crew of interns working on our mission, and one of them created this great graphic. So you can see here in green, the OH H2O absorption, and how, as we move into the sunlit portions of the lunar day, how that OH H2O absorption is affected and influenced by temperature. You're effectively getting both the absorption in reflected light and emitted light, which causes this to be a tricky problem. So you see here the wavelength ranges of the two instruments carried by Lunar Trailblazer. HVM-Cubed will get at the OH H2O portion, while the Lunar Thermal Mapper will independently provide temperature maps. So that is, in effect, the key. Lunar Trailblazer will answer and resolve these questions about the amount of water and whether it is enriched or not in certain terrains by the enhanced spectral range and resolution that I'm also showing over here on the right-hand side, where you can see how M-Cubed senses the shortwave part of the key absorption feature, but HVM-Cubed will capture the whole feature to allow hydroxyl versus ice discrimination. And as mentioned before, we also will have the simultaneous temperature to correct these data and get the true water abundances on the surface. Now, the second thing that Lunar Trailblazer is designed to do is to directly image which permanently shadowed regions on the moon have water within those shadowed regions. So a proof of concept was demonstrated with LROC. This figure from Cisneros shows how you can use terrain scattered light, that is light scattered on the surrounding topography, to image directly what's in the crater. And Lee et al. Showed that if you aggregate and average many M-Cubed pixels, you can actually, even in the M-Cubed data set, pick out the absorptions of water ice frost. So HVM-Cube builds upon that and will directly image all of the polar permanently shadowed regions at the lunar poles to determine which ones have water ice at the surface, which ones do not, which ones is that hydrogen signature from neutron spectroscopy maybe in hydrous crust versus ice. And I think a question that many of us scientifically are wondering of, are there organics as well in these ices on the moon, just as there are on Mercury? And what does that say to the delivery of organics to the Earth-Moon system over time? So again, that spectral range and resolution allows us to unambiguously determine and identify water ice and organics with that radiometric sensitivity to do the direct imaging even in the shadows. The data sets will look like this. There's an image cube. It's an HVM cubed is an imaging spectrometer. So for every pixel, we'll have a spectrum, and I'm just showing a subset of the range on the right to get composition, while simultaneously nested within our data from the Lunar Thermal Mapper instrument, which allows that temperature correction, abundance determination, and better silicate mineralogy. And we'll be getting these types of data, nested data sets for multiple portions of the lunar surface, some with coverage at 3 times a day to search for time variability. So just to say a bit more about those instruments that I mentioned, the High Resolution Volatiles and Minerals Mapper, HVM cubed, is the legacy of M cubed, which you see here, but miniaturized and improved performance of this spectrometer funded under NASA Picasso development. It's an Offner spectrometer with E-beam grading that's optimized for signal in the 3 micrometer region. So you can see our spectral range spans from the kind of green wavelengths in the visible out to 3.6 micrometers at a spectral resolution of 10 nanometers, and that very high signal to noise and uniformity that will allow us to answer these outstanding questions about the form and abundance of water and dependence with thermal properties.
2 minutes, Bethany.
Thanks. The second instrument is the Lunar Thermal Mapper, and it has 14 channels. 6 of them are shared with Diviner, and it has a higher spatial resolution by a factor of about 10. We'll get 25 meters per pixel, and this allows us to get temperature and composition. In the interest of time, I will skip the part about how we get to the moon, but basically we launch with IMAP, which is a heliophysics mission to L1, arc back to the moon, and then enter into a science orbit that is 100 kilometers, polar orbit that is 100 kilometers plus or minus 30. The nature of our data collection is that we're a push broom system. So we're collecting data in targeted areas. The science team has identified 900 targets across the surface of the moon. We're a simplex mission. Our baseline approach is to target the most important areas for resolving these science questions about water. So this is kind of like HiRISE at Mars, those of you who are familiar with that. So we're getting 2% coverage of the moon under our baseline mission in these focused areas for science and getting all of the PSRs. At PDR, we'll be presenting NASA with something we said we'd do in our phase AB, which is a trade study that shows that by adding radio slices and antenna, this is $5 million, 5 kilograms, that we can get global coverage of the moon as well as serve as a comm relay for potential future assets. Where are we in our timeline? So we are in where the line is in green. We are here. We're in the middle of our tabletop reviews, heading toward a PDR and confirmation in the fall before we proceed to build and then launch on IMAP in 2024. So in the interest of time, I will close with a few thoughts here. Lunar Trailblazer is driven by decadal class science in terms of these questions resolving water on the sunlit surface of the moon and in the shadowed regions. I think appropriate for this forum, we are also gathering important information for exploration. Which permanently shadowed regions have ice right at the surface for future exploration and extraction? What are the best compositional maps of the landing sites? And then as mentioned, we have this option to add global mapping capabilities or service, future service in our extended mission for lunar surface communication. So I'll leave it with that and say you can ask me questions now or check us out on our website or Twitter or email me later. So thank you.
Thank you, Bethany. That was an excellent talk. And we have a couple of questions. So Phil asks, mission end, will it end with impact? And will science be possible in last few seconds?
Yes, so the mission will end with impact at some point in the future. We haven't done a complete budget, being only a pre-PDR, but we'll run out of fuel and impact the moon like all of the other orbiting missions. I don't know about science the last few seconds, but certainly the last few hours will be then transmitting the highest resolution compositional data as we go down, and maybe rate some radio science along the way as we go down. Yeah, the close-up view at the end of mission.
All right, we have one more question. I think we'll take that in discussion session because we are kind of running on time. So,
okay,
yeah,
thank you.
So next up is Dr. Ryan Watkins. She's a research scientist at PSI, and she's going to give us new insights into the lunar surface from LROC NAC scale photometric investigation.
Thank you. I am not able to share my screen right now.
Bethany, I think you'll have to stop sharing your screen for her to share.
Oh, yeah, there we go. Let me pull it up real quick. All right, are you seeing my slides?
Yes.
Okay, great. Yeah, so I'm not going to be talking about an actual mission or mission concept. Instead, I'm going to talk about some really neat science that we've been able to do with an ongoing mission, specifically the Lunar Reconnaissance Orbiter, and some neat investigations we're doing with the camera. So I'm going to talk about using NAC photometry to understand the physical and compositional properties of the moon. So for those of you who may not be aware of what photometry is, it's essentially just studying the reflectance properties of the surface and what those properties tell us about different physical and compositional properties. So there are a lot of different factors that affect how a surface scatters light, such as composition and mineralogy, glass content, surface roughness, space weathering, etc. So one of the reasons that we use LROC imagery is that it gives us the orbital data necessary for these photometric studies. Specifically, we have repeat imaging at different illumination conditions of the same areas. And this really allows us to do some good photometric modeling. When you combine LROC imagery with narrow angle camera scale digital terrain models, then we can determine photometric parameters at the DTM scale, so 2 to 5 meter per pixel. So these photometric parameters will depend on different things like composition or physical properties. And then just at the bottom here, you see that combining photometric data with LROC NAC images, and then coupling this with HAPKI photometric modeling and Apollo soil data can really enhance our understanding of the geology of the moon. And hopefully I will convince you of that with the rest of my slides. So here's this slide that I'm sure everybody was really hoping I would show, but lucky for you, I'm not going to talk a lot about it, but this is the HAPKI equation or a form of it. So we use HAPKI photometric models to fit reflectance data from the NAC images. The HAPKI reflectance models are some of the most widely used for interpreting regolith properties from spacecraft data, and they provide very good fits to the observations we see with the NAC images. So really all you really need to know here is that there are a few key parameters that we're interested in. Here's a single scattering albedo up here. This is largely dependent on composition. And then the B and C parameters, which are sensitive to backscattering characteristics and are really just controlled by physical properties like grain size, grain shape, glass content, and things like that. So for the work that I'll show you in the next few slides, the inputs that we need to determine these parameters are the NAC image itself, which has the reflectance data, or I over F, as you'll see the reflectance listed as. Then we need the illumination conditions at each pixel. So these are the incidence, emission, and phase angles. And we are able to calculate these using the NAC digital terrain models and slope data. And then finally, just some other model assumptions and parameters that we derive from empirical and experimental data from other works. So again, just most of what I'll show for the rest of the talk will be a single scattering albedo, but I will talk about B briefly at the end. All right, so then this is just another schematic showing how we take reflectance data from the NAC image coupled with the digital terrain model, which allows us to derive local geometries for each pixel. So local incidence angles, local emission angles, and local phase angles. And these feed into the HAPKI equation as well. And this allows us to output parameter maps. So the one I'm showing here is a single scattering albedo parameter map. And again, this is on the scale of the DTM, which ranges from about 2 to 5 meters per pixel, depending on the actual DTM. And this allows us to really get at physical and compositional parameters at the meter scale or the outcrop scale. So now I'll move into telling you how we're using NAC photometry and these parameter maps at different sites of interest across the moon. So one of the best places to start with is the Apollo sites, because we have very extensive NAC coverage of these areas as well as sample data. So, excuse me, Tim Hahn created a regional scale single scattering albedo map of the Taurus Littrow Valley, which you see here in the corner. And you can see the different colors basically correspond to variations in single scattering albedo, which also correspond to largely variations in composition, but also some in maturity, which I'll touch on briefly. And I will just apologize in advance. The color schemes for each of these maps is going to be just slightly different from one another. We haven't really standardized the best way to display these yet. And I've been trying to I'm in the process of converting a lot of them to colorblind friendly maps. So again, they'll be slightly different slide to slide, but just bear with me. You will see they're largely on the scale of 0 to 1. So what Tim Hahn did is he took images at the Apollo 17 site, again, created this parameter map, and then he correlated over, I think, 30 plus sample stations worth of data with the single scattering albedo. So here, this plot is the single scattering albedo as a function of mafic mineralogy. So FeO plus MgO plus TiO2. And here, the blue line is a linear correlation to the mature Apollo 17 samples. You can see there's a pretty good fit between mafic content and single scattering albedo. Now, you do see a few effects here kind of becoming a little bit obvious. There are effects from maturity. So immature soils tend to plot kind of above this relationship. And we're also looking into the effects of glass content on this curve. So that's kind of a work in progress, but we do definitely see some effects of maturity. So one key thing we really wanted to do with this was constrain the more feldspathic end of the curve. These other Apollo sites, these values are from some older work I did with blast zone studies. But we really just want to kind of get a better constraint on this end of the curve. So that's what we did. So the thing I've been working on the last, I guess, couple of months is the Apollo 16 site, making parameter maps here. So here you see the single scattering albedo map again. And here's the landing area and the different EVAs, as well as the B parameter map on the right, or my right. So you can see that the effects of maturity show up pretty distinctly. You get the rays of North Ray and South Ray crater, which are very immature, and they show up very distinctly in these two maps. So similar to Tim Hahn, I went in and extracted sample data for each soil sample. Primarily, I got mineralogy, grain size, and maturity data, and then correlated this with the derived single scattering albedo values that we got from the NAC images. And then, so here is the slightly updated plot. The fit has been slightly adjusted and is slightly better. So we've kind of begun really constraining this more feldspathic end of the curve. And again, you do see the effects of the immature soils really standing out here. So these are samples from North Ray on the immature ejecta. So these kinds of relationships are very useful for inferring the compositional and physical properties of other areas on the moon that we don't have ground truth data for. So I'll show you a couple of examples of places where we're kind of applying this. I won't go into all the sites we've used this on, but hopefully I can hit a few interesting ones. So the first I'm going to show is the Apennine Bench Formation, which is likely the only large province of exposed crete basalts on the lunar surface. So this is work that's largely being done by Sarah Valencia. So she's using a combination of LROC photometry and M-cube mineralogy data to look at the compositional variations at the Apennine Bench. And the preliminary results so far seem to suggest that the mafic contents within the Apennine Bench are remarkably similar to those seen in Apollo 15 crete basalts, likely indicating that the Apennine Bench Formation is volcanic, likely volcanic. And again, this is the same plot that I showed before, but now we've got the different materials within the Apennine Bench region plotted here. We can also use these correlations to investigate exposures of pure anorthosite on the moon with the goal of better understanding the distribution of crustal rock types at the NAC scale. And I'll kind of talk through this quickly, but if you want more information, there is a poster by Brad Jolliffe this afternoon. So you can check that out for some more details. But if you're not familiar with pure northocite, basically we have hyperspectral imaging data that suggests there's a northocite in very high percentages, so about kind of greater than 95% plagioclase. And Anna Schoenwald went and looked at a few of these areas of pure northocite detections and correlated their single scattering albedos with iron content. And based on her correlations, she found that most of the plagioclase areas didn't really exceed 95%, most of the pure northocite areas didn't exceed 95% plagioclase, likely indicating that there are other mafic components present among these anorthositic rocks. And again, check out Brad's really great poster and audio recording if you want more information. So again, I haven't talked a lot about the B parameter yet. We're still kind of working on establishing some of the quantitative correlations between the B parameter and physical properties, but we are starting to look at it, especially in context of lobate scarps. So this is work being done as part of the Survey-Trex team. We've begun a comparison using OMAT data and NAC photometry to analyze the various surfaces around lobate scarps and other tectonic features that have possibly been recently active. So we're looking at what the B parameter can tell us about surface changes here, and then whether these surface changes could help inform or benefit future exploration. So here I'm showing an example of the Henderson scarp. Here you just see the reflectance data from the NAC image, and then the single scattered albedo and the B parameter. And as we would expect, we don't see any real variations in single scattering albedo, aside from those that we may see with maturity. So again, we don't expect any big compositional changes. But we do notice that we do have some distinct differences in B values right along the scarp face for many of these locations. We're still kind of teasing out what this may mean, but variations in the B values could likely indicate physical changes that were induced by seismic shaking. So differences in perhaps surface roughness, or maybe changes in grain size or grain shape that was induced by the breaking apart of particles during these seismic events.
And if we could wrap it up soon, Ryan, that'd be great.
I can do that. This is my last slide. So just to conclude, I hope I've convinced you that photometry is a very powerful tool that has many useful applications for studying the lunar surface. Correlating photometric parameters with Apollo sample data is really useful for helping us understand physical and compositional properties of areas of interest. And here I've just listed examples like using single scattering albedos from Apollo 16 can inform pan-mineralogy, or Apollo 17 Be values at different areas, such as maybe the Lee Lincoln scarp can inform lobate scarp properties, and much, much more. But really ground truth is key. So we really need more samples to bring back so we can correlate with remote sensing data. With that, I'll thank you.
All right, we'll take the questions if there are any in the discussion time. So moving on next, we have a talk by Dr. Noah Petro. He is a project scientist for LRO at Goddard Space Flight Center, and he's going to talk about the gift that keeps on giving, LRO at Levin.
All right, thank you so much. Comm check, we're good?
Yes.
Okay, fantastic. Thank you again for this opportunity to talk about spacecraft that has really revolutionized our understanding of the moon and its place in the solar system for now 11 years. It's been a remarkable run. I can remember back to the very early LSI, NLSI forums and the excitement around the initial release of data, and here we are 11 years later. And as Ryan so eloquently showed, the data keeps on coming and we're learning more and more about our awesome neighbor in the sky. So let's just talk a little bit about LRO right now. There's been a number of papers that have come out in the last several weeks, generated some interest. Many are after the paper just come out, S.M. Heggie looking at dielectric properties of the surface, particularly at the floor of larger craters in the Northern Hemisphere, and Ariel Deutsch's paper on the roughness of polar craters as an indication of the age of volatiles. One of the really remarkable things about these papers is how broad the types of science that we can do with LRO data, particularly pointing out the Ariel paper, you know, it's a derived product from the topography that Lola has been collecting. Again, 11 years later, I think it's remarkable that we're still harvesting such a wealth of information from our vast data sets. And as Ryan pointed out in her talk just a moment ago, that, you know, we are pushing the boundaries of what we can do with our data. Again, looking back what we thought we would do with a 1 or 2 year mission, to be able to have these kinds of parameter maps over multiple sites because of NAC images is truly remarkable. LRO is healthy. For an 11-year spacecraft, we're pretty soon going to be able to qualify for vintage license plates. You may remember from several years ago, we had turned off our miniature inertial measurement unit. This helps us preserve the life of that object on our spacecraft to use in case of emergencies. Because we turned that off, we needed to come up with a completely new mode to do slews. There was a period of time that we were not doing slews. We're now back in a slew mode, and we continue to refine how we operate the spacecraft. Ben talked about the ESO office at headquarters. LRO is now completely managed within that office at headquarters. Gives us an opportunity to work directly with CLPS landers through the Johnson Space Center and provide landing site support for those commercial landers. As everyone has experienced an impact because of the pandemic, LRO is no exception. Goddard is at stage 4 still, which means we have a very limited amount of people who can go on center. We have adopted a very rigorous social distancing scheme for the operations team at Goddard. No more than 3 people in our operations room at any one time. We've been rotating people in and out of the room to minimize direct contact. They're in close proximity for no longer than necessary and then sent home when we have our commands uplinked for the day. So far, the team is healthy, morale is high, and we've been able to manage LRO in this pandemic, I think, remarkably well. We've also at the same time been training new members of our operations staff, which is giving us a certain amount of a deep bench for continued operations. I'd like to also point out that we operate using for uplinks periodically the global data network, and so we were expecting hiccups, particularly with the Madrid DSN station. That didn't happen as Spain went into a very dire situation with the pandemic several months ago. We also, during the pandemic, or at least recently, had penumbral eclipses where we monitor the battery since we lose direct solar power for a short period of time. LRO went through that with flying colors. Let's talk a bit about the future. We are right now in our 4th extended science mission. This will take us through September 2022. We now have these 3-year extended missions, which gives us a little bit of breathing time from proposing to implementing our mission to preparing for the next senior review cycle. We anticipate proposing to ESM our next extended science mission which will be due in March of 2022 or thereabouts, and we will ramp up the preparation for that starting next calendar year. We have approximately 16.7 kilograms of fuel remaining on the spacecraft, of usable fuel on spacecraft, which means given the mode at which we operate and our low fuel consumption, we plan that we can operate through April of 2027 at this point. So we have several more extended science missions to go. So those of you on the LRO team, keep those pencils sharp. Now, we really have minimized the amount of fuel we use on an annual basis. We do regular momentum unloads, which takes us about over 1.5 kilograms per year. We will do phasing burns prior to eclipses if we need to change our orbit slightly. And we will, if the need arises, change our orbit to optimize observations during, for instance, landings. We were looking forward to the eclipse landings coming up and potentially trying to make some scientific observations of those landings or around the time of the landings. One important note is that we are continuing to drift away from the poles, meaning that we get this incredible density of coverage around the poles. So at the plot at the bottom here, you can see that our orbit is right now at an inclination of about 86 degrees, plus or minus about 0.5 degree. By 2027, we will be about as far away from the pole as we'll get to about 83 or thereabouts degrees. This means that we are going to create an incredibly dense coverage of data over both poles, both north and south. This is really exciting for us, particularly with the interest in polar science coming up in the next several years. I know that some are having a hard time hearing me, so hopefully that's been, you're able to hear me now. Let's see, just as a reminder, we are in this low fuel consumption orbit, and ever since 2011, we've been in a highly elliptical orbit, which allows us to stay in orbit with a minimum amount of fuel use. Without that orbit, we would have met the same fate Bethany was talking about with Lunar Trailblazer. We would have lithobraked by now. At this point, our orbit is stable enough that we don't anticipate anytime in the next 40 years hitting the moon. Let's see. So since 2011, we've used just under 30 kilograms of fuel. As my daughter comes in to show me that she lost her first tooth. Very exciting. Congratulations, Amelia. The Tooth Fairy will make a special visit to you tonight. We're 1 decade into operations. We are a unique mission in that regard, that very few missions have operated as long as LRO. In fact, no missions have operated as long as we have. I try to show that there's these missions that have operated for 1 to 2 years. They capture a snapshot of the moon. We are now in this sort of extended duration, capturing the dynamics of the moon, looking at how the moon changes over time due to impact, due to interaction with the solar wind, and indeed due to the landings or interactions with other spacecraft, whether planned landings or crashes, as we had with the Vikram lander. And so this extended period of operation at the moon really gives us a completely new view of the moon and a completely new picture of how the moon is evolving underneath our feet. So I anticipate that line will continue to grow to the right, and the science that we can get out of that extension really increases. Statistically speaking, I think we're due for a larger impact than we've seen so far. We're all really excited for the chance of capturing what happens when you get a 1 kilometer crater that forms on the moon, and so hopefully we'll be right there. As we get to this point, we're learning that the science that we do enables the exploration in the future. LRO data. Hopefully everyone has a calendar reminder set every 3 months for when we deliver a new batch of data to the PDS. Of course, LROC is now delivering every month for the world to use. I'm going to give a little tutorial, quick highlight of that. Okay, so I'm going to hopefully run a video. It may be a little staticky of the quick map tool of some of the enhancements that came out within the last several months. Showed off some of this material. Not only what this means is that everyone can go off and find their favorite particular landing site. There are actually ways that you can do Boolean expressions. Show me areas that have slopes less than 10 degrees with visibility of the Earth of X or Y amount of solar visibility. Different compositional parameters as well. So this is a really incredible tool for digging into the resources that we've produced as a mission and making it available again for the entire world. I know that I'm now at about 10 minutes. I will make some of the links available. I'm going to end here with a visualization that we have of the lunar South Pole over the year 2024. This is a video that we'll be releasing in the next couple weeks, not only to remind ourselves of what will be coming down the line, hopefully in 2024 with Artemis 3, with the next man and first woman to walk on the moon, but also the chance for the science that LRO can do to support that. We're incredibly optimistic about the future. I think if we've learned anything over the last several months, it's that to engage with the public about science, we really need to be effective communicators of what we're doing, what our goals are, and how long it's going to take. And I'm excited for this opportunity, and I'm looking forward to enjoying that ride with all of you. With that, I'll conclude. And
all right, so do we have any questions? We have like 1 more minute left. So to the discussion, Noah, what do we plan on having after LRO? Because LRO has kind of, made us very much, I would say, addicted to getting high resolution data. And what next? Are we looking?
Trace of volatiles, does it move across the surface or don't move across the surface? That's a great hypothesis to test. The possibilities from both orbit and surface are limitless. I would also like to add, though, the importance of having this synergy between a landed mission and observations in orbit. And we've been able to interact with a couple rovers that are on the surface, at least observe their movement, but the possibilities of making really compatible orbital and surface observations are really exciting. So for instance, if we have a geophysical network that goes to the moon as part of the New Frontiers, a compatible orbital dynamics mission that is measuring the magnetic properties of the moon at high resolution, coupled with high resolution imaging. I don't think there'll ever be a day where we don't need more high resolution imaging of the lunar surface because, for one, being able to observe a landing site for geologic context or to see where an astronaut actually goes. We've been able to do this post facto Apollo observation, but boy, wouldn't it be great to have not only coincident high resolution imaging during a mission, but also before and after. And I'll wrap up there. I could answer that question much longer, but I don't want to suck up all the oxygen in the virtual room.
Maybe I'll have one last question. So LRO, looking up to the poles, we are very much in need of high resolution DEMs, which can be created using NAC stereo pairs. But again, we have really limited coverage, I would say, in darker regions of stereo pairs. So I understand that LRO is already in quasi stable orbit, but are there any plans to increase the coverage and get better stereo pairs, or to create more NAC DEMs for that, for helping future landing missions and everything else?
Sure, NAC continues, the LROC team continues to request stereo observations of high priority targets. We have many that we've already collected. I would also like to point out that we have much more work we can do with the LOLA DEMs. The LOLA team has worked hard to improve the quality of the polar DEMs. Granted, they're going to be at about 5 meter resolution, but for those that have worked with the LOLA polar data, it does also have some artifacts in it. The LOLA team is going back over that and working really hard to remove those artifacts. So I'd say that the story of our polar topographic data is far from complete, and there will be more work done. It's very challenging to get those NAC DTMs of polar sites. The lighting conditions at the pole are very, very harsh. We already have some DEMs that are in the USGS archive for polar locations, and the LROC team continues to work to collect more data. But those high resolution DEMs are very intense products to generate, and so it takes time to make them. But as long as we collect the data and get it in hand, we'll have it for use for future generations.
Thank you so much. I have one more question from Dr. Bethany. So Trailblazer is a mission I'm personally looking very much forward to. How would you suggest other people who are not currently involved with the mission, how will they have an opportunity to be involved in future, or do you have any openings, any grants or anything coming up? Is she here? All right. I think she's not here.
If we lost Bethany, I can jump in if that's okay.
Yes.
As deputy. So because it's a simplex mission, we have a very, very aggressive budget of 55 million. But one of the things we're hoping is that we can, or that NASA will consider a participating scientist program or something like that to help bring the community in. Another thing that we will likely do, especially depending on how all our comms trades end up, is opening up the opportunity for community members to select or to propose targets that we might look at. So we're going to do as much as we can. And if you visit the website, you'll see we are already trying to kind of bring in as much of the public and the community as possible to help them be involved as we can with the mission.
Thank you so much. Do we have any more questions from the audience? I can maybe take a second to look through if there are any. All right, so I think we have come towards the end of this session, and I would like to
actually, can I ask a question of Rachel for Trailblazer?
Yes, please go on.
All right, so Rachel, just what's your PDS archive plan? Everything's going to go into PDS after mission, after 3 months, posted on GitHub, xArchive. I don't how is it going to work?
Yes. I can't remember right now what we said for our first delivery. But we just had a telecon about the different products and how we're going to deliver them. We're talking about doing a kind of M-cubed style for HVM cubed, where we've got the backplanes and all of that. We will presumably get the like the radiance data and those kind of data out as quickly as possible. Because it's a small team with not a lot of funding, the more derived products will probably be a later type delivery like we had before. But yes, I mean, it'll go in PDS like typical. And if you want, I will look up the promised timelines for deliveries.
All right.
Nice beard, Noah.
So we have kind of come towards the end of the session, and I would like to thank SRV for giving us the opportunity, me and Kelsey, both of us, the opportunity to chair this wonderful session with wonderful speakers. Move back to the next session, I guess.
Yeah. Well, Nandita and Kelsey, thank you so much for your excellent job chairing, and thanks to all the great speakers. Really, really enjoyed the session. And what we're going to do now is have a little bit of a break. We're going to come back in about, I guess, 17 minutes at noon Pacific. For those who want to stay, I invite you to stay. We're going to be showing a video done by my friend and amateur astronomer Gary Varney, who has taken a nice video, put it to music with of the moon. These are entirely amateur images, and it's pretty impressive. We saw something similar to it last year at the forum, and then we're going to have slides after that, and then we will return for the next session at noon Pacific. So, so thanks, and we'll see you in just a few minutes.
All right. It is 12 o'clock on the dot, and I'd like to get started. Thank you all for continuing to be with us all day. This is going really well so far. Just a quick overview before we jump into the Student Lightning talks. During this block, we'll start with these talks. We'll do the ISRU Viper session, and then we'll jump back to missions. We have Masaki Fujimoto at the end. And then while the discussion is going on, we will also start the poster. So people who want to stay and follow up with questions, please do. And then people who want to move on to the poster session may do that as well. So with that, I will get started with the Student Lightning Round talk. Each student has 1.5 minutes to introduce themselves, their poster, their work, and to advertise for you to come visit them. Most of these presenters are in the session today, but maybe not all of them. So check the poster listing. I would also like to add, while I'm thinking of it, to please check the poster listing online at the Survey website, because we have been getting some changes today as to which posters. So both the sign-up sheet and the online system are being updated regularly. So you'll see if anybody had to withdraw. We've had a few people with illnesses. Okay, and with that, our lineup today is here, and I'm going to jump right in with Mason Bell. So Mason, go ahead and turn on your microphone.
Hi, everybody. Thanks, Christina. Can you hear me?
Yep.
All right, perfect. So hi, everybody. My name is Mason Bell, and I'm actually here with Arun Kumar and Phaedra Curlin from the University of Colorado Boulder. And we are presenting our lab's work on robotic assembly recovery using virtual reality training for low latency lunar applications. So with coming goals to create a sustainable human presence on the moon, the call for real-time telerobotic operations has never been greater. Current high latency applications on foreign bodies leverage command sequencing to communicate with the rover from Earth. On top of this, hardware duplicates are utilized on the Earth's surface to recreate problems that the rover runs into. These are then used to develop solutions in a risk-free environment. As we move forward into the real-time operation realm, and with current stereo imaging technologies being able to provide real-time physical to virtual environment modeling, we intend to present new methods of failure recovery leveraging VR and AR. By developing our virtual recovery sandbox, we intend to create a virtual space representative of the rover's current state and environment, with the ability to troubleshoot problems as the operator standing next to the robot. By comparing our model to current failure recovery methods, we intend to assess how virtual recovery may supplement the operator's solution development for assembly failure whilst leveraging technologies already accessible to us. And our poster is actually being presented today, so come join us later. Thank you.
Thank you. Okay, now we will move on. If my slides will cooperate. They're just not cooperating. Okay, Anthony, take it away.
All right. Hi, can everyone hear me?
Yes, little bit faint, but so maybe speak up just a
I
little
can
bit.
I can get a little closer to my mic. All right, so hi everyone. My name is Anthony Carroll. I work at the Institute for Modeling Plasma, Atmospheres, and Cosmic Dust at CU Boulder. And part of what I do at Impact is I study electrostatic dust lofting, which is basically dust regolith on airless bodies or can be exposed to UV radiation or solar winds, and they eventually gain a charge, and the dust particles will eventually repel each other, overcoming cohesion and gravity, and loft and may become mobilized and maybe loft away. So this is really cool because it has a lot of natural phenomena that we think can be explained by electrostatic dust lofting, like the lunar horizon glow, dust ponding on comets and asteroids, and even the lack of fine-grained regolith on some asteroids. And so my poster is about measurements of initial launch velocities of a laboratory simulation for this process. So if that sounds interesting, please come check me out. Thanks.
All right, thank you very much. And let's see if we can move to the next slide. Okay, Rushik, are you there?
Hello, can you hear me?
Yes, we can. Thank you.
Hello, Namaste. I am Rushik Chandrachud from India. I am pursuing BSc from BK Birla College, Kalyan, which is affiliated to Mumbai University. Instead of talking in conventional manner, I would like to draw your attention to something different, yet important, and something crucial. When I was listening to some of the presentations earlier, I found that some of the presenters, there was a particular slide for sustainable development. I was glad that this aspect was emphasized and considered carefully by the space explorers. Even I have considered this aspect for the reusability and sustainable development while developing my Luna filter, which can provide mechanism for the filtration of lunar dust over lunar surface. So I would like to mention that seriousness of this statement, that even if we manage to extract helium-3 from the lunar surface, our coming generations would have equal access to the resources which are being used currently. Also, they shouldn't run out of resources and they should not face necessity of finding the alternatives. I thank Survey organization for giving me chance to represent myself on this forum. And also, I wish everyone all the best at the end. And you can come and shake my poster at poster number 31. Thank you, everyone.
Thank you very much. Appreciate that. Okay, and now Ashley.
Can you hear me?
Yes.
Okay. Hello, everyone. My name is Ashley Clendenin. I'm a second-year grad student at Georgia Tech working towards my master's in mechanical engineering and my PhD in physics. I work on the REVEALS project, co-advised by Dr. Tom Orlando and Dr. Peter Letzenheiser. My research focuses on using solar irradiation to drive in situ resource utilization, or ISRU processes, primarily the thermal extraction of water and the thermochemical extraction of oxygen or other raw materials from the lunar regolith. The lunar environment is ideal for utilizing solar to drive ISRU because it has none of the problems that complicate the use of solar on the Earth, like attenuation due to the atmosphere or solar blocking due to clouds. This solar irradiation is even more efficient if we concentrate it using one of the three main concentrating technologies: trough systems, tower systems, or dish systems. To study the thermal or thermochemical extraction of materials from the lunar regolith, modeling and some preliminary experiments have been performed. One particularly interesting thing discovered in this research is that the thermal extraction of water, if not done carefully, could have harmful or even potentially fatal side effects for astronauts involved in the process. If this is something that you want to learn more about, you can come talk to me at my poster, which is Concentrated Solar-Driven In Situ Resource Utilization on the Moon, poster 19 in poster session 1, which is later this afternoon. Thank you for your time, and I hope to answer any questions you have at my poster.
Thank you, Ashley. Okay, and now Ryan, are you there?
Hi, everyone.
Great.
Hi, so my name is Ryan Galinkin. I'm going into my second year of graduate school over at the University of Central Florida. I'm currently working with Dr. Carrie Donaldson-Hanna, and we're mostly working on thermal infrared spectroscopy on mostly the lunar regolith. So it's quite interesting how the upper hundreds of microns is so important to these kinds of structures. A high porosity actually will affect how we view these incoming spectra. A lot of these things get changed, such as, gosh, I'm sorry. Getting put on the spot here is hard. But basically, you get a lot of different effects, such as the small particle size and the low gravity and surface charges, and you get a stacked up structure. And because of this, you get very different effects on the moon than you would on Earth. So when we look at the spectra of things in our lab on Earth, they don't look exactly as they would on the lunar surface or on asteroids in general. And because of this, it's very important to understand how this upper surface layer works. So currently in my research, we're trying to see if we can actually determine how the absolute porosity has effects on these measurements. So because of that, a lot of people have had trouble doing this, and they've mostly dealt with relative porosities. But I'm trying to come up with a relatively trivial way to determine the absolute porosity. My poster number is 37, and find that interesting and want to figure out how I'm doing that with a compound light microscope, please tune in.
All right, thank you, Ryan. All right, now we will move on to Marina. Are you there?
I am, and if you can hear me,
Yep,
awesome.
go ahead.
Okay, so my name is Marina Gemma. I'm a PhD candidate at Columbia University, but I do my research at the American Museum of Natural History in New York City. My dissertation work broadly focuses on the spectral and geochemical properties of meteorites, but today I'll be telling you a little bit about my project, which is poster number 30, titled Multidimensional Characterization of Mineral Abundance in Ordinary Chondrite Meteorites. So quantifying representative mineralogy in meteorites often involves destructive techniques which sacrifice petrographic context in your sample. And traditional methods such as point counting aren't ideal to use because of the fine-grained nature of meteoritic samples. So to determine characteristic mineralogy for the meteorites that I work with, I've combined the non-destructive methods of three-dimensional computed tomography with two-dimensional X-ray element mapping of sample surfaces to ensure that the higher resolution two-dimensional maps and the mineral abundances that I calculated from those are actually representative of the bulk sample. So I've analyzed 20 meteorites spanning all petrologic types across the 3 ordinary chondrite groups, and the detailed petrologic analysis of these meteorites can be combined with their laboratory spectra, which is work I've previously presented at the Exploration Science Forum to better characterize asteroids remotely. So if you'd like to learn more about this work, you can visit me later today at poster number 30. Thank you.
Wonderful. Thank you very much, Marina. And Kristen.
Hi, my name is Kristen Lusinger. I'm a 4th-year grad student at New Mexico State University, and I'm working with Dr. Nancy Chanover. I will be presenting a poster today introducing my project, which is modeling the vertical migration of water ice in seasonally shadowed regions. I actually grew up in a seasonally shadowed region up in Alaska, and so I was inspired to look at seasonally shadowed regions as a really great resource to understand vertical migration of water ice on the moon. We can use the regular disruptions to the sequestration process caused by the sunrises in the lunar summer in order to constrain the mixing rate during the time when the sequestration process was active. So if you want to learn more about my project, I would love for you to stop by. I'm at poster number 42, and I really look forward to hearing from you.
Okay, thank you. Pedro.
I'm here. Can you see me?
Yes, we can. Go ahead.
Okay,
Thank you.
perfect. Hey, everybody. My name is Pedro Montalvo, and I'm just going to briefly talk to you about the current research that I'm working on. I'm a PhD student from Auburn University, and I am co-advised by Dr. Toshi Hirabayashi and Dr. David King. Basically, our research explores regolith mixing depths by applying a numerical model that uses crater populations. And we can use that to map their distribution spatially in craters that host water ice, specifically in the lunar South Pole. So this becomes important because understanding such distribution and such distributions can let us know more about the thicknesses of how these deposits work, essentially, and could aid us potentially on future sampling techniques for future lunar missions. So my poster is number 31 in today's session. So if you got more questions, please stop by. I'll be happy to answer everything out. Thank you.
Okay, thank you, Pedro. All right, Gavin.
Oh, can you hear me?
I can hear you. I can't see you.
Okay, my camera seems to be acting weird, so I'm just gonna go ahead and talk and hope it fixes itself.
Okay.
Hi, my name's Gavin. I'm a PhD candidate with the Institute for Earth and Space Exploration at Western University in Canada. And I'm working with Dr. Catherine Nish and Dr. Gordon Zinsky, trying to understand more about lava flow, emplacement, and surface roughness on planetary bodies, particularly in the Moon and Mars. So on the Moon, lava flows is one of the best ways for us to try and understand past volcanic processes and interior magmatic processes. But unlike Earth, we still don't have a very large suite of data sets that allow us to look at the surface roughness of lava flows at different scales. So part of my research is to use terrestrial examples, which do have similar morphological properties to some lunar lava flows, in particular when you look at them through radar. So my poster, which is studying the lunar lava flow emplacement by quantifying the surface roughness of the Hollow Lava Flow field using synthetic aperture radar and LiDAR will be able to help us understand flow emplacement mechanics on the moon. So if you'd like to learn more about my work, my post is number 81, and I'll be presenting it today. Thank you.
Okay, thank you. And Michael, I think, is our last one.
Okay. Let's see, are you able to hear me okay?
Yes, we can.
Okay, awesome. All right, so hello everyone. My name is Michael Walker, and I'm a PhD student working with Jack Burns in the CU Boulder NEST team. And my research looks at the use of mixed and virtual reality technology for mediating and enhancing human-robot interactions. In terms of space exploration, this really means how can we leverage this technology to create new and improved interfaces for better facilitating surface telerobotic missions. These new technologies allow for enhancing and viewing collected data from these remote space robots in the full dimensionality of our world. Additionally, this technology presents a means of astronauts of the future to immersively teleoperate these robots, either from orbit or the safety of a space habitat or a surface habitat, and provide enhanced methods of robot control for manual teleoperation missions or manual error recovery for missions featuring robot autonomy. Currently, the disadvantages, such as operator fatigue or the required infrastructure, seen with these new interface technologies featuring head-mounted displays have not made a strong enough case yet for use in current space missions. However, it is my hope that with my work and work like it, will provide designs and justification of adoption of these new interface technologies for future space missions. And today I'll be presenting a poster during the first poster session. It'll be poster 21. And if you'd like to hear more or talk more about this topic, I'd love to see you there. And thank you for having me.
Thank you. Let's just make sure I was right. Okay, so I thank all of you. You did a great job. And I encourage all of the attendees to join them at the poster session today. And we will now move on to the ISRU and Viper mission session. Do we have Parvati and Ashley available?
Yes, we do.
All right, I will hand it over to you. Thank you, ladies.
All right, thanks, Christina. So the lightning talks are always a hard act to follow, but fortunately we have a very nice afternoon session of talks lined up for you all. So this is plenary session 3, which is titled ISRU and the Viper mission. My name's Parvati Prem, I'm at APL, and my co-chair today is Ashley Clendenin, who just gave a fantastic lightning talk and also has a much more interesting background than me. So watch out for that when Ashley comes online. Just a reminder to speakers, you will have 10 minutes for your talks plus 2 minutes for questions. We will interrupt briefly at 8 minutes to give you a warning that you have 2 minutes left. Reminder to everyone else, please have your microphones and videos off unless you're speaking. And if you have questions, go ahead, raise your hand on the Zoom window or type your questions in the chat, and we will try and call on you in the order that you raised your hand or typed. We have 6 talks today, followed by a mission update and then some time for discussion. So without further ado, I would like to invite our first speaker, who is Daniel Andrews. And Daniel's talk today is titled Viper, Pathfinding Lunar Resource Understanding. So Daniel, over to you whenever you're ready.
Very good. Can you hear me?
Loud and clear.
Very good. You see my slides?
We're seeing the PowerPoint window, so you might want to go into slideshow mode, but they look good either way. That's perfect.
Very good. Well, it's my pleasure to give everyone a briefing on Viper and where we sit right now. It's very exciting to hear the lightning round before this session, because I know some of what Viper will be discovering as a mission will help be a pathway for a number of the activities that we were just hearing about. So that's pretty cool. So here's how Viper fits in with the overall NASA swoosh chart, as we call it in-house, showing all the lunar activity plans associated with the human return to the moon. But you can see below how VIPER fits within that framework. So why VIPER? So VIPER represents direct science measurements of polar volatiles. You know, the LCROSS mission ground truth that the elevated hydrogen signals really were an indication of water, but now we need so much more. That was a big binary answer. But beyond that, we also need to understand the lateral and vertical distribution, as well as understanding the physical state and composition of those volatiles. Further, in doing so, we're hoping that we'll be able to actually build some lunar resource maps. I know the whole community will be building maps around the data that's there, which will be immensely useful for steering future missions, both state-sponsored missions, commercial missions, science missions, exploration missions. So great utility up and down the line there. In particular interest for exploration, we heard this from the administrator earlier this morning, was the ability to make use of the resources as well. And this idea of ore grade, which you may hear a little bit about from Tony Colapret, who I think is presenting next, is really important to understand the nature and the viability of being able to get at volatiles in different locations, in different circumstances. So VIPER is really hoping to help better define the nature of that. So where will VIPER explore? The science team and the broader community have identified 4 different ice stability regions. You have to break up the problem into some chunks, right? And then go and understand those pieces, those chunks. And so in this case, there's 4 different ice stability, thermal stability regions where ice could potentially exist that VIPER is turning its attention to. These are actually captured in our level 1 requirements as a mission. So the 4 types are called surface. In the first case, you can think of this as being, for example, permanently shadowed regions. That would be areas where ice could potentially be stable on the surface. So that could be frosts, could be other things, but most likely in permanently shadowed regions. And the question is how much and what's the nature of it. What the ice stability region we call shallow has to do with the first 50 centimeters below the surface. So the first half meter in there, the models would indicate that ice could be potentially stable there. That would be a different region. A third region would be what we cleverly call deep, which would be the next 50 centimeters, from 50 to 100 centimeters below the surface. And then finally, dry. And dry is where we basically expect that it's fully desiccated, that we don't expect anywhere in the first meter for there to be ice stable there. For example, we're probably going to land in a sunny area in the polar region for all the reasons that would make landing a little easier. We wouldn't expect to see ice there. It'll probably be in a dry region, but we're going to use that as a control reference as well in order to just fully characterize the nature of the polar region as it relates to volatiles. So let me touch on some of the driving science specs for VIPER. We're targeting around a mission duration of 100 days. For those of you who remember the Resource Prospector mission, VIPER standing on the shoulders of that work, but that was going to be a single lunar day. So maybe as much as 14 Earth days. The VIPER mission is trying to go for 100 plus days. So it's a considerably different mission problem that we're having to work against. We're carrying 3 spectrometers, neutron spectrometer, a near-infrared spectrometer, and a mass spectrometer. The mass spectrometer is a new entry for VIPER in comparison back to Resource Prospector. It actually was flying on Resource Prospector as part of the oven system, or variation of it. And so there is still connection back there, and a drill. You can see the drill depth is about 1 meter. From an engineering point of view, something the team is having to deal with here is the driving energy case for our system's capabilities was the permanently shadowed region working duration. So we would have a model of the activities we plan to do in a permanently shadowed region, would include one subsurface assay with the drill, and some amount of navigating going in, obstacle avoidance, that type of thing. And when we modeled that and looked at the energy, that was the driving case under Resource Prospector. In the case of Viper, the driving case has to do with its ability to stay warm in hibernation in the dark, because as I noted, we're going through multiple lunar days. And so that ends up being a big energy storage topic, which I'll talk a little bit about in a moment. We're nominally looking for a 12-mile distance travel. That's going to be driven very much by the surface plan. And that surface plan will be baselined out in CDR, which will be next calendar year. But just nominally, that's about what we're looking at. Performance specs of the surface segment, as we call it, which is the rover and the instruments. I won't go through all these, but you could read them yourself. About 430 kilograms. You can see the up-down links. We're using DSN. The dimensions there. Wheel diameter grew since the RP days, and for good reason, to be able to navigate these terrains more robustly. We're an explicit steer system. Each wheel can actually be steered separately, so you could crab walk, you could traditionally roll, but also with adjustable suspension. So that means that we can navigate through more challenging environments. We could actually adjust our own CG live through different articulations and so forth. So we figure in this area that's a largely unknown area, having that ability and capability to navigate some of the unknown is going to pay for itself on the mission. You can see waypoint driving. We're not teleop, but we're also not fully autonomous. Given that it's the moon, we have pretty quick communications, but not quick enough for teleop. And so we're doing waypoint driving, where we basically give commands, say 5 meters up ahead, and then the rover itself autonomously drives those 5 meters, and then we send the next command. So sort of carroting along the rover, and then of course, based on what we're learning as we go. So here's an image. It's probably one generation behind. We haven't updated the graphic here, but it's pretty darn close, of the surface segment. You can see the cameras, the nav cameras up top, up on the mast. That's also our
2 minutes
mast.
left, Daniel.
Thank you. And some lights up there. You can see the neutron spectrometer system hanging off the front, and the yellow MLI, which is basically our divining rod. Further prospecting evaluation instruments that I noted before, Nervus and M-Solo along the bottom. They're there to be able to look at the cuttings pile, but also just surficial conditions that are occurring there. So pretty capable rover. Quick hit on the science manifest. The Trident drill, of course, can drill down to 1 meter. I'll try to go quickly here. The neutron spectrometer is prospecting for hydrogen-rich materials seen effectively down 1 meter into the soil. So it's our divining rod as we're going through. Then in using that, we also can take measurements with our near-infrared spectrometer, which is good for superficial measurements. So it could look at things like frosts, but also evaluate excavated materials, as can M-Solo mass spectrometer, and including sublimation that will be occurring under the rover and as materials are brought up. Quick view of how we compare. Bottom right corner is where the latest version of Viper is sitting. You can see for a roving mission, it's pretty fast, 20 centimeters top speed. That's 4 times faster than any of the Mars rovers along the top. And U2, not quite comparable to the human-based rovers, but it gives you a relative feel. And again, we're electric only for our heating. So that's driving, of course, our battery load, our mass, and the whole energy system design. Quick little teaser video here of some of the swimming tests that we were doing up at the NASA Glenn slope facility. This is a capability that you get by having a more complex explicit steer adjustable suspension system. We have found in the testing that we've been doing that we could navigate areas that sink other rovers by using that type navigation approach, or locomotion approach. So it's working quite good. And then finally, I wanted to close with what many of you have heard, the Selection Eclipse project program of Astrobotic to be bringing us to the South Pole of the Moon in late 2023 on the Griffin lander. This is a video that Astrobotic has published. You see a representation of the Viper rover up on top. This plays very much like what we had kind of natively designed to in our own plans, for those of you who remember back in the Resource Prospector days. So this is a really good fit. It was a really good solution that was offered, and we're very happy to be joining them on the journey to the moon. And I think that's everything I have.
All right, thanks, Daniel. That was excellent, and you have a cute little rover there.
Thank you.
And we do have a minute for questions, and I see that Pam Clark asks in the chat, what do you anticipate surrounding environmental temperature variations to be, and how's that affecting the design of the dual spectrometers, which are sensitive to temperature?
So on the spectrometers, I think I'm going to defer to the next talk where Tony Colaprete, who is the project scientist, might be able to address those. I can tell you, though, that the extraordinary temperature differences that we expect to see as we go through these long shadows of a polar region are a key factor that we're bringing into our energy system design. And that includes our ability to retain heat when we need to retain it, and our ability to shed heat when we have to dump it through the radiators. And so it really does require quite an impressive system design. And especially when you think about it's all solar powered, right? So we don't have a nominal bias, heat bias coming from a plutonium source or something that we can work with there. So it's a key part of our energy system design.
All right, thanks, Daniel. And we do have one more question in the chat, but I'll let you look at that when you get off the Zoom. And next up, we have Dr. Project Scientist himself, Tony Colaprete, who will be talking to us about the Volatiles Investigating Polar Exploration Rover, VIPER mission, measurement goals and traverse planning. So Tony, over to you whenever you're ready.
Okay, can you hear me?
Yep, loud and clear, and
Excellent.
we can see your slides in...
I will go to the first slide and go to slideshow. I'll try to reduce this thing out of the way.
All right, looks good.
Excellent, thanks. And yeah, good introduction to this, Dan. What I'll try to focus on is the measurement requirements, the measurement kind of plans, what we intend to do, a little bit more on the instruments and the traversing. Kind of fill in some of the extra details of the mission from a science perspective. VIPER really has two basic science objectives, and these are pulled directly from the mission science level 1 requirements document preamble. And it's really to do two things. One is to characterize the physical distribution and state of polar water and volatiles. To understand its distribution, the cold traps and regolith, but also to work towards understanding the origin of these volatiles. This is much more of a science-driven goal compared to the next goal, which is understanding or providing the data necessary to evaluate a suite of ISRU architectures. And this is an ongoing activity within NASA and the commercial sector as to exactly what resources are at the poles of the moon and how might we utilize them. There's a range of different architectures one could choose from and work toward. And VIPER is trying to provide some critical additional data to help those technology development efforts. Diving a little bit more into then what it is that VIPER is going to do, and I know a lot of you have probably seen this before. It really is all about characterizing the distribution and the physical state of the volatiles at the poles. And many of you have probably seen this figure to the right. It comes from a standard used in terrestrial mineral reserve exploration by various entities, and it describes the process from going from inferred resources to a proven reserve. And we're really talking about working on the left-hand side of this, as we've obviously, as you all know, have very strong indications that there's volatiles and a range of forms, states, and distributions. So we need to increase our understanding and confidence in how they're distributed, so we can assess the probability of a reserve being available. And so to do that, there's really some critical observations that are needed, and they're highlighted here on the left. First, the distribution. We've said that. The concentration, including the lateral and vertical extent and variability. That's important. But what I call the physical state. So is it ice? Is it bound? Is it chemically bound? Is it adsorbed? Is it mixed uniformly or chunky or what? So it's something about the physical state of the volatiles as well. And also, and just as important, the context and correlation of those two factors with the environment. As I'll mention in a second, it's not enough to measure the concentration in one place or another without having any ability to correlate it with broader environmental factors. And this is how, of course, we do it on Earth. When we go looking for minerals, resources, we need to do the same thing on the moon. So that includes everything from accessibility, what's the overburden, the environment, sun shadow fraction, et cetera. So these are all very important things we need to measure to really help us understand this side of this figure. So it's a distribution, physical state, context, and correlation. And the level 1 requirements are shown here. These are our full level 1 full success requirements. There aren't many, which is very much intended to be. So I'm not going to go into the details here. They're displayed. You can read them, play back and pause. But they align exactly to what I just described. The first one has to do with the distribution and the physical state. Likewise, the second, the distribution in the vertical sense. And then the next two are really correlation and context, where it's like, okay, you're going to measure these things, and this is the kind of regions you need to measure them across, and also the other things you need to pay attention to while you're measuring the volatile concentrations. So these are our level 1 requirements that drive all of the mission level 2 and measurement plans. So an important thing to keep in mind is that VIPER, at its inception, going back to Resource Prospector and before that, is really borrowing heavily from what we do on Earth to develop resource models. It is really an applied science we are conducting here, not just a basic science, discovery type science. It is really applying what we know in terms of processes and techniques from resource identification on Earth to the moon. So it's kind of one of the real focused efforts ever to do this on a planetary body, I believe. And what we wanted to ultimately come out with from all this is a sense of the distribution and the ability to build what we call a resource model. So on Earth, terrestrial mining companies often build what we call mineral models. They allow you to predict the distribution of a mineral type and the likelihood and the confidence that you'll find it. And that's what they take to the bank to get the money to build the mine. We certainly want to do that on the moon, but we got a whole lot of data gaps that we have to fill to do that first before we go to the bank, so to speak. And part of that is not just making the measurements, but it's also building models in terms of the emplacement and retention. And this is the applied science aspect. It's just not prospecting and trying to get lucky. It's actually thinking about where you might find water, what's the likelihood, and testing those theories then with proper exploration techniques. So ultimately, as I mentioned, we'll have a resource model that comes out of this. There's already resource models being built. Kevin had one published recently, was really nice. And that's what's going to feed into all these things here. Dan mentioned this, so I won't spend too long on this. The correlation is important. And one thing we think important to correlate to is temperature. So we're trying to make our measurements in a systematic way such that we can correlate them with some kind of spatial proxy that we can measure from orbit. So for example, temperature at the surface, but also ice stability, temperature at depth. And this is what Dan described. This is an ice stability depth map that Matt Siegler has run for us at 20-meter resolution, we organize it into those 4 temperature proxies that Dan mentioned: dry, deep, shallow, and surface. And you can see that aligned here. This allows us to actually build up a organized campaign for making measurements and making sure we make them in a systematic way so we can build these larger regional maps. Within each one of these stability regions, which we call an ice stability region, ISR, we need to characterize it at scales that are really important. And I won't get into it here, I have in the past, but impact gardening, temperature variations at very small scales are likely to be very important to controlling the distribution of water in any one of these ice stability regions. So within each one of these, we need to measure the heterogeneity across it. And by that, I mean measuring at scales less than 5 meters. We need to understand how things vary within an ice stability region. We also need to make sufficient measurements that we can characterize the total yield of an ISR. So, while a single lander or 2 might measure individual patches, it may not have enough continuous measurements of an area to assess a larger area or volume. And then finally, we need to compare one ISR to another ISR. Thanks. Separated by some distance. So that's all key and has to happen in one of these ISRs. So all this boils down to this set of kind of high level 2, I would call them measurement requirements. And I won't run through them all here. I'll leave it here and you guys can look at it back. But what's key is VIPER is all about getting distance or odometry, a distance on the wheels. We need to cover a lot of area to actually get the kind of measurements we need to understand the distribution in each one of these ISR areas. This is the VIPER mission. Dan mentioned that, so I won't go into that. A little bit more on the instruments. Dan mentioned each of these. I won't go into any more detail here except to mention to Pam's question a bit. The near-infrared spectrometer also includes a 4-channel thermal radiometer, as Bethany described. It's really nice to have a simultaneous measurement of the infrared temperature as well as the near-infrared spectra, which goes out to 4 microns on this spectrometer as well. But I also will mention that we have a great set of navigation and hazard cameras that are going to provide fantastic geologic context, wonderful imagery, and also, of course, lights. We go into places, the illumination conditions at the poles are incredibly challenging and exciting. And so we really are developing some systems here to rove and maneuver within these shadowed regions, both in shadow, between shadows, and that's all going to provide excellent scientific data. We are also, of course, capturing all the other rover sensors for science, everything from motor currents to temperatures, et cetera, that can be used for science. Real quick, prospecting is when we're driving. All the instruments are on except the drill, of course, while driving. And this is a fundamental difference from Resource Prospector as well. We have the near-infrared spectrometer, the mass spectrometer, always looking under the rover, and the neutron spectrometer constantly measuring neutrons flux. We have constant measurement of surface temperatures as well from under the rover. So in this way, we can really build the density, the aerial density needed to actually get the uncertainties down and in terms of total water concentration in an area. When we do drill, as Dan mentioned, we have a 1 meter drill. It goes down and brings up samples in 10 centimeter bites, we call them, just 10 centimeter sections. Each section is observed simultaneously with the MSOLA, which is the mass spectrometer, and the near-infrared spectrometer fields of view. This gives us both the solid and the gaseous concentrations of a wide range of species. All these requirements I've described go into a range of science operation plans and documents. And this gets very detailed. I won't get into it in detail here, but this is just an example of some of the science activities that have to be built and then brought into a traverse planning tool, which is a very complex problem when you have both sun and COM constantly moving dynamically, you have slopes and everything else. But this is all being done now to build a series of traverses to evaluate both the rover design and the science operations. And this is one of my last slides here, just an example of a VIPER study traverse. This is a South Pole area north of the crater Nobile. This shows this white line is a traverse. Each one is approximately 1 lunar day. And we're running out to these red areas, which are PSR, ice stability regions. The green and yellow are the other ice stability regions of shallow and deep. And we run out there and conduct a range of science activities at what we call science stations. And this gives some of the statistics here in terms of total amount of measurements and whatnot. One thing I'll point out is this is overlaid on top of a 1 meter DEM from NAC images. So it's not stereo, it's made from shading. And it allows you to get actually fantastic NAC at much higher posting. And with that, this is my last slide here. So we've all seen the fantastic discovery that's been made over the last decade. And we're finally getting back to the surface with a range of missions, VIPER being one of several that really, I think, provides the next steps in our exploration and documenting of the resources potentially at the South Pole of the Moon. And with that, thank you.
All right, thanks, Tony. Great talk, and I see you have 4 questions in the chat window. In the interest of time, I'm gonna let you take a look at those in the chat when you get a chance, and otherwise we'll defer them towards the end. And just a reminder to everyone, if you're not speaking, go ahead and switch off your microphone and video. If you are speaking, of course, have your microphone, and if you're comfortable, your video turned on. All right, so our next speaker is Chris Zacny, and Chris is going to be talking to us about Trident, the regolith and ice drill for exploring new terrain for the VIPER rover. So Chris, whenever you're ready, and let's see, so we don't see you, but your slides look great.
Okay, thanks so much, and
now we see you.
Sound check.
Yep, sounds good.
Oh, good. Thank you. Thanks so much, and appreciate opportunity of talking about Trident drill for VIPER rover. I'd like to acknowledge my co-authors, Phil Chu, Vincent Vendiola, Jackie Quinn, and Julie Kleinhans. Jackie is at Kennedy, and Julie is currently at NASA Johnson. All right, so the goal of a Trident drill is to penetrate to 1 meter depth in lunar regolith, which could be dry, it could be ice cemented regolith. So it's specially designed to penetrate a variety of regolith, different water concentrations. The goal is to capture sort of samples in 10 centimeter bites and bring them to the surface for analysis by MSOLO and NERVAS. And what you see on top is essentially neutron spectrometer that's going to look for these hotspots. Once it finds a hotspot, at that point, rover will stop, the drill will be deployed, and the cuttings will be brought to the surface. The Trident drill is called essentially NASA baseline drill. It's not just designed for VIPER rover. It is designed to be also deployed on landers. So on the left-hand side, we have a rover VIPER. In the middle, we have a lander where drill is essentially stuck to the side of a lander. It's sort of the same configuration as Luna 24, which was a Russian sample return mission back in the 1970s. And on the right-hand side, we have boom or arm deployable drill from a side of a lander. So all these configurations are possible with pretty much very little modifications to the Trident drill. Most of you are familiar with the technology development, and most of you know it takes decades to do this. There is no difference here in terms of VIPER drill. It started back in 2005, so almost 15 years ago, as a CROOKS project. It was the very first rotopercussive drill that we have designed for a rover mission that would go to the moon. The project unfortunately got canceled a year later. Then we switched gears and we started developing a drilling system for Mars exploration. Very first drill was called Icebreaker. We tested it in Mars chambers as well as in Antarctic dry valleys. So pictured on the bottom left-hand side is me standing next to a colleague, Gail Paulson, in dry valleys. We drilled down to 2.5 meter depth in massive ice and ice cemented ground as a sort of analog to drilling on Mars. The drill was very heavy. It weighed 40 kilograms. So when we had the opportunity to put it on a CMU rover as part of a Life in Atacama or LITA mission project, we had to take out significant kgs to make it fit. So from 40 kilograms, we turned it down to around 15 kilograms without affecting its performance. It was a major investment in sort of engineering. For the next 2 years, we were driving around Atacama and deploying the drill pretty much fully autonomously. In 2014, we had the opportunity to turn the Martian drill into the lunar drill again as a part of a resource prospector. At that point, we changed actuators, we changed some of the subsystems, and we start focusing on developing what's becoming now a Viper drill, fully designed for Viper rover and for lunar terrains. This is an overview of a drill itself. On the left-hand side, it's an engineering test unit that has been extensively used in different formations. Right in the middle, you have a CAD design of the latest Trident drill. It has a rotary percussive drill head, and both rotation and percussion are decoupled, and that's extremely important because if you want to use different modes of penetration, you would, in some cases, you want to use rotary only, like retracting from a bottom of a hole, percussion to clean up the auger, rotary percussion when you cut into extremely hard competent materials. The auger is relatively, what you would find in a Home Depot, but it has different features to help with the sample retention and excavation. The bottom of the auger has the so-called bite section. It's essentially designed to capture material and retain it. Very often when you pull the auger out of the hole, material falls down to the bottom of the hole. We do not want them. We want the material to be brought to the surface. So that's why we have this bite section. As we're pulling the drill out, there is a rotary brush which forms a worm gear with the auger. Material is brushed off and dumped to form a cutting spile. On the right-hand side, we have two Z stages. The first one, called the deployment stage, lowers the drill to the ground and preloads the drill to the ground with 200 newtons. And then we have a feed stage that essentially drills down to meter depth. So by deploying the drill and pushing it against the ground, we're closing a forced loop. So the rover is not supposed to see any additional forces apart from an initial force applied by the deployment stage. The drill is using the bite sampling approach, where each bite is 10 centimeter in length. So we drill 10 centimeters, we pull out, we dump the cuttings so they can be viewed by NERVAS and MSOLO. We go back into the same hole, we drill another 10 centimeters, we pull out, dump the cuttings again, and so on. So bottom line is a shots taken from an actual vacuum chamber testing in NASA Glenn, showing how the pile of cuttings looks every 10 centimeters. So you go from very small to very big. Why are we doing it? The main advantage is that we preserve stratigraphy in these 10 centimeter bites. So every 10 centimeters, we have a data point that can be cross-correlated with measurements of NERVAS and the MSOLO. There's also a bunch of other additional benefits. Drilling torque is essentially, or final torque is a combination of the drilling torque required to break up the formation and the auger torque required to move the samples up. By going down every 10 centimeters and drilling first centimeter or two, the final torque that we actually reading out is essentially contributions from a drilling torque only. So we measure the strength of the material just by measuring the drilling torque. The bit also has a temperature. So every time we go down, we preload it and we measure the temperature, which is another benefit because the hole is empty. Something that we have investigated again in Antarctica, this graph shows that essentially doing binds versus no binds leads to higher penetration rates and lower power. The blue curve is the power that goes from around 80 to 100 watts all the way to 200 watts as we go down to 1 meter depth. But if we have binds, the power stays around 80 to 100 watts. Penetration rate drops as the auger chokes up, whereas with a bind sampling approach, penetration rate is extremely high. So that's some of the additional benefits. The drill has been tested thoroughly at NASA Glenn in something called VF13 or Vacuum Facility 13. Despite what the number says, 13, the tests have been actually very successful. We've done tests, drilling tests in over 30 drilling tests in a bunch of different sampling chambers with both M-Solo and Nervous. And what we found is that both data from M-Solo and Nervous correlates extremely well with water concentrations. And the tests have been done in as close to the lunar conditions as you can get in terms of temperature and vacuum and water concentration. So a lot of folks think drilling is just a drill, but I want to point out that drill can actually provide quite a number of useful information for science exploration. One of them is measuring the subsurface strength. The way to do this is you take the drill and you drill into materials of known strength. So this could be a 30 megapascal sandstone, 60 megapascal sandstone, and 72 megapascal sandstone. And you measure specific energy of drilling, which is essentially a combination of power and penetration rate. When you go to the moon, we drill, we measure specific energy from a drilling telemetry. We can extrapolate through this curve and get information about subsurface strength using this calibration curve. The drill can also be used to determine water concentration as a function of depth. This graph as a strength in megapascal versus water concentration versus temperature has been done experimentally in a laboratory setting. It essentially shows that as the water concentration increases, the strength of the material increases, and as the temperature decreases from 250 to 70 Kelvin, the strength of the material increases as well. So if we combine it with the data coming from the moon, this is the graph that you have seen in previous slide. We're using the data of around 35 MPa. We're using this graph to calibrate out to get water concentration. So in this case, the strength is around 35, 40 MPa. We draw the line across here and we hit the water concentration at the 77 Kelvin, and we get down to 12%. If our strength was, for example, 5 MPa, we would come in here and the water concentration would correlate to around 5 weight% water. So this is something we can use to cross-correlate data that comes from M-Solo, Nervous, and also neutron spectrometer. The water concentration, so the data that we get from in terms of water concentration is very good information, but what it could be in the physical state on the moon in two different forms. The first one is something that we are extremely familiar with in cold regions, so-called ice cemented ground. So all the soil is essentially held in a matrix of ice. It's extremely hard. But also what the same data would be provided if ice is essentially
Chris, you're
mixed.
close to 12 minutes.
Oh, I'm sorry. Okay, so I'm gonna finish it off. But the bottom line is Nervous Trident can also provide information about the concentration of material, whether it's ice cemented or ice mixed with soil grains. I'll skip the last two slides, and I'd like to acknowledge NASA and the VIPER team for funding, and the SBIR, ASTEP, ASTED, and PIDIP. Next step is PDR CDR that's going to happen in August of 2020, and the delivery of a drill happens towards the end of 2021. And apologize for going over time.
No worries. Thanks for a great talk.
Okay.
So we do have a lot of interesting questions in the chat, and hopefully we'll get to some of those in the discussion session or when you have a chance to look at the chat. And just going forward for the speakers, we will give you an 8-minute warning. We'll also do a 10-minute warning going forward, just so that we can keep track of time, because it is hard via this format.
Yeah,
But thanks,
apologize. I
Chris.
didn't actually hear your 8-minute warning.
Right, yeah, no worries. Totally fine. Not your fault. Okay, and I'm going to hand it over to my co-chair, Ashley, for the second half of the session.
Thanks. So our next talk is by Craig Hemel, who will be telling us about regolith materials for ISRU in vacuum conditions, effects of phase evolution, character, and composition of X-ray photoelectron spectroscopy, and in situ calorimetry.
Hello, everyone. Can you hear me okay?
Yes, we can't see you though. If you feel like you want to share your video, you can.
So today I'd like to share some research that we're doing at the University of Central Florida in collaboration between Dr. Steele in the Material Science and Engineering Department and Dr. Britt in the Physics Department, all under the Center for Lunar and Asteroid Surface Science. So in particular, in this study, we're looking at a unique asteroid.
Craig, sorry to interrupt. Your sound is cutting in and out a little bit.
Okay. I'll see about changing headphones here. Okay, if you could let me know if this is any better. So we're looking at.
A little bit better.
So we're looking at an asteroid regolith material. And in particular, we want to look at this material to focus on some of the engineering consequences of using this regolith material for ISRU. So in keeping with that, we want to use a material that has a crystal structure and a composition that is relevant to the asteroid regolith. And we want to explore properties that are important for engineering applications. So in this case, we'll be looking at antigerite, which is a serpentine structured material that's highly porous and has a low density. So this readily lends itself as a functional material because it can allow for catalysis with its open structure. It has a lot of surface sites that can react with certain materials. It can also take chemicals out of the environment in the same manner, and can also be used as an energy material because of the porous structure, allowing for charge transfer and sequestration of charged ions. So antigerite is a silicate, and a hydrated silicate that also contains magnesium and iron. So we want to take this material and we want to look at its temperature sensitivity. And in keeping with describing the material in outer space relevant conditions, we are going to test the material in an inert atmosphere, in air, and then under vacuum. So the first thing we did was look at the materials, the influence of particle size. So in doing this, we took an unsieved fraction of antigerite and compared it against sieved fractions of greater than 212 microns and less than 53. And in doing BET surface area measurements, we found there was a weak correlation between the particle size being the small fraction or the larger fraction, and attribute this to the high porosity of the material. So the porosity dominates the surface area rather than the actual nominal surface area. So we chose to use the smaller fraction because a lot of the applications in using this as a functional material relate to surface reaction. So we want to increase the amount of surface area, nominal surface area if we can. So in doing so, all our subsequent experiments involve grains with less than 53 micron. So here I have thermogravimetric analysis and differential scanning calorimetry up to 1,000 degrees in an inert atmosphere under nitrogen flow at 1 atmosphere versus under vacuum conditions. So there's 5 peaks labeled here, and this is all for antiquarite. Peak 1 is the loss of weakly absorbed water species. 2 is related to pore reconstruction. 3 is the beginning of a dehydration process, which will be most important for the endpoint material and use of the material in application. So that one at peak 3, we actually have formation of a hydrated phyllosilicate and then a fraction of olivine. And then in peak 4, we have complete dehydration, and 5 is conversion completely to olivine materials. So you can see in the vacuum environment relative to the inert atmosphere, peak 3 is more comparable to peak 5 in the vacuum environment relative to inert. In the inert environment, peak 5 is very much higher. So we would say that under vacuum conditions, we have more use of that hydrated material or more evolution of these phases, and it's not available for transformation in peak 5. So this is important for temperature processing of the material, and also further suggests this the necessity of the space-similar environments. Okay, so in doing X-ray diffraction studies on the materials in each of these environments up at different temperatures, we can look at the actual phase composition as it changes temperature. And so a lot of these, it supports the description of above 600 degrees. We have loss of antiquarite and formation of forsterite and enstatite. And so that's represented here, but also in the red highlighted region, we have an increased peak under vacuum relative to the inert environment. This is really the most significant change that we can see from the XRD study, and suggests either that it's an iron-rich phayolite phase, or it could also be a greater production of forsterite over enstatite, which is reasonable considering in the DSC environment, we saw a large peak 3, where we have that initial formation of a hydrous material and decomposition of antiquarite. So we would say that the enstatite, which has greater oxygen content, would be less favorable to be formed in this vacuum environment because it's consumed earlier in the reaction. Okay. So now that we have these impressions of what's going on physically and what phases are formed, we want to look at the chemical composition to really describe what's happening at each of these points in processing material. So in doing so, we did X-ray photoelectron spectroscopy, and we looked at specifically spectra for magnesium, iron, silicon, and oxygen, and looked at the relative amounts of each of these, as well as probing the chemical states for certain material, certain of the elements. So first here, this is a survey scan that just shows the entire range, the inclusion of all of the elements. And in comparing the stoichiometry of our material versus an idealized material, we see it's comparable stoichiometry. So any changes that we find experimentally, we can relate to the process. So here we have a direct comparison among a control unheated material heated to 1,000 degrees in air, nitrogen, or vacuum, and we see the stoichiometric implications of each of these. And so the real takeaway, with heating, there's greater oxygenation in air, nitrogen, or vacuum, although we see for the vacuum material a decrease in oxygen and of the metals composing the material. So something to consider here is that X-ray photoelectron spectroscopy is a surface characterization method. So in looking at that, we know from the DSC and thermogravimetric analysis measurements, the overall weight loss that happens with heating to 1,000 degrees is the same, independent of the heating environment. So we know that the components are not being lost, they're reassembling for the most part, or are lost in the same proportions. So when we have this change in stoichiometry, it suggests that it's formation of new phases of unique character. So now we've broken down each element and taken a spectrum from each of these. In considering the oxygen, there are several peaks attributed to it, and it's specific to the bonding chemical environment surrounding the material. And we see that they're fairly comparable for nitrogen and air, but in the vacuum, we see a clear distinction where there's a greater or a more comparable amount of the hydrated species and magnesium oxide phase. So we look into the magnesium spectrum, iron later on. So here, the graphs show comparable distribution of magnesium oxide and of metallic magnesium. So we think, based on the previous measurements, that there's not much of a change in the oxidation of magnesium relative to the other components. So moving to iron now, we look at, has a more complicated spectra because of its increased number of redox states available to it. And if you look at the highlighted peaks here, related to 2+ and 3+ redox state iron, you can see that under vacuum condition, the 3+ state is much more highly favored compared to the 2+. So it's more oxidized, more oxygen directly interfacing with the iron. And based on the stoichiometry that we saw from the survey spectra, we would think that iron is directly interacting with oxygen, perhaps at a subsurface location. So the surface is silicon rich when it's been heated, although the oxygen that was in the material and distributed is now more coordinated with iron and moved below the surface.
It's been 10 minutes.
In conclusion, and for the future, the study shows the value in measuring or evaluating materials in environments that are more reflective of how they would be in our space, and especially in considering how the materials change as functional, so how their surface changes even if the phase composition is similar in related materials. We also saw that there were specifically changes in the distribution of enstatite or forsterite, and then also the oxidation states of iron. So in continuing this research, we want to look at stronger vacuum environments and see if there's a trend in this phenomenon with increasing vacuum, just where the processes end up on a phase diagram. And also the kinetic considerations of the thermal treatment, how if the distribution of phases will change with increased time at each temperature, and then also the functional implications of the oxygen loss at the surface. So if we wanted to form our own phase, we could, of a relevant material, maybe for catalysis, we're thinking to do maybe a metal oxide nanoparticle synthesis on this antigerite substrate. And that could be accomplished by the dehydration of the surface and the oxidation of the metal salts to produce nanophases and a functional material. Okay.
All right, thank you for an excellent talk. In the interest of time, we are going to move directly to our next talk. So if you have any questions for Craig, you can ask them in the discussion section later. So our next talk is by Garrett Schieber on the experimental evaluation of heat transfer and mass transfer for the development of lunar thermal H2O mining.
All right. Sound check, can you hear me?
Yes.
Okay. Great. Give me 1 second. All right. So hi, again, my name is Garrett Schieber. I'm a PhD candidate at Georgia Tech, and I'm a student on Reveals, and today I'll be presenting part of my PhD work. So The focus of my talk is on ice mining, but before we talk about mining the ice, we have to understand the sources of ice on the moon. The earlier talks gave an excellent introduction to how we can characterize and really get the ground truth for this ice. But to give you a quick overview, LCROSS indicated the presence of ice in permanently shadowed regions. And recently, a very good paper came out of class, which indicated, tried to go over a couple key questions. And so we have to know the concentration, we have to know the distribution, and then finally the physical state or the morphology of the ice is needed to be known. And so that recent modeling out of class helped answer a couple questions in terms of concentration and distribution within the regolith. And so their conclusions were just regolith in permanently shadowed regions may contain more than 5 to 8% of water ice, and its maximum will be at or below about 50 centimeters of depth. And that also impact gardening may lead to homogeneity. However, ultimately ground truth is needed because we still don't know the exact morphology of the ice within the regolith. Is it particles? Is it a coating on the regolith particles? Is it a sheet? And there's many other possibilities. However, and I don't think this is mentioned a lot, the ice will fill a significant volume, especially if it is at 5 to 8%. And so I prepared a quick demonstration to the right with the average surface porosity of about 0.5. If that regolith is filled with 5 to 8% of ice, the porosity goes down 10% as that ice fills a further 10% of that void space. And that has implications for the design of thermal mining. Now, in terms of mining technologies, when one hears the word mining, they think excavation. And however, I think that excavation will require extensive infrastructure. And just to picture that, I see the Lunabotics mining competition. And so if you can see my mouse, here's a promotional image for the Lunabotics mining competition. And you can see that their concept even has an astronaut supporting this lunar mining outpost. And so I believe that for kind of the first generation mining outpost, it's going to be helpful to propose an alternative technology that does not require excavation. And that alternative is thermal mining. And so thermal mining, again, does not require excavation and is fairly simple as essentially regolith and ice are heated. In this case, I'm showing concentrated irradiation as the heat source, and that would be reflected into these permanently shadowed regions. And that heating causes ice to sublimate. Sublimation is, of course, the phase transition from solid to vapor. And that vapor then sublimates out of the regolith and then is funneled to a cold capture tank shown here on the right. And the funneling occurs as there is a semi-transparent capture tent that doesn't allow volatiles to escape into space, but also allows that concentrated radiation to strike the surface of the cold icy regolith. And so even though it's a fairly simple design, there are still engineering challenges associated with design of thermal mining systems. And so the important physics in play here are heat and mass transfer. And so accurate models are needed to assess both heat and mass transfer to assess the feasibility and optimize the design of thermal mining systems. And so porous media, and this is complicated by the fact that porous media are inherently random and difficult to model. And so experimental study is needed. I should provide an image of JSC1A just so we can show how inherently random porous media are. And so now the first aspect of the physics I would like to talk about is the mass transfer, and the mass transfer specifically of the volatiles within the pore structure of the regolith. And so mass transfer within a porous media can be modeled with the advection diffusion model shown here, where the first term is the advection term and the second term is the diffusion term, where at low pressure, diffusion is dominant. However, because we want to be sublimating this stuff, higher pressures may be more relevant. And in that, advection can significantly enhance transport. And furthermore, the tight pore space can lead to moderate high pressures, at least locally. And so both, in addition, both of these advection and diffusion rely on experimentally determined coefficients. And so in a previous work, I've determined experimental coefficients used in transport. And just to give a quick overview, I'd like to draw your attention to the plot on the right. On the y-axis, we can think of this as the transport coefficient, where a higher transport coefficient corresponds to less resistance to flow, and a lower transport coefficient corresponds to less resistance to flow. And so the Knudsen number, or more resistance flow, excuse me. And then on the x-axis, we have the Knudsen number, where the Knudsen number is the ratio of the mean free path to the wall diameter. And another way we can think about this is essentially the ratio of the distance between molecules to the distance between particles within your porous media. And so at very low pressures, the distance between molecules is very large. And so a high Knudsen number corresponds to very low pressures. And so what we see is that at the highest Knudsen numbers, we have very limited transport. And as we move to higher and higher pressures, the advection kicks on and enhances our transport. And so these results are shown for nitrogen. And nitrogen was the first step towards moving towards the more complex H2O, because both nitrogen and H2O will both have advection and diffusion. In addition, terms such as permeability are gas independent. And so H2O experiments are currently in progress to measure the gas dependent slip and additional H2O specific phenomena. Unfortunately, this aspect of the project was delayed due to COVID. So moving on to heat transfer. Heat transfer in thermal mining can occur in the following pathways. A conduction between regolith particles, radiative heat transfer within the packed bed, heat transfer through any gases in the interstitial pores, and then finally conduction through the ice itself within this icy regolith. And so all of these mechanisms for heat transfer have different orders of magnitude in terms of how much they contribute to the overall effective conductivity, heat conductivity of this packed bed of icy regolith. And the first one and the lowest one is the pure conduction through the regolith particles themselves is fairly limited, on the order of 10 to the minus 3. And then the radiative exchange, when normalized to the temperature gradient, we call this the effective radiative conductivity, can enhance this conductivity all the way up to about 10 to the minus 2. And then depending on the pressure of the gas within the pores, conductivity can be enhanced all the way up to 10 to the minus 1. However, for the majority of the cases, it's on the order, it's much, much lower, as with no gas, you can't have conduction through that gas. And then finally, the most interesting mechanism, I believe, is the conduction through the ice. And that's because ice has conductivity on the order of 1. And in fact, ice may form bridges between particles, enhancing heat transfer into the regolith, and
2 minutes.
essentially providing a pathway for that heat. And so to kind of measure this, direct temperature measurements coupled to a solar simulator to kind of demonstrate this thermal mining are envisioned. I was hoping to get this done within the scope of my PhD, but I think due to COVID, I will have to nix this aspect. But hopefully another student can come along and continue this project. However, the work situation has led me to develop a model for thermal mining. And so to give a quick overview of this model, we have regolith, a packed bed of regolith, where I'm modeling right now, or just providing a snapshot up to 75 centimeters, where at around 50 centimeters and beyond is where we're really going to start seeing high concentrations of water ice. And I provide a solar heat input of 10,000 watts per meter squared, and a time from start in this transient model of 6 hours. And the results of this model are shown here, where on the top x-axis, we have the temperature. And so at the surface, we get a temperature of 550 Kelvin. And then we have a significant temperature drop all the way down to about 225 Kelvin, in which the temperature levels off. And then on the bottom x-axis is the density of ice in each cell, or the concentration of ice in kilograms per meter cubed. And so we see that we've completely desiccated the top 6 centimeters of regolith, but then we see a small spike in ice concentration, and then it levels off to the value in which I initialized it at. And so basically what's happening here is, as we desiccate this edge layer of regolith, we remove the heat pathway as in the ice. And so then we rely we rely solely on the radiative conductivity and maybe any conductivity contributions of the gas, which is fairly limited. And this leads to a significant thermal resistance, essentially meaning our heat cannot penetrate very effectively to the maximum. Now, I wish I could get into this more. However, this model details and engineering solutions to try to enhance this heat transfer and hopefully get around to this 50 centimeters depth are discussed in upcoming work that I'm developing. So in conclusion, ground truth and prospecting are needed to determine the ice content, the distribution of the ice, and the morphology. Further experimental study is necessary to refine both the models I presented for heat and mass transfer. And thermal mining is a promising option. However, like I showed in the last slide, engineering solutions need to be developed to enhance the heat transfer into regolith. Right. And that's all. Thank you.
Thank you, Garrett. So we have 2 questions in the chat, and I think we have time probably for one of them, and the other can wait till the discussion section. So Caitlin Arendt says, for your H2 experiments, at what temperatures are you working under?
For, I'm working at, okay, so we're talking over here. Those experiments, I'm working at a higher temperature. Because the thermal mining process is proposed to take place at higher temperature. And another reason too is a practicality reason. As I try to measure this gas, I don't want condensation or deposition in my vacuum chamber. And so I'm right now measuring at about 100 degrees Celsius or 373 Kelvin. So.
All right, thank you, Garrett. So we will move on to our next talk. And if you have more questions for Garrett, you can bring them up in the discussion section. So our next talk is by Clive Neal on how is the Artemis Space Camp sustainable?
Clive, you are muted right now?
Yeah. Still can't hear you, Clive.
I see that your microphone is unmuted, but we cannot hear you.
Okay.
I think I heard you there for a moment.
Did you hear me now?
Yes.
Yes.
Okay, so I'll take the headphones off and go back to old school. So I want to talk a little bit about the Artemis Base Camp and the Artemis rollout that we have that was just came out from NASA, and I put the URL at the top there. Of course, it's one of those that is easily memorized, but it'll be on the on the slides when they go up on the website. But one thing to look at here is the idea that we have this sustainable architecture, and I've highlighted a piece from this document. In placing and building the infrastructure, systems, and robotic missions that can enable a sustained lunar surface presence. And I've been trying to understand how that is going to be sustained, and that's why the questions I've been asking throughout today, especially this morning, I thought were pretty important to try and get a handle on this, because it's important for science endeavors as well as many other things. And Jake and Ben and Sarah gave presentations about the NASA perspective on this early today, about how the science impact of Artemis is going to be rather impressive. However, if we look at this document, there's no date given for the establishment of our base camp, and the administrator was quite pointed about having a date to be able to drive his budget as best as he can. But there's very few details on how sustainability of lunar exploration and development will actually occur. There is no definition, so there's no real pathway for longevity. But if we look at how human lunar exploration can be sustained, and I've looked a lot at Apollo, and I've looked a lot at the failed other attempts to go back to the moon, and we need long-term political support and public funding, long-term public support and international buy-in and partnerships, cooperation, not competition, because Apollo barely lasted 3 years before it was cut due to the fact that it was done in a spirit of competition. And once the competition had been sorted, then there was no reason to keep going. So, and I think maybe the most important thing is that this has to show that the Artemis has benefits back here on Earth. And I think this is the most important thing to focus on here, because the benefits that can be demonstrated to come back to this planet will facilitate government funding and public support and international partnerships and cooperation. So if we take a look at the return on the government investment that's necessary, there are a number of tangible things we can point at that actually happened during Apollo, and that was the renaissance in STEM education. Jobs, expansion of old and development of new companies and industries, technological advances, medical breakthroughs, and other opportunities that are heretofore sort of thought of, but there are others that haven't been thought of yet that inquiring minds may want to know. So I think that there is important opportunity here, and these nuggets of hope, as I've called them, are sort of scattered within this document. And I just want to point out a few here because, yes, on page 9, it does say we will develop new technologies, going to advance industry and discover new resources that will help grow the economy. So we have a commercial on-ramp in defining new technology areas now and fostering their development. And it was very pointed that Rachel Klima gave a talk about the Lunar Surface Innovation Initiative and through STMD and the consortium that's being run through APL. This is a great start to showing a return on investment. And some of these technologies could be for cold tech, getting into the PSRs. We tend to gloss over the fact that these are some of the coldest places in the solar system. And so technology needs to develop to be able to actually utilize any materials that are in there. Cryogenic storage and transportation is another issue. I called it the hydrogen problem because hydrogen boils off at very low temperatures. And any technological advances here can have important implications for hydrogen fuel cells and the hydrogen economy back down on this planet. And then engineering, landing sites and high traffic operational sites, i.e. dust mitigation, and then robustness of systems. When we ran the Lunar ISRU workshop in last year, we heard loud and clear from the mining industry is that mining is hard on systems. And trying to maintain them even on Earth is difficult. So robustness of systems then becomes essential if we're actually going to do any large-scale movement of regolith, for example, or even thermal mining, because I still think you're going to have to take off that insulating layer somehow at a regular basis of regolith once it's been desiccated. So other nuggets of hope. Is that just because we're going to Mars doesn't mean to say we're going to abandon the moon. Good to hear the administrator talk about that. It's Moon and Mars for once, and we can actually go out into the solar system together. And it talks about CLPS being important here. But I put up the CLPS companies. But what is the evolution path for CLPS, and how is this entwined with establishing and evolving the Artemis Base Camp? Because if you're not growing and evolving, you're basically dying. So we need to think about this now and put those steps in place to actually grow this, because it will become important for science development. It will become important for sustained human presence on the moon. And it will become important for developing the economy that will actually promote sustainability. And then finally, talking about the ISRU will enable the production of fuel, water, and oxygen from local materials. And again, it says in the document that this will enable sustainable surface operations with decreasing supply needs from Earth. So we have another commercial on-ramp here, and we can actually estimate what the demand would be for life support consumables. You can see here that oxygen and water, both in kilograms, and you can see that this may not be the driver in terms of getting commercial involvement. It may not be viable for commercial companies to be involved in supplying these sorts of needs. But again, the Artemis Base Camp is slated to have a transportation system. The human lunar landers are refuelable, at least the descent stages are going to be refuelable. So we have an opportunity here to start expanding the propellant side of the demand. And again, we actually now develop another commercial on-ramp. But critical in this is reusable engine development. And that type of engine, whether it's methane or hydrogen being mixed with oxygen, could actually drive the demand for the resources. And you can see in the graph on the table on the right, you've got manufacturable on the moon. Yes, you can manufacture methane, but you need a carbon source to be able to do that. Whereas we know that there's water on the moon, and that this is certainly a potential fuel source, because water, as we look at our solar system, and the more that we learn, is potentially the oil of our solar system as humans move out ever beyond the Earth-Moon system. So, just to wrap things up, we need to understand, and we've heard this a few times, if resources are reserves. But I want to emphasize the point here is that over in this diagram on the right, economic is part of definition of reserves. So we need to make sure that if we're going to get reserves, or understand if there are reserves there, what is the economic cost of extracting them? So a resource prospecting campaign is certainly essential and needed. And VIPER, I think this is one of the most critical missions NASA has ever done, because it represents a good start to a prospecting campaign. Very encouraged by the talks we've heard about VIPER today. And I think this deserves full community support, because if we look at the types of data that we're going to get out of VIPER, they are going to inform science, exploration, as well as commercial markets. And I think that it's important that we don't stovepipe this as a science mission. It is a space exploration mission that is going to inform science, exploration, and commercial entities to derive business plans. So, final slide, we need to show the return on the government or taxpayer investment. And we can do that through, it's the best way to make Artemis Base Camp sustainable. Immediate need is to prove lunar resources are reserves. And we need to sort of establish markets to close that potential business plan. So how much is NASA and other space agencies willing to pay for those consumables? And then future growth and evolution of the initial base camp will be critical, I think, for sustainability, because it will increase demand and interest as we continue to move forward. So this evolution plan becomes very important for science, exploration, and a sustainable space program through a creation of jobs. Thank you very much.
Thank you. So we have a few questions in the chat. The first is from Mark Cialtola. Why would the moon hopper need to be controlled by the Artemis base? Why not from the Gateway or even Earth?
It's could be controlled from anywhere. The point is that it's a intra-lunar transportation facility that is reusable and can be refueled by, it puts a demand on the need for local resources to able to do that.
And then another question by Annabelle Peltzer. Because the moon has significantly less gravity compared to Earth, is generating artificial gravity for an astronaut on longer missions a possibility, or is something like that at all in discussion? How will we prevent bone loss?
Great question. We know a lot about microgravity and how the skeleton dissolves, and we know 1G, the skeleton tends to stand up to it, but we don't have the database to look at what happens to the gravity at 1/6G. Is that enough to prevent bone loss? We don't know. But this is something that I think is critical to have a sustained, maybe even permanent human presence on the moon to understand this, especially if we're going to get humans to and from Mars and don't kill them in the process.
All right, so that's all the time we have for questions now. If you have more questions for Clive, you can ask them during the discussion. And I believe it's over to Christina Gibbs now.
Yes, thank you very much. Thanks, Ashley. Thank you, Parvati. We have one more talk before the poster session, and I just want to quickly just say that, you know, international partnership, you heard it this morning, is a major part of SERVI, and we have seen a lot of collaborations with international partners throughout the years with SERVI. 17% of our publications since the inception of SERVI itself are with international collaborations. And so we were very excited. Many of you may have been there last year at the signing with Japan and SERVI and NASA. Dr. Lori Glaze partook in that, along with Dr. Masaki Fujimoto, who's going to speak to us now about Hayabusa 2 and the MMX missions. So please welcome him with me, and then we'll jump into the posters and/or discussion session after that. Masaki, are you here? No?
Yes, I hope we can see my slide.
We can see your slides and we can hear you, so take it away.
Okay, good, thank you. So Hayabusa 2 is an asteroid sample return mission. It has been exploring one of the primordial asteroid Ryugu. It has made 2 touchdowns on its surface, and the second touchdown was after an impact experiment that excavated the subsurface samples, so that we think we got some subsurface samples sampled in the second touchdown. Departure from Ryugu was in November last year, and so it's heading towards Earth, returning to Earth. And landing in Australia will happen in December this year. So it's about half a year from now. So I think it's the right time to talk about how we will handle the samples after we recover the capsule from the desert in Australia. So that's what I'm going to talk about today. So after recovering the re-entry sample, what we will do is to, of course, secure the safety first, like removing the battery and the electronic boxes, and then do some cleaning. And then the first thing we do in Australia is to sample gas from inside a container. Well, Ryugu is a primordial asteroid, so there's some expectation that the gas may be inside a container, and we make sure that we get them before losing them during the transport back to Japan. So we're gonna build this kind of quick look facility at the site, and then get the gas samples if anything is available. And then by a private jet, we will transfer the sample capsule back to Japan, and then bring it to our curation facility in Japan, in the suburbs of Tokyo. And then what we will do is to remove all those, all those things that's surrounding the core part of the container. And then the core part of the container will be transferred to the clean chamber at the curation facility. So this photo shows the machine. This is the machine with which we will curate the samples, with which we will get the samples out of the sample container. First, we will open the sample container in vacuum, and then recover and curate some of the samples in vacuum forever. But that's not an easy process. So instead of having all of them handled in vacuum, under vacuum, we will move most of the samples to a chamber under purified nitrogen atmosphere. And then under those purified nitrogen atmosphere, we will manipulate samples of various sizes. And what this slide is showing is that a millimeter size sample, a millimeter size particle is like a ballpark number to show what the sample size will look like for this mission. And the total amount of sample is expected to be about 1 gram-ish, but that's something we don't know yet. We'll have to see until when we open the sample container. So this is a plan. December, we will recover the capsule back from Australia, and then the curation starts. And in about a half a year, we should be ready to do the initial analysis or preliminary examination, which will last for about a year. And then around 2 years from now, we should know that the result from the initial analysis should be able to tell us the high science potential of Ryugu samples returned by HABS-2. So initial samples, you have to wait about a year until we know we have the showcase for the science potential of the samples that will consume about 50% of the returned samples. But then in June 2022, 2 years from now on, the science opportunity will be open to the international communities. We will issue the first international AO for sample analysis, and then I think, you know, at some frequency, AO will be issued on and on and on, so that you know, our friends all over the world can have the opportunity to analyze the samples. So what I have to tell you now is that we already have a very high expectation of the samples, of the high science potential of the samples, because remote sensing observations already tell that the Ryugu sample seems to be much darker and looks very flaky, if I'm using the right word, flaky, which means that it's just unlike any meteorite that's available on the ground now. So the expectation here is that we're gonna analyze the sample that no one has ever analyzed before. And I think in 2 years from now, that kind of science opportunity will be available for everybody on this planet. But at this stage, you might be wondering that it's December that we will get the samples back. We will get the return of the sample capsule back. But before talking about that capsule recovery operation, I'd like to tell you the comparison between the HABS first and this HABS-2, the second one. So this photograph shows you the capsule reentry for the HABS first, which happened about 10 years from now. You can see the capsule returning, and you can see that the spacecraft itself is burning in the air. But for HABS-2, this is the plan. It's going to be different. So you can see the capsule returning back to Australia, but the spacecraft itself will fly by Earth. It will not dive into the atmosphere of Earth, so it will not burn out in the air, but instead it will make a flyby, and then the plan is to have an extended mission. So it's going to be a long mission though, but still the plan is to make it rendezvous with small 10-meter size near-Earth asteroid. So the extended mission will have a planetary defense flavor. And because of this small target asteroid is a fast spinner, it's going to bring us some new science as well. So extended mission, it will take some time, like 10 years until we get to the new target. But once we get to the new target, I think HABS-2 will accomplish its second objectives of its life. And then, but again, as I told you, this capsule recovery operation will take place in December. And who knows if the pandemic will be over by then. Well, I think not many people believe that it will be over by then, but in any case, we have to do this. If we don't do this, we'll just miss it. So we have to do this. And by itself, it's a lot of work, but under this COVID-19 pandemic, there's a lot more work we have to go through, but we are determined to do so. Like we will charter a flight to send the team into Australia. We will accept the 14 days quarantine before we can start anything related to the operation. The team will be composed of 80 people, and 80 people quarantine for 14 days seems like a headache, but still we are ready to accept it. And then we have to do all the operation under the social distancing. And that's another headache, but we're determined to do so. And we just have to do this. And I think we can do this because we already have a good plan to do this under this weird circumstance. So that's about HABS-2. And then I want to tell you something about another sample return mission, MMX. It's a Phobos sample return mission. We had an official approval in February this year, so that's very good. And the expected amount of sample from Phobos will be like 10 gram-ish. So it's an order of magnitude larger than HABS-2. So, well, the first target science is to understand the origin of Phobos. So based on that, on this science theme, people have thought about what they should do with the sample. So this is like the chart showing how they have thought through, assuming that this is a small body sample return mission. But on the other hand, because ejecta from Martian surface could have been showering the surface of Phobos for a long time, throughout the history of Mars, we can expect to collect Martian samples from the surface of Phobos. So this MMX mission has a flavor of poor Mars sample return mission. So this is another perspective that let the sample scientists think about what this mission should be and how they should handle the samples after the samples been returned.
Masaki, 2 minutes, please.
Yes, and indeed, we have two sampling systems. One is a Cora that will access fresh subsurface materials provided from Japan. And another sampler is a pneumatic sampler that will mainly collect samples from the surface of Phobos. And if you think about the Martian samples, the pneumatic sampler, the sampler from the US, may collect more Martian samples than the Japanese sampler. So, well, it's good to have friends so that we can be, we can meet the goal of two purposes. I mean, two perspectives. So anyway, oh, by the way, then you might wonder, what about the planetary protection issue? We have gone through the argument, and then the MMX mission is categorized as unrestricted Earth return mission, in case you are interested. And then, so the planning is going on. Planning of sample handling from MMX is moving on. And I think the scientists are really enjoying the discussion. But there will be, for sure, benefit a lot from experience with HABS-2 samples. And that campaign will start in half a year from now. So thank you very much.
Thank you very much. We have time for a question, and then we can move into the discussion session. I'm not seeing any hands raised. And I did see some, here's one. Question from Camilo. Why will samples be handled in purified N2? What are the pros and cons versus other gases, e.g. inert or vacuum? Masaki, did you hear that?
Yes.
Okay. Yep.
On the other hand, because organic chemistry can be one of the pillars of HABS-2 sample analysis, some people worry about the isotopic, there might be some contamination to the isotopic analysis. So that's one thing we really have to be careful in doing the sample analysis.
Okay, it did cut out for a moment, but I think maybe you could talk with her or him again. Pascal, why don't you go ahead and unmute and you can ask your question, and then we can finish up with this main part of the session.
Hello, Masaki. Do you hear me, everybody?
Yes, thank you.
Yeah, thank you for the talk. In fact, every talk today. But Any update on MMX flyby plans at Deimos?
Oh, we're not there yet. I'm sorry. Because now we're making the detailed design of the spacecraft and the, mass resources and the fuel allocation. There's going to be a trade-off between how much you want to spend your resources in like low altitude orbiting around Phobos versus flyby of the, more detailed flyby of Deimos. So we're not there yet, but well, the short answer is that we're not there yet.
Okay, so is this something you might decide only after or once you are at Phobos?
I think so. I have to ask the project manager for details, but they're really focusing on the low altitude campaign around Phobos now.
Yeah, of course. All right, thank you.
Okay, so if everyone who would panel and Dr. Fujimoto could stay here in this room, that would be great. If it's time for you to move to the poster session, you can go to the poster website for Survey, the NESF 2020 website, and you can click on to visit poster, and from there you can get to the Zoom links. They should all be active. We are encouraging you to visit the students first. We are encouraging you to visit as many posters as you would like. And with that, I will also say that we are going to be doing a survey at the end. I think Greg mentioned this morning, but we would like your feedback on how this is going. We are trying some new things, and so we very much do want your feedback. So you can write to me or you can submit the survey or both. And with that, I'll turn it back to Parvati and to Ashley and let you guys run the discussion and leave it at that for the day, and thank everybody.
All right, thanks, Christina. So Ashley, I know, actually has a poster herself, so she's going to run on down to her very exciting poster. And I don't want to keep everyone too long because the posters really are fantastic and I want you to have time to look at those. I do have, so I've been trying to keep track of questions that weren't answered. The speakers have done a great job of answering questions in the chat, and I see people have been answering each other's questions, so that's fantastic. But I do have 4 questions on my list, and then we'll see if there's anything else that we didn't quite get to. I want to make sure we don't skip those. So the first question is for Garrett Schieber. And this one was from Kirby Runyon. So Kirby asks, Garrett, with the deep regolith being colder than the interior of the thermal tent near the surface, are you confident the vapor will come to the top and not be driven even deeper underground? So Garrett, if you're there, go ahead and reveal yourself.
Yeah, I was really hoping I was able to answer this one because I meant to mention this in one of my later slides. But unfortunately, just with nerves, forgot to mention it. So as this volatile or H2O sublimates, it can transport in any direction, right? And I think that's what she's asking about. And so, however, basically, as it transfers into the colder regolith, it's going to potentially phase change and deposit, which is going to fill that pore and make it less likely for additional vapor to transfer further into the regolith. In addition, as you move down into the regolith, you have a density stratification, and it gets more dense as you move down. And so actually there's a lot less resistance for this sublimated water vapor to move up rather than down. And so the answer is it goes everywhere, but the majority of it should actually come out, which is good news for the technology.
All right, thanks, Garrett. Good, great, very clear answer. I was wondering the same thing, and you answered that very well. All right, so Chris, is Chris Zagney still online? All right, perhaps we lost Chris. That's okay. In fact, I'm just gonna put these questions out there in case anyone else from the Viper team or anyone else from the Honeybee team who's been involved in that in the Trident development could chime in on this. But there were a couple of questions. So Kevin Cannon had asked whether there was any concern about tribocharging when using Trident in PSRs. So if Tony or Dan or anyone else on the team is online, would anyone like to take that one?
I don't know, this is Jen. I don't know if Tony is still on the line or not, but that has been looked at and has been looked at during the testing. I don't know how much of that is publicly available or not. So I'd rather have Tony address that.
All right, thanks, Jen. And next we had Shuai Li. So Shuai asked whether the drill would create enough heat to melt water ice and other potential ices such as ammonia or methane. Anyone want to take a crack at that?
So again, that has been also addressed in field campaigns and in testing, and no, we should be fine in that respect.
All right, thanks, Jen. You are going to be our point person for the last Viper question, which is a little more technical, but this one was from Deep Joshi, who asks if there are plans to use the drilling data in real time to optimize those operations, and whether the drilling data would be used to get at stratigraphy. So I think the answer to the second part of that is yes, that there are plans to sort of take bites and get at stratigraphy. Jen, do you have any idea on whether there are plans to use the drilling data in real time? Is that something that can be done? I know you've done a lot of work looking at the ConOps for a mission like this.
Yep. Yeah, the short answer is yes. And not just the drilling data, but all of the other instrument data and rover telemetry data as well. So that's one of the beautiful things about doing this mission on the moon, is that we're so close that we can essentially operate in near real time. And so it is part of the science architecture and the science operations to be getting that data that's being collected from the rover back to the mission control center and to the science backroom team, so that we can make decisions and make tactical operational decisions in real time using what we've learned from the data that the rover is taking back. And this is one of the exciting aspects of this mission, and also one of the challenging aspects, because we have never operated a planetary rover in this manner before, taking near real-time data that's coming back, assessing that information, making sense of it, and then turning around and making tactical decisions to affect the actual operations of the rover itself. So the answer is yes, and that's, I think, one of the most interesting parts of this whole mission.
Right, wonderful. I certainly agree with that. And I was doing my best to keep track. I think those were actually all the unanswered questions we had. I think the speakers and everyone sort of chimed in and had a very productive discussion on the chat. But was there anything else that I could ask an hour of questions myself, but I'm not going to do that because the posters are much more interesting. But does anyone have any other questions? And
I see a hand raised from Pascal. I just don't know if that's the same question that Masaki talked about, or if he has another question.
Oh, right, Pascal.
That was the same question. Thank you.
Okay. Just, no problem.
But it was a very good question.
Okay, well, thank you. I think if we've got through all the questions, we don't need to expand the time. It's meant to be as long or as short as needed. So thank you to everybody. And I'm going to go ahead. We have a few people here, and Greg will make this announcement again in the morning, but our team, Ashkan Najad and Maria Luis, they worked very hard to make everything ready for the poster session. So I just want to thank them. And I think everybody should go off to the posters that they're interested in. So thank you very much.
Bye, everyone.
Bye-bye. Thanks for a great session.
Bye, thanks.